Hello, and welcome to the machine learning course brought to you by firstmentor.com. I am Rishabh Sarkar, and I am going to be your mentor for this particular course. Firstly, I would like to congratulate you to take a step closer in understanding machine learning to its very heart or to its very depth by taking up this particular course. A brief introduction about me. I did my bachelor's in computer applications from Symbiosis, and I went on to pursue big data analytics from St. Joseph's College. So, what all are the things that we're going to do in this particular course? We're going to look into the theoretical aspect of machine learning. Then we look into the basics of Python and understand the language a bit better. Then we do a bit of basic statistics where we apply few formulas to understand statistics a bit better. It's not going to be very difficult. It's just the basics so that we understand what all machine learning is built on top of, as statistics is the basic thing that uh, forms a foundation, a firm foundation for machine learning. Then we look into EDA, which stands for explanatory data analysis, which is nothing but a particular step that we do before jumping into machine learning, where we understand everything that we can by using visualization techniques or some other techniques that we are going to do in this particular course, and try to infer everything that we can from the data. Then we look into the heart of the particular course, that is machine learning and its various types. We're going to look into and work with all the algorithms that come under machine learning. Then we look into ensemble learning, which is not tough. It's just the advanced version of machine learning where we use various algorithms together to make our program way more rigid and perform better on a particular data set. And then we go on to the final step where you guys have a particular data to work on and apply all the knowledge that you gain from this particular course. So without wasting any more time, let's just jump to it. In this video, we are going to look into the theoretical aspects of machine learning. So, what is machine learning? According to books and what Google is going to tell you is that machine learning is a branch of artificial intelligence and computer science which focuses on the use of data and algorithms to imitate the way humans learn and gradually improve accuracy. Well, that might be a bit difficult for people to understand who are diving into computer learnings or machine learnings for the first time. So let's just concentrate on the layman definition, which says that it is the use of data to help the computer understand various patterns, which helps it make better predictions. Let's take a real life example to understand this. If you are a student and there's a teacher overlooking you while you solve a particular sum, the teacher is overlooking you because he or she knows that you're bound to make mistakes. And he or she is present over there so that whenever you do so, she or he is there to guide you and tell you that what is the right solution. Let's look at the picture now where we see that there is some data and we try to find some pattern, and then we tell the computer to analyze and understand and learn these patterns. Now, through this entire process, there is a person on the right overlooking this entire process just because the machine should not learn something that is wrong. If a machine learns something that is wrong, it's going to keep that in memory and always going to and will always predict something that is wrong. Why do we use machine learning? Well, machine learning helps us predict better. It is approximately knowing what's going to happen in the future, where the key term is approximations. We when we use machine learning, people feel that we are able to predict the future. We are able to predict the future. That is not a wrong statement, but it's an approximation. It is not actually what's going to happen in the future. Well, we'll look into a few of the case studies that I've mentioned here in detail in the upcoming slides and understand where are these algorithms used in particular so that we can understand the scenario a bit better. Well, we have stock market price predictions here, which is quite a generic topic for machine learning enthusiasts. So we all know that stock market has huge variations in prices every seconds, and there is tons of data that is generated on a regular basis. So understanding the data and trying to find patterns and informations is a basic machine learning uh, example. And this is from the financial sector. Let's look into the entertainment and the sales sector, where we have the recommendation system. So what is a recommendation system? A system that looks into the various factors it is provided with and then makes similar suggestions based on that. So the recommendations made by the program can be judged on the basis of how appealing are they to the customers. So if the particular program that you have written, the recommendation program that you have written works perfectly, the GIF on the right is going to come where the person just looks into all the recommendations and just consumes them without thinking twice because he or she likes them. So we do encounter recommendation systems on a daily basis. YouTube uses a recommendation system to uh, cater to your needs in particular. Then we have Amazon and Flipkart giving you recommendation systems below the product that you're looking into. So we are going to look into these and we are going to try out these in the upcoming videos. So the next field that we're going to look into is all fields. Yeah, so basically customer segmentation is not something that the customer uh, identifies or looks at like the recommendation system. You can have a sense and feel of it as you go through the various applications. There are recommendations that come below. Customer segmentation is done in the backend by the companies. So what is customer segmentation? This system helps us segment the particular customers into various groups. This is from the company's point of view. So the customers are segregated and separated on the basis of a few factors. So what are factors? Factors are nothing but attributes or characteristics. So how do you identify a person and an elephant? So a person will have two arms and two legs. The ears will be small. We do not have a tail. But when we come to an elephant has huge ears. It has four legs. It doesn't have any hands. It has a small tail. So you know that, yeah. So that's an elephant and this is a human. That's how we basically go on to segregate them on the basis of various characteristics. So if we take a normal example of telecom industry, considering that you are a prepaid user or a postpaid user, which kind of plan do you prefer? Are you planning to shift? If you're planning to shift, then the particular company needs to cater to your group, to your specific needs, and provide you offers that will be appealing just to you. Now, that's where customer segmentations come into play. The next segment that we're going to look into is insurance, and the topic that we're going to discuss is fraud detection. Now, this is one of the most important topics in the current world, where due to the advancement in technology, there is a huge uh, demand for these particular softwares where you can identify frauds from the originals, where there are some records that are fraudulent or which are frauds, and there are some normal records from the insurance perspective. And the insurance companies want to identify, okay, this is a fraud and this is a normal transaction. So how do you do that? We are going to look into them as well in the upcoming videos. But to understand that these segments do use machine learning to identify or have a basic approximation. Okay, this record can be a fraudulent transaction, or this record may not be a fraudulent transaction. Credit card, credit card for fraudulent transactions is one of the use cases that you might find in the news quite often. So this is an important topic that you should look into, as like if you want to research a bit more about it, feel free to do that. It's obviously going to help you. So the common question that I hear a lot is, how do I start? After hearing all of this, it might be a bit confusing, like the man on the right. But to be honest, it's not. You need to, there are a few basic necessities to understanding machine learning. Well, after hearing the requirements, please do not get afraid. It's nothing like you need to know it exactly, but it's good to have that information with you. So you need to know a bit of coding, you need to know a bit of stats and math, and that's all for you to get started. Now, if you do not fulfill these requirements, there's no need to worry because the course will cover all of these. And only after we cover all the bases here will we dive into machine learning and understand it from the core. What language is the best to code in? For beginners, I feel Python is the best language to code in because of the English-like syntax, and there's a huge number of libraries that you get to choose from, and you just need to install them. Uh, and import them and use them accordingly for your own particular use. And you do not need to code everything from scratch. The other programming languages have libraries, but they are not as extensive as Python because it's open source and there's a lot of contribution that happens globally. Then there is the open source thing that we just spoke about. Because it's open source, anybody and everybody can download it without paying a single penny. But that doesn't mean that you cannot code machine learning algorithms in other languages. There are other languages that can be used for machine learning. R is one of them. You can even do a bit of machine learning on Java. But for this particular course, we'll stick to Python due to the advantages that we just discussed. But I would highly recommend people to go outside this particular course's curriculum and try out machine learning algorithms on different languages. It's going to be good for you in practice. Well, that's all for this particular video. A small note at the end, when you download these particular presentations from the resources folder, you do make a note that there is this presentation note that comes below, and you will find small notes over there. Like for example, when we spoke about factors, if you do not remember them, you can, if you do not remember the definition that I gave at that moment, you can always refer to the notes section or the presenter notes section below. That would be all. See you in the next video. In this particular module, we're going to look into the various statistical methods which form the foundation for any machine learning method. So what are the things that we're going to look into in this particular module? We have descriptive statistics, we have probability and conditional probability, we have the various probability distributions. We concentrate on the main three, that is binomial, Poisson, and normal. And last but not the least, we have inferential statistics. So what is statistics? This is a practice or science of collecting and analyzing numerical data in large quantities, especially for the purpose of inferring proportions in whole from those in a representative sample. Well, it's obviously a big bounce. So let's look at the more simpler definition that we all understand. So basically, it's a branch of science that deals with numerical data. It is mainly used to infer knowledge about big sections, or we can call them parts or proportions, by trying to understand a smaller section of that bigger chunk. So basically, the concept of population and sample come in here. So a population is considered the entire data. So if you want to say, if you want to talk about an example, or let's take an example to understand this better, we can say that all the people in a particular state can be called as the population and be referred as the population for our particular experiment of whatever purpose we are taking that population into consideration. So a sample would be a part of that particular population. So if you say that, okay, so there are a few states in a particular country and I want 10 to 20 people from each and every state. So basically what you're doing is you're taking samples from those populations, or you can say the entire country is a population here and you're taking various samples from various places, which in turn will represent the entire population. We're going to look into details and you'll understand this better as and when we come across various factors. So why do we need statistics? And I know that you already got that, but let's just have a look at it. So the major reason is that it helps us understand data better. So if we understand the data better, we are going to work on it better. When I say we are going to work on it better, basically what we are trying to say is that we're using various statistical tools and methods to understand the data better, or you know, we are using particular tools and techniques to come up with some outcome, come up with some understanding. Correct. That brings us to our next point. When we work on it better, our deliverables or outcomes after working on the data turns out to be better. It's as simple as that. And all of this is possible just because our statistical methods help us to understand the data better. Kinds of data do we deal with? So I've been tossing around this word data for quite some time now, but I haven't explained it in detail. So the first thing you need to understand is that data can be structured or unstructured. When I talk about unstructured data, it's basically something that is way more complex to see, visualize, and understand. An audio file will have various wavelength. It has various channels. If I have to say it in a way, there is mono and there is stereo, and there are various other factors which make it difficult to just look at and understand. Whereas, on the other hand, we have structured data, which is in the tabular form where there are columns and rows, which makes it very easy for us to understand just by having a look at it. The best example for any structured data would be an Excel sheet. And I'm hoping that everybody here at least has seen an Excel sheet, if not have worked. Well, the entire data over there is just represented in columns and rows, which makes it really, really easy to understand. Now, there are other divisions of data as well. The singular form of data is called datum. Many people do not know that. Even I did not know that for a couple of years. Yeah, so the main two divisions that data can have is numerical and categorical. So when I say, okay, how many legs do you have? You say two. How many hands do you have? Two. How many eyes do you have? Two. How many nose do you have? You have one. So basically, all these numbers or anything, any data that you can represent in a numeric format comes under this particular category. But when we say about categorical data or quantitative data, basically we are talking about something that is more of textual. What do I mean by that? So when I say, okay, what's your gender? You either say a boy or a girl. You do not say 0 or 1. Correct. So that's how categorical data is different from numerical data. Numerical data is also called as quantitative data. Now the higher divisions, we'll look into them one by one. Let's look into the numerical aspect first. So we have discrete data and we have continuous. So the major difference between them that makes it different is that discrete data concentrates more on whole numbers. How many children do you have? Two. How many how many people do you have in your family? Three or four, whatever number that is. So it's basically it deals with whole numbers, but when we come to continuous data, it basically deals with decimals. So when I say what is the balance, what is the current balance for your savings account, you'll say okay, it's somewhere around 12,050.6 paise or 60 paise or 70 paise or 60 paise if you have to put it that way. Or you'll say that, okay, what is your height? My height is 155.55 centimeters. It's not always necessary that your height will be 155. Or if your height is 154.99, it is not equivalent to 155. You're rounding it off, which obviously tells you why we need two different types of numerical data. Correct. Let's move on to categorical data. So we have binomial data, we have nominal or unordered data, and we have ordinal data. Well, the words might sound really, really confusing, but to be honest, they are really simple. So let's look at binomial data. So the word bi means two here. and any particular outcome which has only, sorry, what I mean is any particular answer or solution which only has two probable outcomes makes it come under this particular category. So when I say, if I toss a coin, what's going to be the outcome? It's either going to be heads, it's going to be tails. Correct. That's how it comes under binomial. So let's look into nominal. So nominal is where the categories come into play, but they are not in orderly format, or you cannot rank them. So when I say, okay, how many t-shirts do you have? Or what are the, so you'll say three, and what are the colors? So you go on to say, okay, I have red, green, and blue. So if I ask you to order it, the very next question that you will have is, okay, so how do I order it? You red is not higher in power or higher in hierarchy than blue. So how do I order it? That's where ordinal data comes into play. Well, you're not going to order it by color, but there'll be some ways of ordering it, correct? So if you go on to see in any clothing brand, when you go to visit in the mall or any particular shop, they always order their particular clothing in an ascending order, where you have the smallest size first, and then it goes on to the largest size that is possible for that particular brand or that particular clothing. So you see what I'm trying to point out here, right? So ordinal data is basically data that you can rank. When I say that who are the top three scorers from a particular match, you say, okay, there is player one who scored the highest and is the best. Then there's player two who scored good, better than three, but not as good as one. So he is in the second position. Now, when you say, okay, so the third player did better than the rest, but not as good as player 2 and 1. So is in the third rank. So you order them, you can order them. That's ordinal. We understood nominal and binary. So that's what you need to know about the data and its various types. So in this video, we'll concentrate on descriptive statistics. So what is descriptive statistics? So basically, these are variables that help us summarize the data that we have, which can either represent the entire or the part of the population that is called the sample. Now, considering that we did understand populations and samples, we're going to move ahead. And basically, we see here that there are two major branches of descriptive statistics, one being measures of central tendency and the other being measures of variability or spread. We're going to look into the measures of central tendency first. So measures of central tendency when this particular phrase, if this particular phrase is set to some, the first thing that comes to that particular person's mind is that it's something related to something that's in the middle, center. So when we say measures of central tendency, we basically are talking about three things: the mean, the median, and the mode, the three M's. So the mean is nothing but the average of the data set, which is also sometimes referred as the expected value. It's basically the average of the population or the sample. The value gives us an approximate idea of what the entire data set looks like. So on the right, we have an example where there are three bins and each bin has a few balls. Now, the first bin has 5 balls, the second bin has 6, the third bin has 7. If I ask you to find the average or the mean of this particular question, it's a basic addition and division problem. We add in 5 and 6 and 7 and then divide it by 3 and we get 6. It's as simple as that. So that's what mean generally is. So this is how we write the formula for mean. So there are different notations that I'm going to explain. So this is x bar. We call this x bar, which basically represents mean as given here. Then we have the summation sign and x. This is called sigma, which basically means some direction. divided by n, which represents the number of observations. So if this is difficult for you to understand and remember, the basic thing is summarization of the values divided by the total number of observations gives you mean. That simple as that. The question says that there are three baskets, A, B, and C, and they have 12, 14, and 22 apples respectively from three different locations. Now the farmer, Mr. Orchard, a wild name, to be honest, wants to know how many apples on an average does he have. So it's a basic sum. We have the numbers here. We have 12, 14, and 22. We need to add them up and divide by 3. And we get the answer as 16. Simple, straightforward. Let's look at a different example. So you can see that the question is same, but there is this one value which is a bit different. It was 22 earlier, it's 220 now. Well, that's not a typo. It's done intentionally. So I would really want you to pause the video here and solve the sum out yourself. Considering that you did solve the sum, let's look at the answer. So the answer you should have got is 82. Now you see that it's way bigger than what we got earlier. And just because that there is this one particular uh, value that pulls the mean towards itself. Well, the mean is the average, or it says that, okay, if you have three places on an average, you get somewhere around 82 apples from each place. Well, it doesn't seem so. We have 12 from A and 14 from B. So is the question wrong, or did I teach the wrong formula? So don't get scared. The question and the formula is right. So 82 is the correct answer. But if you want to see, is it the actual correct answer? What I mean by that is 82, or the mean value, represents that on an average, uh, this is the value that you should get out of each basket, or approximately this is the value that will be near to the values from all the baskets. But that doesn't seem to be the case here. We have 12 and 14 in one of the baskets and 220, which basically says that this basically doesn't make sense. Correct. So why is this happening? So the value over here, 220, is called an outlier. So an outlier is something that doesn't fit into the general stream of data. So when you open a particular shoe rack and you see shoes that range from say 6, 7, and 8, it's understandable that okay, these are normal shoe size. But on the right, you see that there's a shoe that is really small, say a size that is round about 2, or you see a shoe that is really big, say a size of 13, which is enormous. And because of these points, the entire data is kind of shaken up, and the mean goes on to bend or is pulled towards these outliers. So are we done here, or does the mean doesn't make sense? It's not that. We're going to look into how to solve this problem in the next video. In the previous video, we saw that our mean value was pulled because of something called an outlier. Let's understand the outlier a bit better before going into trying to solve this particular sum in some other method. So basically, this is a small dummy data set where it's a small party or a gathering of a few employees or people. So there's Mr. X who has an income of say $1,500. There's a Mr. Y who has an income of $1,200. Now there's this giant who comes in, Elon Musk, and has an income of $1 billion. Now, just because Elon Musk is a part of this particular data set, the mean approximately jumps to $333 million. If you just consider the two people on the top, the mean would be somewhere around 1350. But just because Elon Musk is a part of the data, the mean approximately jumps 10, 20, or 100 times. So that's what an outlier does to your data. So let's look at the definition before going into the formulas. So median is the middle observation after the observations are arranged in the ascending way. In this way, it is not affected by the outliers. Now, how does it do that? So let's just look at the formula for now. So median is n plus 1 divided by 2. So if you have three records, the middlemost observation will be 2. That makes sense. First, second, third. Second is the middle value. Now, what happens when the values are even? So say if you have four records, what do you do then? What is the middle value? 2.5. Well, there is no 2.5 record. So what do you do is n by 2. N by 2 is 2. So 2th observation plus 2 plus 1, that is 3, and the third observation. So you take in the values of the second and the third observations, considering that there are four observations now. So you take those two, add the values, and then divide that value by 2. Having a look at these particular formulas, let's understand them better with the help of an illustration. So coming back to the very same example that we couldn't solve with the help of mean, we could see that the mean was somewhere around 3,300 million. But if we consider the median formula, we are getting somewhere around 1,500. Now, how is that? So if we go on to arrange this particular data set, 1,200 will be on top. After that, we have 1,500 and then the 1 billion. Now, there are three observations. So going back to the formula, we can see that the formula is n plus 1 by 2 because the number of observations is odd. So over here, it will be 3 plus 1, that is 4. 4 divided by 2 will give us 2. So that is basically the 1,500 value that comes in the middle. You understand what happened here? We came down from this to this, which is the actual middle value that should have been here. Just because of the outlier, we are getting a different value. So median helps us get the middle value. Let's look at a different example for median so that we have a better idea. So we have four families that are going to meet in a restaurant, and the manager asks the host, so what are the number of people per family on an average that are going to come so that he can make the arrangements of the table accordingly. So the host recollects that family 1 has 3 members, family 2 has 4, family 3 has 5, and family 4 has 5 again. So now he can't say that, okay, you make 3 chairs here, you make 4 there. So he gives you, so how does he give an average value? So the okay, so let's just do the mean calculation here. So the mean should be 3 plus 4 plus 5 plus 5, that is 17. Now, what is 17 divided by 4? It will be 4.25. Now, you cannot have 1/4 of a person, right? Coming back to the median over here will be the second value plus the third value divided by 2. So 4 plus 5 divided by 2, that is 4.5. This seems to be wrong as well. And why is that? Because we cannot have a half a person sitting in one table and half of a person sitting on the other. The concept of mode comes in then. Now, what is mode? Now, if you thought that mean is the most easiest to calculate, let me prove you wrong. Mode is supposedly the most easiest central tendency value calculator. So what is it? Mode is the observation with the highest number of occurrences, or in statistical term, we call it frequency, in the data. The data doesn't need to be arranged. We can identify the mode just by glancing over the frequency for each observation. Consider that there are 10 people and we just go on to add in or take a frequency count of all their uh, customers, or how many customers they go on to add in to the particular company on a for a particular week. So if I go on to say that who got the most, who has the highest frequency, it is easy to identify that it is the person who comes here, the person who has the ID 6. Makes sense, right? Let's look at a different example form. So there were a few people, and they were all asked to check their pockets and take out any amount of change that they had in their pockets. So the one person had 8, 5, 7, 10, 15, 21, 5, 7, 2, 5. These were the values that each and every person had in their pockets. So if I go on to say what is the mode for this particular data, you say that 2, 8, 10, 15, and 21 occur once. So that is okay. But let's see if there is any other value with higher frequency. So we see that 7 occurs twice in this particular data set. Okay, that's better. But is there something better than this? We see that 5 occurs 3 times. So according to what we just learned, just because 5 has the highest frequency, that makes it the mode. Going back to the very same question that we encountered earlier, where the restaurant problem, we go on to see the same data over here. So now we have 3, 4, 5, and 5. Now the median gave us values in decimals, and we cannot have people cut into halves or quarters. So basically, if we take mode, we can just say that, okay, you do one thing, manager, you can have 5 chairs, and if there are people lesser than that, the seats can just be empty. Makes more sense, right? So that's how we have 5 as the best answer for this particular problem. So you see that there is no one particular method that conquers all problems. Somewhere you need to use mean, somewhere you need to use median, somewhere you need to use mode. That's exactly what I wanted to point out through this particular presentation. Now that once we are done with mean, median, and mode, let's look at a few terminologies that might come in handy. So we have bimodal here. What is bimodal? So bimodal is nothing but your data now doesn't have one single value with high frequency. It has two uh, values which have high frequencies, like the graph on the right. Let's take a basic example to understand this particular guy. Say that you are a shop owner and you want to see the distribution for your beverages. Now you will have a distribution something like this, showing that there are two particular beverages that are highly in demand, or the demand outrun the others. So generally, you will have tea and coffee running out all the other beverages. Like if you go on to see the consumption of tea and coffee compared to say something as general as say green tea or some other beverage that is common, you will see that tea and coffee is highly preferred, and that's the best example that you can have for this to understand this particular distribution. Now, I've been talking about the bell curve, and you saw the mean and the median, and how do we go about it. But what is the bell curve? Like, we understood the shape of it comes from the bell shaped thing, but what is it exactly? So the bell shaped curve basically says that if we go on to take a random group of people. Let's take an example to understand this. Let's just say that we take a random group of people from the crowd, and you take in all their ages. Now, after making a tally of each and every age, you will have a distribution that looks something like this. So that makes sense. You will have very low number of people with say age of 0 to 5. There'll be kids. Basically, there'll be very people generally do not go out with small kids or something like that. And you will have very low number of people with high values, say a somewhere around 90 to 100. Correct. So the values in the middle the teenage or adults or just adults, whatever you want to term them as, will have the highest frequency. That makes sense, right? So that's what the bell curve shows us, that the distribution will have, as we go towards the mean or the middle, we're going to see that there'll be high number of people coming in this particular section. And as we go towards the ends, the the distribution will have lower number of people towards the end for this particular example. Now we understand something called the skewness. Firstly, let's get these two terminologies in our head. There's something called the negatively skewed data and there's something called the positively skewed data. Now, obviously we got terminologies, but what do they mean? So if you want to see, the bell shape over here is a bit crooked and has the bell towards the right, and there's a small end that comes out from here. So now let's understand the terms here. So this bell is also referred to as the hump, and this is called the tail. Now, on the basis of the tail's direction, we term the particular shape of the curve. Now, just because the tail is towards the left, we call it negative. It's in the negative direction, and we call it negatively skewed. The opposite happens in positively directed graphs, where the tail is towards the right and the hump is towards the left. You can either remember it from the hump's perspective or the tail's perspective. But in statistics, we generally take the tail into consideration and then go on to describe the particular graph. Now, what happens in this particular graph is, as we saw in the earlier examples, because of the outliers, the mean value gets pulled towards the outliers. Correct? You can see that over here as well. There is some value that is very, very high, and that pulls the mean from the middle. We can see that the median, as it is, divides the particular data into half for both the cases, and mode over here goes on to show what is the highest value for each of the data, being showing us the peak. Now, if you do not get time to plot the particular data and have a visual visual feel of the particular data, what do you do then? Well, there's another way of identifying it. As we can see here, if the mode value is greater than the median and the median value is greater than the mean, it basically signifies that your data is negatively skewed. And if the positive value, if it's positively skewed, you will have mean as the greatest, median being in the middle as well, as usual, and then comes in mode. Now that we have an understanding of the measures of central tendency, let's look at the measures of spread. So in layman terms, measures of spread is a measure that gives us an idea of how spread across the data is. So just because the data has same mean, median, or mode, that doesn't tell us that the two data sets are similar in nature. So there's a brief explanation of how the graphs would look with the same median and the same mode, but with different spreads. Let's look into this in detail. So there are two classes with 5 students each, and the obtained marks are as follows. So the class 1 has a person with minus 10, 0, 10, 20, and 30. Yes, the value or the marks that this particular person got is minus 10. It's not there by mistake. There are examinations where you get negative marking for a particular answer. So this guy might have just got on. And in class 2, we have 5 students with marks 8, 9, 10, 11, and 12. The mean for both the classes are 10. Taking that into account, can you say that the data sets are similar? Take a moment to think this out, and you can even scratch out the mean calculation here just to cross check. But think for a moment and then I'll share the answer. Now, well, the answer is no. The data have a different spread if you go on to see. And how do we look at that? So let's just consider the range for the classes. So the range is nothing but the maximum value minus the minimum value should give you the particular range of that data. So the class 1 has a minimum value as -10 and the maximum value is 30. So that gives us a 40 unit spread for class 1. Now class 2 on the other hand has the maximum value as 12 and the minimum value as 8. So that gives us a class spread of 4 units. So for this particular case, we see that the range gives us a pretty good idea of how spread across the data is. But it generally doesn't need to be the case all the time. There might be cases where the range is same, the mean is same, and we interpret that, okay, the data sets are similar in nature, but they turn out to be something different. Let's look into this. So why range isn't the best way to understand this? Like we saw earlier, that sometimes the best of methods also fail to give us a correct interpretation of the data. That's why we use the alternatives to balance out the pros and the cons. So range is no different. There might be cases where the mean is same, the data range is same, but the value differ, telling us that the data might have a different spread. So if we go with range all the time, we might end up with a completely different interpretation. Well, it's funny because it's true. So let's look at some other ways of finding out the spread as well. There's something called the variance, which is nothing but we go on with the same definition with some wordings. So it means it's basically a measure of how data points differ from the mean. So in the layman terms, it is a measure of how far a data set or numbers in that particular data are spread across from the mean. So how far are they from the mean or the average value? And the formulas are listed here. So this is a letter called sigma. It's a Greek letter which defines variance. Sorry, sigma square defines variance. And the formula is this is also sigma, and summation minus mu. This is also a letter which defines the population mean, the square of that divided by n. And s square is nothing but the variance of a particular sample. Now, I hope we are clear with the difference between populations and samples. But this is the formula for sample and this is the formula for population. The only difference is that the number of observations is reduced by 1. Now, there is a statistical and mathematical explanation to why is this so. But for the basic understanding, we'll just take that in that the number is reduced by 1. And the main reason is uh, that the variance that we calculate for the sample, if we reduce it by 1, it's nearer to the population variance, which technically is what we want. So for now, we look into this and we go on to see how variance works. So we take in the same example again. We have classes with the same values, students scoring the same marks, and we calculate the variance here. So class 1, we have -10 whole square plus 0 -10 whole square, and then we go on and if we sum all the values in the numerator, we come up with a value 1000. Now divide 1000 divided by 5 gives us 200. That's known. Class 2, we calculate the values in the similar way, and we find out that the value is 2 for this particular case. Now, if we look closely, we see that we came across the ranges and we saw that the range is higher for class 1. That means that the data is more spread. The variance just confirms that particular interpretations for us for this particular example. As we discussed earlier, that range may not be true all the time, but variance gives us a better idea. Now, variance is not the ultimate solution again. We look into something called the standard deviation. So the standard deviation is nothing but the square root of the variance. So it is a quantity expressing by how much the members of the group differ from the mean value for the group. So the formula is same as the variance for this particular case, and we just take the square root of it. Let's take the example into consideration and understand this better. So we have the same question again, and we see that there's this square root symbol that's added onto the entire sum. So the square root mind you, the square root symbol is for the entire thing and not just for the numerator. It's for the denominator as well. So we calculate the entire thing. It should be the value should be root under 200, and if we go on to calculate it further, it will be 10 root 2. Now for class 2, we see that the value comes down to root 2. Now what does this mean? So we have values of class 2 and the standard deviation of class 2, and we have values of class 1 and standard deviation of class 1. If you go on to see, the values for class 1 are 10 times more spread out than the values of class 2. That's what the standard deviation says. Don't take my word for it. That's what the standard deviation says after we calculate this particular thing. Correct. So if x is root 2, 10 into x will be 10 times of the value. That's what it means. Now that we've understood that, let's just try to justify our answer for the standard deviations. So if you go on to see, the value for mean was 10 for both the classes. But according to the standard deviation, what it says is the units are 10 times spread across compared to class 2. Now if you go on to see, the values that are nearest to the mean for class 1 are 0 and 20, and they are 10 units apart from each other. And if you go on to see the values for class 2, 9 and 11 are the values nearest to the mean, and they are 1 unit apart from each other. Doesn't that make sense? Like 1 unit apart from each other and 10 units apart from each other. Do you see the pattern? Well, if you didn't, and what I'm trying to say is that for every unit difference in this class 2, there is a 10 unit change in class 1. Let's take take in the other set of values that are there, the extreme values. So here we have minus 10 and here we have 10. So from 10 to 0 we have 10, and 0 to minus 10 we have another 10. So there's a 20 unit change. But if you go on to class 2, we have 8, then 9, and then 10. So there's a change of 2 units. So that solidifies our interpretation of the data by using standard deviation. And that was what we need to understand for standard deviation. Well, the first thing that came to my mind after I did standard deviation was, what is the problem with variance? Now, it's going to give us the same answers, just the square root of it. So, taking the previous example, we see that the value for classes are marks, correct? So these are, as I said before, these are the marks of individual students. Now, when we take the variance into consideration, we get the final value in terms of marks square and not marks, which doesn't make a lot of sense. It's like saying, okay, how much do you earn, sir? And the particular person replies that, oh, I earn $1,000 square, which doesn't make sense. Like, what is the guy trying to say? How much does he earn? It leaves you confused. That's the very reason we use standard deviation to remove the square. When we take the root of something, the square is removed, as simple as that. So if I take the square root of marks square, it will be nothing but marks, correct? So that's all that you need to know about measures of spread in general. The topics are really, really vast, but this is all that you need to know for basic understanding of the topic. So today we will learn a bit more about probabilities and a few other things. Well, Why are we going to do this? Because it's kind of an important topic when you go on to see machine learning and artificial intelligence. We basically talk a lot about probabilities when we are talking about accuracies or how good your model is performing. That again boils down to accuracies. So probability is an important factor. So you should pay more attention to this particular video. So what is probability? So probability is the quality or state of being probable, the extent to which something is likely to happen or be the case. So let's just have a more basic definition as usual. So basically it tells you the chances of an event to occur or not to occur. We can quantify it in terms of fractions, decimals, or in terms of percentages. Now, the important factor that we need to keep in mind is that when we are trying to express it in terms of fractions and decimals, the value will always be between 0 and 1. So the probability of an event happening can be 0.5, 0.6, 0.9, but it can never be 1.2. I hope you get this point. But when we are so basically you are going to say that okay, there's going to be between 0 and 1%. No, that's something that's wrong. It's a wrong concept. So basically, when we go on to convert it to percentages, 0.5 is basically 50%. 0.9 is 90%. 0.99 is 99%. And 1 stands for 100%. That's how you go on to convert fractions and decimals to percentages. So the formula for calculating probability is pretty simple. So A is the event and the probability is denoted by P, and you read P brackets A as P of A or probability of event A. And the formula is pretty simple. It's right there. It's the number of favorable outcomes for event A divided by the total number of outcomes. We'll look into a sum to understand the formula better. So what is the probability of getting ahead for a fair or an unbiased coin? So fair and unbiased are the same uh, size of two coin, if I have to put it that way. Fair and unbiased do mean the same thing, and people do get confused when they see this. So remember that. So we know that the event over here is getting ahead. So A is getting ahead, and P of A is the number of favorable outcomes divided by the total number of outcomes, as we saw earlier. So the number of favorable outcomes for head is 1 because there are only two sides to a coin, head and tail. So head is one of them, so 1. And the total number of outcomes can be either a head or a tail. So there are total 2 outcomes. So you divide 1 by 2, that is either 0.5 or 50% or half. It's up to you to represent it in the same way, but it goes on to mean the same after all. Let's look at a different example, which is a continuation of the first one, but it is a bit different. So here we are not finding the probability of getting ahead. We are trying to find the probability of not getting ahead, in considering that it's a fair or an unbiased coin again. So here we have an event B, which says that what is the probability of not getting ahead, or you can simply say that what is the probability of getting a tail. Now for this particular case is the same. So there are total outcomes, and tail is one of them. So 1 divided by 2, and the answer boils down to the same thing, that is 0.5 or 50% or half, however you want to say it. Let's look at a different example to understand the concept better. Now this would be a right time to get your scratch pads out and scratch the calculations to understand this. So what is the probability of getting a 4 in a roll of a die, considering that it is unbiased? So again, the concept of unbiased comes in that the it's a normal dice with 6 sides, and each of them have the respected numbers. There is no tampering with the die. So basically, there are 6 sides. 4 is one of them. So an unbiased die has an equal chances of getting any of its sides. The same goes for the coin as well, which means that all the sides are equally likely to occur. Now, equally likely is another term that you should take that into consideration because it's going to occur a lot of times. You're going to hear it a lot of times. So basically what it means is that all the sides have an equal chance of coming, or you rolling a die and a 4 coming or a 6 coming is equally likely. So the probability is equal. Now, for our case, the event that we are looking for is 4. So we getting a 4 is our event. So A is getting a 4. Okay. So now the probability of event A occurring is 1 divided by 6. Now 6, because there are 6 sides to a die, so 1 divided by 6. That's how we understand probability in the basic terms. Now, what is union and intersections? So this is an important thing again, because we do not just find what is the probability of an event occurring. We also see the dependencies and the relations and try to find them out. It's the data is not always available to us, and we need to still look into and find the values for the events. So these are some important topics. So the signs might be confusing, but they do kind of mean the same thing. So I remember it this way: U stands for union, and the other way is the intersection. So intersection means that it's a common area between the event A and B, or you can say that. So these are, I usually take a Venn diagram into consideration to understand it. So murdered parents and Alfred have a common intersection. This is this area, and A union B is the entire area of A and B. So basically it means the entire area that you need to consider can be called as the union. The formula is pretty simple as well. For intersection is the probability of event A occurring into probability of B occurring, and for the union is probability of A plus the probability of B minus the probability of A intersection B. Now the main thing that you should observe here is that we are subtracting the intersection here. Now if you think closely, it's pretty logical, because there are two circles and I'm considering one circle, I'm considering the second circle, and if you go on to see, they have a common area. Now the common area is considered twice, so we need to remove it once to have the perfect value. Let's look at an example to understand this better. I hope you have your sketch pads out. So there are 52 playing cards in a deck. What is the probability of getting a jack of hearts, or a jack and a heart, however you want to put it? So basically, there are 4 suits in a deck of cards. There's the heart, there's the diamond, there is the club that looks like a tree, and there is the spade that looks like a leaf. So these are the 4 suits, and each suit has 13 cards. So it's a known fact that there are 4 suits in a deck, and each suit has 1 jack each. So there are total 4 jacks. And so there should be uh, so the number of jacks should be 1 divided by 52. Let's test it out. Okay, because we are trying to find the jack for a particular suit that is hard. The value should be 1 divided by 52. For this case, we know the answer, but let's test it out. So the probability of A is getting a jack. So there are total 4 jacks as we discussed, 1 for each suit. And 4 divided by 52 is 1 by 13. Now the probability of event B is, so our event B is probability of getting a heart. So there are total 13 hearts. As we discussed, there are 4 suits and each suit has 13 cards in it. So the probability of event B is 13 by 52, which is 1 by 4. Now if I want to find two events happening simultaneously, or if I want to find the common area, we discussed that it is called the intersection. Okay, so A intersection B is 1 divided by 13 into 1 by 4, that is 1 by 52, as we did the mental math earlier, that the answer should be 1 by 52 logically, and we got that. So the formula does work. Now let's look at the second section of it, where there are 52 cards in a deck. What is the probability of getting a jack or a heart? Here the main point that you need to see is that it was an and here and an or here. So when you say and, basically you're talking about the intersection, and when you say or, you're basically talking about the union. The probabilities remain the same. So the probability of getting a jack is 4 by 52, that is 1 by 13, and the probability of getting a heart is 1 by 4. Now the intersection is also same, it's 1 by 52 as we found out earlier. Putting in these values in the union formula, we see that it comes down to 1 divided by 13 plus 1 by 4 minus 1 by 52. Now, if you do the math yourself, you'll find the answer to be 16 by 52 or 4 by 30. It's pretty simple. Once you have all the uh, points with you, it's just drawing a single line. It's just putting them in the formula and you have the values in front of you. So that's what it is for the basic examples. Now look at some of the anomalies that happen. So what is the probability of getting a 4 and a 6 in a roll of die, considering that it is unbiased? Now, if you go on to think logically, if I roll a dice, I cannot have 4 and 6 at the same time. Correct. So the is the question wrong? No, the question isn't wrong. It's I'm trying to put in this particular thought process into your head that every question that is asked doesn't need to have a very great answer. So let's go on to apply the formulas and test it out. So our event A is basically a 4 as our outcome, and event B is a 6 coming as an outcome. The probability of A intersection B is where A and B both occur at the same time, which is not possible for this particular case, as the Venn diagram also shows. So since there are no intersections, therefore there are no value. Therefore there is no possible value. So P of A intersection B for this particular case is 0. So in this video, we're going to look into conditional probability, which is an extension of what we did earlier, that is probability and unions and intersections. So this should be probably a cakewalk if you did get what we did in the earlier video. So how is conditional probability different from probability? Conditional probability is finding the probability of an event given that the other event occurs. So basically, you're trying to find the probability of an event based on an other event which has already occurred. So the formula is pretty simple, where we have P of B given A. So let's just look at the illustration here. That the event that may or may not occur, given probability of the event that may or may not occur, given uh, the event that already happened. So this is what basically it means, and this is the formula for it, that P of B intersection A divided by P of A. Pretty simple formula. So that's basically the gist of what conditional probability means. Let's look at a few examples to understand it better. So there are two dice and they are thrown simultaneously at the same time. And the sum of the numbers obtained is found to be 7. What is the probability that the number 3 has appeared at least once? So if you want to read the question again, just pause the video and read it again to understand and process it better. So basically event A is where 3 occurs at least once, as we have mentioned here. So what are the combinations? So there are a few combinations. Let's just look at it one by one. So there is 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 6, and then again the reverse 1, 3, 1, 2, 3, 4, 3, and so on. So if you go on to see that the probability of these occurring, there are 11 combinations here. So the probability of these occurring is 11 by 36, and the event B is that we obtain a sum of 7. So basically when I add the two numbers on the dice, I basically get a 7. So 1 plus 6 is 7, 2 plus 5 is 7, 3 plus 4, 4 plus 3 is also 7, 5 plus 2 and 6 plus 1 is also 7. So if you want to see, there are a few common or similar points in both the places. So we see that there are 2 points. So A intersection B is 2. And the probability of A intersection B is 2 by 36. Because there are 6 combinations here, P of B is 6 by 36. You can simplify it to 1 by 6, but it's up to you. I'll keep it this way for easier calculations. You'll see why. So applying the conditional probability formula, we get P of A given B is equal to P of A intersection B divided by P of B. So we found out the intersection value to be 2 by 36 and the probability of B to be 6 by 36. If you go on to do this, scratch it out, and you will see that it's going to be 1 by 3. Okay, this is a pretty simple sum, but let's look at a different sum to understand it better. So in a group of 100 computer buyers, 40 bought brand 1, 30 purchased brand 2, and 20 purchased brand 1 and 2. Pretty rich guys, it seems. So if a computer buyer chose at random and bought a brand 1, what is the probability they also bought computer from brand 2? So this is a tricky one. So there are two brands, and we have the numbers with ourselves that there are a group of 100 computer buyers, and 40 of them buy brand 1, 30 of them buy brand 2, and 20 purchase brand 1 and 2. So the intersection is 20. We got that from here, and there are 40 and 30 for brand 1 and 2 respectively. So probability of A will be 40 by 100, understood obviously. And the probability of A intersection B is also 20 by 100, that is also understood. Now, what are they asking? So what is the probability that the people who buy brand 1 will also buy brand 2? Okay, so we have P of A given B. So we just apply the formula simply that the P of A intersection B divided by probability of B will give us 0.2 divided by 0.4, which is nothing but 0.5 or half, however we want to represent it. So the answer, like if you get these questions, basically you write the last conclusion. Put in a habit of writing the last conclusion. It's going to help you a lot. So the conclusion is the probability that the person bought brand 2 computers given that he purchased brand 1 is 50%. So that's all that you need to know about probabilities and conditional probabilities. And we're going to look into a different section of probability in the upcoming videos. After looking into probabilities, conditional probabilities, now we're going to look into probability distributions. So probability distributions can be categorized mainly into discrete and continuous. So before understanding that, we need to understand what are random variables and what are the different types of it. So we'll look into it in parts in the upcoming slides as well. So random variables play a vital role in probability distributions and also serve as a base of probability distributions. Now, probability distributions is a statistical function which links or lists all the possible outcomes a random variable can take in any random process with its corresponding probability of occurrence. So I hope you understand why am I trying to discuss random variables with probability distributions, because the probability distributions are based on the random variables. We're going to look into the relation in depth in the next slide. So taking an example, we have number of heads and the probability in the table. So if a random variable can take only finite set of values, and well, then they will be called discrete random variables because they will have a finite set of values there, like they can be either 0, 1, 2, 3. So then they are discrete random variables, and their probability distribution will be called probability mass function. Okay, now the probability distribution of a discrete random variable is a list of values of different outcomes and their respective probabilities, as I have listed out here. Now coming to the probability distribution of continuous random variable, that is called probability density function, or PDF for short. Now the probability mass function is called PMF for short. It's quite counterintuitive. So That's the basic understanding of which kind of random variable has which kind of a probability function, probability mass function, probability density function. I think you can remember these two. What is the need of probability distributions? So according to the definition of random variables, is the variable which can hold different set of values from the outcome of a random process. However, it lacks the capacity to capture the probability of getting those different values. So it cannot hold the random variable and the probability. So the probability distribution helps us create a clear picture of the possible set of values with their respective probability of occurrence in any random process. Okay, so that's how we get the entire linkage between random variables and probability distributions and why are they necessary. Now, standard probability distributions are like there are a few standard probability distributions that we are going to look into. There are many, to be honest, but we are going to look into just the standard ones. Firstly, we have binomial distribution. So a binomial distribution can simply be thought of as a probability of a success or a failure outcome in an experiment or experiment on survey that is repeated multiple times. Now, the binomial is a type of distribution that has two possible outcomes that is in the name. So a binomial means bi means two. So there we have it in the name that only has two possible outcomes. Now, the examples of that will be a coin toss, where the possible outcomes can only be heads or tails. And you can also consider taking a test and having two outcomes, either you pass it or you fail it. So what is the criteria for binomial distributions? So the number of observations or trials should be finite, which means that they should be countable. They should not extend to infinity. Now, each observation or trial is independent. In other words, none of the trials have an effect of the probability of the next trial. So if I toss a single coin and then I toss it the next time, the probability of the first toss should not depend on the next toss. That's one thing. Now, the probability of success, that means the tails, heads of or fail or pass as I've listed here, uh, should be exactly the same for each and every trial. So the first coin that I toss has a probability of 1:1. That is, a general fair coin has a probability of 1:1 for tails and heads. Now consider that I have a biased coin and I know that the probability of getting a tail is 2 and head is 1. And it doesn't matter that it's a biased coin, but it does matter if I go on to say, okay, I'm going to toss the 2:1 coin first, that is like the biased tail coin first, and then it's okay, the next iteration I will just use a different coin which considering a different probability. That doesn't happen. The probability should be exactly the same for the number of occurrences. Okay, so that's what the criteria defines. Now, coming to the next kind of distribution, where we have Poisson distributions. Now, Poisson distribution of probability is a probability distribution that is used to show how many times an event is likely to occur over a specific period. In other words, it is a count distribution, if I have to put it that way. So Poisson distributions are often used to understand independent events that occur at a constant rate within a given time period, obviously. So it was named after the French mathematician. You have the name there. So let's take an example. So if the average number of people who buy cheeseburgers from a fast food joint on a Friday night at a single restaurant location is 200, so I know that there are 200 people buying cheeseburgers from a particular food chain on a Friday night. The Poisson distribution can answer questions such as what is the probability that more than 300 people will buy the burger. Okay, and this is the formula by using which you can get the answer to this particular question. Coming to normal distributions, which is generally the most used distribution or the most well-known distribution. So a normal distribution, also known as the Gaussian distribution, is a probability distribution that is symmetric about the mean, shows that the data near the mean are more frequent in occurrence than the data that are far from the mean. In the graph, the normal distribution appears as the bell curve. We have seen this before. And the standard normal distribution has two parameters, the mean and the standard deviation. So we want to look into the detail of standard normal and normal distribution in the next slide. But for general purpose, let's just look into this. So for normal distribution, 68% of the observations are within plus minus one standard deviation. So this is one standard deviation from 0 to 1. So you see that this is -1 here and this is 1 here, and 68.3% of the data lies here. Now going ahead, the second standard deviation will have a total of 95.4%. That's what listed. That's exactly what is listed here. And going ahead to the third standard deviation, we see that we have 99.7% of the data lying under it. So that's how we go on to cover the entire thing. You see that there is exactly 60, yeah, so we have exactly 68.1 under the first standard. Then it goes on to increase 13.6 on both the sides and 2.1 for the last, not exactly the last, but for the third standard deviation, it increases 2.1 on both the sides. So that's how we cover most of the graph. So many things can closely follow a normal distribution: height of people, size of things, size of things, products by machines, or various products and machines, and errors is measured, blood pressure, and so on. So that's something that you can look into. Now, the standard score is basically used to get the standard normal distribution. So the number of standard deviations from the mean is called the standard score, the sigma or the z-score. So once you have standardized the normal distribution, it looks something like this, where the mean is 0 and the standard deviation is 1. Now, one standard deviation might represent different units in the actual distribution based on your data set that you're using. But in this case, like for the example that we have taken up here, the mean is 1010, and one unit, one standard deviation is approximately 20. No, it's exactly 20. So 20 units is one standard deviation, and you see that it's consistent for all the things here. So because this is a perfectly symmetric curve that you have taken into consideration. You see that it's 20 units here again, and you see that it's exactly one standard deviation away. So it basically represents the same thing, but in a way more standardized manner, if I have to put it, which gives us more, more understanding, gives us a better understanding of the data representation in a more concise manner. So to convert the values to a standard score, we basically subtract the mean, then divide it by the standard deviation. We can look at the formula here. Now, why standardize? It can help us make decisions about our data. So we can obviously use this curve as well, but this gives us a better understanding, saying that, okay, a particular point is 3 standard deviations away from the mean. So basically, it's 60 units away from the mean. So that gives us the idea. We do not have to look at such big values. And in this particular case, we have values till like 4-digit values, but you can also have values ranging anywhere between 5 to 8 to 10 digits. Now, at that point, it is quite difficult to understand these things, but standard normal distribution helps us in that. So more about the normal curve. So the more congested the data is in the middle of the distribution, more data falls within the interval. The lesser the data falls within the interval, the more dispersed the data is. So considering the interval is, say 1 standard deviation or 2 standard deviations, we see that the more the amount of data that falls within, the more peak the graph is. So this is because because basically a histogram goes on to show the frequency of the data, and if the data lies within this particular range and has a high frequency, the graph will look something like this. Considering the other graph, which is a bit more plateaued down, you have a huge range that comes into play, and almost each of them have an equal amount of distribution. When I say almost, it basically means that a point over here doesn't have a huge difference from the point near the mean. They obviously have a difference, because when you have points near the mean, they basically have a higher frequency, but it won't be very different. But going back to the high peaked graph, a point on the, say, on the third standard deviation will have a huge difference than the one on the first standard. So I'm talking about the units, if you remember. So you have the mean as 0 and the standard deviation as 1, as always. But if you want to see the data, you will have the data represented in a different way, because the data will follow a different trend altogether. So that's how we understand the graphs. So that was more or less what you needed to understand, the basic understanding of probability distributions. So in this video, we are going to look into hypothesis testing. So what is hypothesis testing? Hypothesis testing is an act in statistics whereby an analyst tests an assumption regarding a population parameter. We're going to look into what is population, what is parameter, what is sample, and what is statistic in the upcoming slides. But for now, just take my word for it that an analyst takes an assumption that is there and tries to hypothesize over it, that if it's right, if it's wrong, what are the various alternatives. So a hypothesis test evaluates two mutually exclusive statements about a population to determine which statement is best supported by the sample data. Now, the terminologies that I spoke about earlier, we're going to look into it in this slide. So the parameter is a terminology that we basically use to summarize or describe the characteristics of the target population. As I mentioned here, the diagram represented pretty well that this is the entire population. And when I talk about the mean of the population, I basically mean the parameter, because the mean is a characteristic of the population. So basically what you're talking about is the parameter. Now, taking a random sample or a random selection of points from this population, we get a sample. Now, the sample, the sample mean will basically be the statistic. These are the same terms, but mean different in different status. So when I talk about populations, basically I'm talking about parameters. When I'm talking about samples, basically I'm talking about the statistic. Okay, so how do you remember it? Parameter starts with a P and population also starts with a P. So that goes there. Statistic starts with an S and sample also starts with an S. So you remember it that. Okay. Now, mean is just not the characteristic. We have variance, standard deviation, and proportions as well. We have the same for the samples as well. So they are depicted in different ways. So the mean is depicted by the mu symbol, but it is depicted by the X bar over here. And you have the variance as sigma square. You have the variance as S square here. It is small s. And the standard deviation is by sigma. You have small s as the standard deviation here. And the sample proportion is a small p. So I hope you understand the difference between parameter and statistic. So what is basically sampling distribution? So it is a probability distribution of a statistic obtained through the number of samples drawn from a specific population. So if this is the population and I take random samples from here and plot an histogram based on it, it is basically a sampling distribution of it is basically a sampling distribution of the population. So what is a standard error? It is very similar to the standard deviation. Both are measures of spread. The higher the number of the higher the number, the more spread out the data is. The standard error uses statistic, that is the sample data, and the standard deviation uses parameters, that is the population. Now, the standard error tells us how far our sample statistic, like for example mean, uh, deviates from the actual population. So the larger our sample size, the smaller the SE or standard error. In other words, the larger our sample size, the closer our sample mean is to the actual population. Now, we have two hypotheses. Generally, we have a set of hypotheses, but in this case, we're just going to take into consideration the null hypothesis and the alternative hypothesis. Now, you can have multiple alternative hypotheses, but we'll just consider one for the time being. So what is the null hypothesis? So a statement in which no difference or effect is expected. If the null hypothesis is not rejected, no change will be made. The word null is in this context, it basically means the commonly accepted fact. It doesn't mean that the statement itself is null. So if I go on to say that the earth revolves around the sun and it takes approximately 265 days, it is a generally accepted fact and it's going to be a null hypothesis. Now, a second person comes up and says that no, it takes exactly 364.25 days, and you are going to do some computation and going to see, okay, that is correct, and you basically reject the null hypothesis. Now, the particular claim that the other person made is different from what we had initially made. Now, that's what is an alternative hypothesis. So, a statement in which some difference or effect is expected. Accepting the alternative hypothesis will lead to change in opinion or actions. It is the opposite of null hypothesis. Just with the example, we just understood that, when we go on to accept the alternative hypothesis, we obviously reject the null hypothesis and we go on to now say that, okay, uh, a year is not 365 days, it is 365.25 days. Okay, so I hope you understood the difference between null hypothesis and alternative hypothesis. So what is a one-tailed test? So it is a statistical hypothesis test in which the critical area of a distribution is on one side. Now we'll look into what is a critical area, critical region, or rejection region, and so on. But let's understand what is one-tailed test first. So it's on one side, but not on the both. So remember that part. So it's either greater than or less than a certain value, but not on both the sides. So if the sample being tested falls into one side critical area, the alternative hypothesis will be accepted instead of the null hypothesis. Now, what is the critical area that we have been talking about? So the critical area, which is also known as the rejection region, is basically the region that corresponds to the rejection of null hypothesis at some chosen probability level. So the area is depicted by blue section here, that is basically shaded out blue, and that's basically the critical region. So we go on to determine, okay, so any probability that lies within that particular region will be rejected. So that's what the critical region means. Now, extending the knowledge that we have about one-tailed test, we extend that knowledge to a two-tailed test. So a two-tailed test is not very, very different from a one-tailed test, but we'll see what is the difference that it has. It's a method in which the critical area of a distribution is on two sides. It's not on a single side, it's on two sides, and tests whether a sample is greater than or less than a certain range of values. Okay. So if the sample being tested falls into either of the critical areas, the alternative hypothesis is accepted instead of the null hypothesis. This is the same as we saw in the one-tail test, that if it falls in the rejection region or the critical area, we go on to reject it. We go on to reject the null hypothesis. That's what I meant. So by sorry, by convention, two-tailed tests are used to determine significance at 5% level. So that is the general accepted norm. Uh, Now, when I say 5% level in a one-tail test, basically the 5% is on one side. But when I say a 5% level of significance in a two-tail test, it's going to be divided into both sides. So now each side will have a 2.5% rejection region. Okay, so these are the two differences that we have from a one-tail test to a two-tail test. So test statistics, it measures how close the sample has come to the null hypothesis. Its observed values changes randomly from one random sample to different random samples. So a test statistic contains information about the data that is relevant for describing whether we reject the null hypothesis or we accept the null hypothesis. So we basically talk in terms of accepting it or rejecting it. We do not say, okay, we accept the null hypothesis. Okay, the null hypothesis fails to prove itself, so we won't accept the alternative hypothesis. No, basically what we mean is the same, but when we go on to make our statements, we basically talk in terms of the null hypothesis. Now, different hypothesis tests use different tests. So the test statistics based on the probability model assumed in the null hypothesis. Common tests are these that we have here. So the hypothesis test is Z test, and we use Z statistic for it. T uses a T statistic, and OY uses an F statistic, and a chi-square test uses a chi-square statistic. So these are the basic hypothesis test and the test statistics for their respective hypothesis tests. So let's look into the type of errors now. So there are two types of errors that can relate to incorrect conclusions about the null hypothesis. We are going to extend the very same study ahead in classification tasks when we go on to see machine learning aspect. But for now, let's just concentrate on this. So the type 1 error is occurred when the sample results or leads to reject the null hypothesis when in fact it was true. So that's when we call that that particular data is in the type 1 error, basically a false positive. Now a type 2 error is when we accept the null hypothesis when it was in fact false. So that is a false negative outcome. So these are the two errors that we have here. I think you can have a look at here. So basically, if it's true and true, it's correct. If it's false and false, that is correct. But when we have a false negative, basically we have a type 2 error. And when we have a false positive, we have a type 1 error. Now, looking into the level of significance, it is the probability of making a type 1 error, and it is denoted by alpha. Alpha is the maximum probability that we have a type 1 error for 95% of confidence interval when the level of significance is 5%. Okay, so that's what I've listed on that's what I've written here, that the confidence interval is 95 is at 95% level, and the alpha value is 0.05. So this means that the 5% probability that we reject a true null hypothesis. Now, what is the p-value? The p-value is used to hypothesize testing to help us support or reject the null hypothesis. The p-value is evidence against null hypothesis. The smaller the p-value, the stronger the evidence that we should reject the null hypothesis. The p-value is basically, p refers to the probability value. So the smaller the probability value, the higher chances are that we go on to reject the null hypothesis. Now, what are the steps involved in hypothesis testing? So we state the null and the alternate hypothesis first. So we keep those things on the table. We know that what is the null hypothesis and we know what is the alternative hypothesis before going ahead. Now we choose a level of significance to go ahead. To set the criteria for a decision, we state the level of significance for a test. It could be 5%, 1%, or 0.5. Based on the level of significance, we make a decision. to accept the null or alternative hypothesis. Now, generally, it is at 5%, but we can go ahead and make our changes accordingly. So we calculate a test statistic. We want to say, okay, what test statistic do we actually need for this particular problem? Now, construct acceptance and rejection region. So we're going to say, okay, this is our acceptance region and this is our rejection region. Based on steps 3 and 4, we draw the conclusions about H0, that is null hypothesis. So compare the p-value with predefined significance level, and if it is less than significance level, we reject the null hypothesis or else we accept it. Or, or the better way of putting it is, if the p-value is low, we go on to reject the null hypothesis, and if the p-value is higher, we fail to reject the null hypothesis. Those are the two statements that you make. So you talk in terms of rejecting the null hypothesis. Were you able to reject it, or did you fail to reject it? Okay. So that was a brief understanding about what hypothesis testing is and how do you go about it. Now, I did not dive deep into the details because that would just make it more confusing. So having a basic idea helps you understand the concepts briefly, but I do recommend you guys to go ahead and explore more if this interests you. But an understanding of this level gets you through most of the times. But it's really good to go ahead and explore. Yeah, so that was more or less it about hypothesis testing.
So in this lecture, we are going to look into the Python aspect of the particular course. And before starting off into the programming world, let's just know how to go about to start it. So basically what I mean by that is we need to have a particular platform that we write the codes on, right? So what are these platforms called? So these platforms are called IDE for short, but basically what they mean is integrated development environments. So basically the ones that are listed here are Colab, Jupyter, Kaggle, and I know you're wondering why didn't I read out Anaconda, but I'm going to explain that why. So some of them are online, like Colab and Kaggle are online versions, and Jupyter is the offline version of uh, Python notebooks. Now, how is Python and Python notebooks different? So a Python code will have a .py extension, but a Python notebook will have a IPYNB extension. So the py is Python, that's pretty obvious. NB stands for notebook, but the I is the important factor. I doesn't stand for important, but is the important factor here. It's called the interactive Python notebook. That's what IPYNB stands for. So Jupyter came up with this thing where you write a particular code and the outcome comes right beneath it. Now, once we are done installing Anaconda, that we are going to do right after this, I'm going to show you the same code run on a normal IDE like Spider that comes along with Anaconda, and then I'm going to run the very same code on Jupyter, and I'll show you how the outcome comes like. Now, once you install Anaconda, uh, you basically get a lot of IDEs that you can work along with. Basically, you get Jupyter, Spider, PyCharm. If I'm not wrong, you get RStudios as well, and a few other softwares. Now, on the uh, now, why am I specifying on Anaconda is because when you download Anaconda, you get Jupyter Notebook and the other IDEs, obviously, but you also are installed with the prerequisites or the prerequisite packages that you need for data science. So taking a few examples randomly would be NumPy, uh, then you will have matplotlib, scikit-learn. And these are the various packages that are generally used for any of the data related problems. So these come pre-installed with Anaconda with the IDE. So it's quite helpful. Now, Anaconda is a bit hardware heavy. So if someone has a low specification laptop, not to worry, you have Colab, Kaggle, and Jupyter as well. So if you are installing just Jupyter, you can do it, obviously, no issues there. But you need to install the packages separately. Now that's not a problem, just a bit of extra effort. So if you can do that, not an issue. Or you can always use Colab and Kaggle. So let's just go ahead and install Anaconda and then have a look at the programs. So how to install Anaconda? So either you can just go to Google and search Anaconda Navigator on it, and the first link should take you to the particular website that we're going to look into, or you can just click over here and that should take you to the link that we are going to look into. Or you can just check out the notes section of the PPT for this particular slide, and you'll find the link there as well. Anyway, any which way you're comfortable with, just be on the particular link, and that should help you out with going ahead. So once you click on the link, this window should pop up. So what is Anaconda Navigator? You get to read a bit about it here. And there are some notes that you can refer for why Navigator is better. You can look into each of the hyperlinks mentioned here to understand what each of the application mentioned here in the picture, which by the way just shows you which are the applications that you get in Navigator. So I told you that you get Jupyter Notebooks and Spider. I told you that you get RStudios as well. Along with that, you have PyCharm, which you can use for Python programming. These are other softwares that you feel free to explore. These are pretty good softwares as well. And that would be it for this particular document. Let's just go into the one that we are interested in. So you go on to press install Anaconda hyperlink here. So it should load up this particular web page here. And you can see that it lists down the system requirements for each of the OS that you can possibly use. These are the main three OSs that are mentioned or are compatible. So we have Windows, we have Mac OS and Linux, the ones that we are interested in. And I am going to install Windows as I have a Windows laptop. If you have a Mac OS, you go for this particular hyperlink. If you have Linux, you go for this particular hyperlink. So let's click on Windows. Even though you don't follow this particular video for downloading, you get an extensively detailed report of how to go about uh, installing the particular software. You get screenshots of it as well. But let's just go ahead and download Anaconda installer. So once you click on this particular link based on your internet speed, uh, it takes you to this particular page and you click over here. For Mac OS, it'll have a Mac sign here, and for Linux, it'll have a Linux sign here. So once you download this, something like this pops up. You can just close this and wait for some time. It should, it's still loading based on your particular internet speed again. It should load up here. I'm going to save it in my downloads section, or yeah, I'll just save it in my downloads section. I press save and it should get downloaded. So I won't wait till it gets downloaded, obviously, because you can see the speed is quite low. But it should get downloaded in, say, 15 minutes based on the internet speed. So let's see what happens once this is downloaded. So once you click on the particular application that gets downloaded, uh, this should pop up. You press next. These are the terms and conditions that you can read, but I would not waste that much time. And I'll press I agree. Obviously, it's just for me. So you do that. I would select the general location that's there and do next. I'll do it to my default Python 3.8 and press install. It should install pretty fast. You can have a look at the details here while it gets installed. So once the Anaconda software gets installed, completed, it should show you something like this. You press next. Some additional settings that they have brought in, they are just mentioning that. And you can either have this individual version ticked in. This is something that you can get untick and check as well. So if you want to, you can. I don't want to look at the tutorials. I'm not going to check that. And I do not want to get started just after I press finish. So once you're done with this, you just press. So this is how the Anaconda Navigator looks like. And as I mentioned before, these are the main two applications that we are going to use out of these are the Jupyter Notebook and the Spider IDE. So if you're wondering how to come up with this particular section or how to open up this particular application, you just search for Anaconda Navigator on the search bar just beside your Windows icon, and you should find it there. So basically, we are going to see the very same code run on Spider, and how does it look and how is the look and feel of the IDE? What are the various shortcuts? I'm going to talk about them. And we're going to look at the very same code run on Jupyter Notebook and what are the advantages that I find uh, is uh, is more useful or is has a upper hand over Spider or different IDEs. So once you open up Spider, this is how the basic IDE should look like. And let's just understand the icons on top over here. So you have file. This particular icon stands for file, and you have a folder over here, and you have the save button over here, and this is the run button. So these are the basic buttons that you should know initially. And this is what you call the interpreter. So Python has an interpreter, and whatever you write actually goes inside this particular here, and the output comes here. Let's just look at it let's look at the working example. So I have a print statement. This is how you write a print statement, and I say this is a line, and I either press F5 or I can press this particular button over here. I'll press F5, and I see that uh, it comes up like this is a line. So this is what the output should look like. Now, if you see that there's a star mark here, which basically indicates that your particular file is not saved. So you need to save it first, and you can either press this particular button or you can just press Ctrl S. I'm going to save it on my desktop by the name test, and that should do it. Yeah, I just replaced the older test.py with the new one. So that's what it shows. Now you don't see that the star mark here, which basically indicates that your file is saved now and it's safe for you to close the particular program. Anyways, if you don't save and you close it, the particular IDE should ask you, do you want to save it before closing it? So let's look at the input statement. So you say input, just say name is equal to input, and then say enter your name. And I'm just going to so this message actually pops up on the command line here, and it's basically more of like a message for the client or the user who is using this particular program to help him or her understand what is the input that the program is looking for. So I'm just gonna print the particular value that is stored in name. Sorry, I'm gonna print it here like this. And let's just give a small formatted print by saying this is what you entered. Okay. And let's see what it does over here. So I'm just going to press F5. It runs the file and it's asking for my name, obviously, and I did enter my name here, and so this is what you enter, and it comes out Rishabh. So it's a basic input and output statement. So I hope you understood the basics of the IDE and how it performs and how it goes about. So let's look at the very same example on Jupyter, and I'll tell you a few tips and tricks that might help you create a report ahead when we work on ML programs. So once you open up Jupyter Notebooks from the Anaconda Navigator, you can directly search for Jupyter Notebooks in the search bar, and it should ask for your default. If you have a default browser set up, it should open up like this on your default browser, or it will ask you which application do you want to open up with. Any which ways, you should land up to this particular page which says Jupyter, and it gives you the root directory. So when I say root, it basically means your C drive, and my C drive has all of these things. So it shows up that. So I want to create a particular file in my desktop. So I go to desktops and I press new, and I want to create a Python file. You can even create a text file or a folder if you want to. So I'm just going to create a Python file, and it should open up in a new tab. So I'm going to just click on that and it should open up on a new tab. So once you're on the new tab, you will see untitled as before we saw that even in the Spider ID, the default name that is given to your file is untitled. So if you want to click it to something else, I will just say it's test2. I'm going to rename it. You can see that it's renamed here. And remember that it's in the desktop. So you can definitely go to the desktop and see what did the name got changed to. So there are a few things that you need to know about Jupyter Notebooks. As I mentioned before, that it's an interactive Python console. So IDE, sorry. So how do you go about it? I said that we're going to look into the same example. So I'll just say print, and this is a line, and I'm going to press either you can press Control Enter or you can press Run. So it shows this is a line. Now you see that there's a next command line that comes in here. We can enter your code, and it's not on a different on a different window where you need to go on checking. So that is easier. Every output just comes underneath your particular code. So it's easier and more formatted and helps you create a report. So let's just look at the name aspect of it again. So I do input and enter your name. So I just press enter, not control enter, to go to the next line, and I do print name, and I do control enter this time to get this particular box-like structure where you enter your name. So I say press Rishabh, and it should print Rishabh as we said. Now the other thing that is quite nice about this particular Jupyter Notebook is that even if I don't write print, I just write name, what happens? I just press enter. It should give me an error, right? Because it doesn't have the print state, but it doesn't. It gives you an output called Rishabh. It actually prints in the value. So it still does that. But if I just do, say if I have another variable, say I have a different name, which I'm writing as, say, Zach, and I go on to say print diff name, and I press enter. So even if I do Rishabh now, it's not going to show Rishabh and it's going to show Zach because the print statement overrides the previous output. So just keep this in mind. It kind of bugs you there. So if you have a single output, you can just use the without print line as well. But I would prefer, I do recommend you to use print statements. It keeps you in the habit. So that's one of the advantages, and I'll just talk about a few other advantages that are pretty nice. So there's this plus icon and there's a save button again. So I want to remove this particular line from here. I just press the cut button and it gets removed. And if I have to add another line, I add in a line here and I do a different print here. Print, say, okay, so this I'll write as the first line and is the second line. Okay. So basically my output is going to look something like this, but I want my first line to be on top, right? I don't want to copy this, paste it again and write it. So what I do is I just use these arrows. So currently I'm on this particular cell and I click this arrow and you see that the particular cell goes up and the other cell comes down. Logical. But now I do not want the second print statement. What do? I use the scissor icon here and cut it out. So that helps when you have a lot of and I do not want these extra ones. So I just do this and it gets deleted. So these are the few things that come in handy. Apart from this, there is this other thing that you see over here. There's a drop down saying there's code, markdown, raw notebook convert, and then heading. So what it does is I'll just do okay. The other shortcuts that I quickly use is if you click on the left side of it, or if you're inside, it basically is green. And if you are not writing and you're just on the cell like this, it is blue. Just remember these. So if you're writing this and then you press A, it doesn't do anything. But say you want to be in the blue region now, or you just want to select the particular cell, but do not write anything in it, you either click on this side of the cell, or you can just press escape. By doing this, the line turns blue, which means that you've selected the cell, but you're not writing anything in it. And then when you press A, there is a line that is inserted above. So I'll just write, sorry, this is a line, and I'm not going to, I'm not going to run this because this is not a right code. So, and when I press A, like I press escape, or clicked here, or I press escape, and then I press A, it basically creates a line on top. Now, this is something that I want to write notes, or I'm writing this print statement. So what does it mean? This is a line. So I'm just going to do what I am going to do is I'm just going to make it into a markdown. And when I press Control Enter now, it basically is a line, or it helps you document your particular code easier. You can even document it in the way like using comments, or if people are using Spider for your particular working here, you can just use comment statements. They work the same way. They don't get when you press Control Enter or when you run it, it doesn't get printed. So this is ignored. And the other thing that I would like to mention is the header thing. So this is for first code and I do heading, it's going to ask me, it's going to tell me that if you want it in lower heading cases, you can just add in the number of hashtags and it does the job. But for this time, I'm just going to do this. So this is the maximum size that you can have. Say I want it in a bit of a lower size. I can just add another hash and you go on adding it. I think it goes up to the seventh stage. Yeah, 6 or 7, and then it stops. Then when you press this, it doesn't work. So for the now, I want it to be at the highest order, and I just press this and move this particular line. And this is how your code should look like. So you have a particular print statement. You have it documented either this way, or you can document it this way. And you have the output here, your particular heading stating what it is. And that's how Jupyter Notebook helps you document your particular code, and it is easier for you to understand. So that was all about the introductory part for Jupyter Notebooks and IDEs in general. From the next video, we're going to look into the basics of Python. So today we're going to look into the basics of Python. So today we're going to look into the basics of Python, starting with data types. And so there are four main types of data types in Python, and they are namely integers, floats and strings, and booleans, obviously. So we're going to look into each of them and try to understand what happens when and why do we require them. So here we can see that we are taking an input and we're using int in front of it. As specified, int stands for integer, and we're just going to run this and understand what happens. So I'm going to run it. We saw that the user input box comes in. I'm just going to put an arbitrary number, say 123, and press enter. Now what happens here is it says that it belongs to the class, and I'm saying that there's a type function. So this is a type function and it tells you which class does this particular variable belong to. So it says that it belongs to the int class, and this is the value for the number. So I just printed the number out here. Let's see what happens if we put in a decimal number. So it says 123.23, and I hope you understand what is the difference between decimal and integers. So decimal numbers have some value after the decimal. Integers do not have. Integers can be positive and or negative, but they have to be like a complete number. They cannot be any fractions. So when I press enter, it says that there's an issue. So 12.123.23 is not of the type base 10. So this is an error that pops in because the default data type for the input function is string. So how to resolve this error? I just do float and then do the typecast. So I think this should solve it. Yes, it did. So basically what I'm doing here is I'm taking an input 123.23 and saying and sending it to the float function. So the string over here gets converted to float, and after that the float value converts to int. It's a bit confusing at the moment, but let's just look at the float function and I think you'll understand what it means. So I press Control Enter and I press 123, an integer number, right? So it should return me 123 and class of int. So when I press enter, it says that it belongs to class float, and the value over here is not 123, it's 123.0. And why is that? Firstly, because I typecasted it to float. Now we'll understand typecasting in a bit, but understand that there's a function called float, and I'm sending it a value that the user is entering. In this case, it's 123, and it's converting it into a float, irrespective of which base it is in. So it might be 123 or 123.25. It will always return a float value. When I say float, I basically mean decimal values. So it says that it belongs to class float because it's obviously I'm passing it to the float function, so it does give me the value. So now let's just understand what the string functions are and why am I not doing str over here. So basically, as we saw earlier, that for an integer value for a class int, I need to have an int in front of the input, correct? So let's just put str and see what happens. So I'm doing str name. I need to enter my name here. So enter a name. So I'll just enter mine and I press enter and it belongs to str. No errors, but what if I do this? Should throw me an error, right? But it doesn't, because the default enter type, as explained earlier, is string for the input function. So I've mentioned a few points here. So typecasting. So basically what I did right now, I did not typecast it again. It just takes on the computational time. At this particular instant, taking this particular example, you could not see the difference because it's just a input of a word. Okay. And even the slowest laptop should compute it within milliseconds, if not nano or microseconds. So if you go on to say if you're taking a complete page as an input from a book or the complete book for that matter, and then you're taking that as input and then typecasting it, it is quite a heavy task. And it is unnecessary because it is already in the string format. So why do it again? So that's the basic logic behind it.
now let's understand what is Boolean. So Boolean values will always return true or false. So when I do Boolean 12, let's just see what it does for you. Okay, so the shortcut for commenting is control and the backslash. If you are confused between what a backslash and a front slash look like, this is what a backslash looks like, and this is what a a front slash looks like. Whichever side the slash is bending towards. So I'll just write for commenting, you need to do control plus backslash, and that should comment it. I'll just comment this out as well. So I just commented down and I just want to see what is the value for the test one. So I press enter and the test one value says true. So why did it do that? I haven't done any kind of computation. I'm just passing it a value of 12. Let's see what if I do what is the output if I do 1. It still gives me the value of 1. What if I do 0? It gives me false. Now that's interesting. Let's look at test 2 and 3 for that matter and then understand what is happening here. So I run this and I see that the test 2 result is false. So 12 is less than 1. So okay, 12 is not less than 1. I'm so sorry. 12 is not less than 1. So it returns the value as false. That's pretty understandable. So okay, now let's see what is the value if I do number is equal to 12 and the number is okay, greater than 1. What if I do this? It returns 2. Okay, so it's basically checking if the value inside is true or false. But what happens here? Why is it returning 1 as true and 0 as false? So in computers, we refer to 1 as true and 0 as false. So if you go on to see, it's pretty logical, right? So there's a combination of ones and zeros. It is either correct or it is not correct. So computer just understands binary and that's how it is. So we're going to look into that. I think that's pretty obvious, right? So ones and zeros, true and false. So that's how the value for test 1 is false. So after the data types comes the arithmetic operations. So basically there are 7 arithmetic operations that Python does by base, and addition, subtraction, multiplication, division, modulus, exponential, and float addition. So addition, subtraction, multiplication, division, these are the 4 basic things that I guess everybody knows, but we're going to still look at it. So you see that there are 2 numbers here, number 1 and number 2. So number 1 has 23, number 2 has 34, and I'm saying number 3 is equal to number 1 plus number 2. And the final output for number 3 will be 23 plus 34, and that is 57. Pretty obvious. So what are we doing here? So basically we are trying to optimize the value here. Okay, so here we are taking the input in 2 different lines. Here I'm making it into 1. So basically what this particular line means is 23 goes to number 1 and 34 goes to number 2. So if I have another variable, say num3, I basically need to have another value this side, and that does the job. Okay, so that's basically one aspect of it. And I'm just printing the values out for you here so that it's easier for you guys to have a look at it. So basically number 1 is 23 and number 2 is 34 as we had written here. And we did that in 1 line. We have 1 line less now. So getting that out of the picture, let's see what the output looks like. The output should be same, right? Because it's the same thing.
But now if you go on to see, you basically just have 2 lines of code. Comparing to this, we have 4 lines of code. That's what optimization means. So you basically make your code as simple as possible and as, you know, taking less time and less space are the two main aspects of optimizing your particular code. So the lower the number of lines, the better and faster your code is. Or you can look at it this way, that instead of taking 1,000 lines, you did the job in 10 lines. So basically you shrunk the particular code to just 10 lines and it does the same job. So that's what optimization means. So we're going to look at the optimized results from now on, considering that you all got it. Now looking at subtraction, again is the same thing. We have two values, number 1 and number 2, and the final output should be number 1 minus number 2, and that is minus 11. Pretty obvious, right? So it's 23 and 34 is greater, so the value should be negative. Now the same goes for multiplication, 23 into 34, 782. So we got that. Now we have two different sets of outputs. So you're going to look at the first one first. So it's the basic one. Number 1 divided by number 2 is this huge number, but it is not humanly possible to remember all these digits. So there is a formatting function in Python that, okay, just we're going to look at both of them. And it basically helps us to reduce the number of decimal points. So that is easier for us to remember. So what this particular thing means is the placeholder. The brackets basically means the placeholder. And here we have a colon symbol. Colon means everything before the decimal. And 2F means two floating point numbers after the decimal. So basically, we should get a value of 0.68 because it rounds off the entire thing behind it. Let's see what it does. And it does that. We got 6.8. So the 6.4 and everything is rounded off to 6.8 and we get a 0.68. So now it's easier for you to remember. Okay, so basically I got a 782 by multiplying it and a value of 0.68 after dividing it. So this is quite helpful for giving formatted outputs where the user wants formatted outputs. So basically, even when bank transactions are supposed to be worked on, we're going to work on questions like that. So I would rather want my balance to look something like this rather than look something like this. Well, I would like to have a bank balance of this huge before the decimal, not after it. But yeah, I think you get the point. So coming to modulus, now this is something new that you guys might not have seen. So we have two numbers, 23 and 10. And I've made the print statements again, giving the placeholders here using the format function, with this being the first placeholder value and this being the second placeholder value. Let's run it and see what do we get. So after dividing 23 by 10, we get 2.3. That's pretty obvious again. So 23 divided by 10 is 2.3. The decimal point value comes here. And after modulus, we get a value of 3. So that's pretty interesting. How does modulus calculate that particular value? So 23 is nothing but 23.0, right? So 23.0 divided by 10 gives us a value of 2.3 as expected. So when I do modulus of 23.0, it basically is just considering the value after the decimal, or for in this particular case, the remainder, or for any particular case for that matter. But just because I'm doing it divided by 10, so my 23 becomes 2.3 after division, and it just considers this particular point. So let's see, 8 modulus 2 should be 0 because 8 is completely divisible by 2. So that is the case. But when I do 9 mod 2, it gives me a value of 1 because there is 1 as the remainder, correct? But it gives me a value of 4.5 here. So 4.5 because it does the calculations and gives you the value. So it's not the value after the decimal. It was just because, it was 9 divided by 10, that is 0.9. So if I do modulus of 9 divided by, I should get the value 9. So you see, because it was by divided by base of 10, you got that value. But modulus gives you the remainder after division. So the remainder after division was 3. Okay, so 10 into 2 is 20, and there was a remainder value of 3. So after modulus, the value that we get is 3. So let's look at the exponential operator now. So again, optimizing it, putting in the placeholder, formatting the values, and I'm giving 2 multiplication signs. Let's see what it does. Okay, so obviously not very clear. Let's just change the values and see. Okay, I do 4, 2. Okay, so it's giving me the power. What it basically means is 4 raised to the power 2. Okay, so what it's doing is 4 into 4, and it's giving me a value of 16. Okay, so it basically gives you the power. That's what it does. Now, what does floor division mean in general? Let's look at what it does after doing a general division and what it does after doing a floor division. Okay, so the value after division was 2.3 as observed earlier as well. But the floor division value just gives me the value of 2. Now, in this particular case, any value after the decimal is not considered. So a floor division value will always give you an integer outcome. Let's just look at a very, very big number and then divide it by, say, 200. Okay. So now that gives me a value of this huge number, 0.005. What if I do a floor division? It just considers the value before it, as expected. So after that comes comparison operators. So we saw that we are giving value, assigning values using a single equal to. So here we have equal to. You pronounce it that way. This is not called equal to. This is just basically called checking equal to value. Basically, it checks, it doesn't assign it. We're going to look at it one by one. So the double equal to check that we just did is false. And why is that? Because number 1 is not equal to number 2, correct? So they are not same. That's what double equal to checks. So let's just look at the other, let's just look at this one. So this one is less than check. So is 23 less than 10? No, it is not. So it's going to give me a value false. Let's look at this one. Is it greater? Yes, it's greater. So it gives me a value of true. Let's look at the other one. So this one checks, is it less than or equal to? Okay. So this will give me a false. And even if I change the value to 10 here, oh no, I change the value to 10. So now it's equal. Okay, so basically it checks first that is it less? Okay, it's not less. So is it equal? Yes, it's equal. So that's why it gives me the value of true here. Now let's check this one out. It gives me true because it's equal, not because it's greater. Sorry, I should have changed this to 2 and showed you. It gives me a value of false. So 10 is not greater than equal to 12. So it gives me a value of false. So that's how they work. Let's look at the assignment operators now. So we already have looked at equal to. We're just going to look at it again. The same thing. Now division equal to. Now the best part about assignment operators are, if you know how one works, you will know how all of them work. Because you know the operators, you know what is floor division, you know what is modulus, you know what is subtraction, multiplication, addition, you know, exponential, everything. So here we have an example. Let's look at that. So I'm assigning n equal to 2, and I want the sum equal to n plus 2. Now n plus 2 is 4, that we know, understood. But can I optimize it again? Okay. So here we have sum plus is equal to 2. Now they mean the same. Okay, let's just look at it. How do they mean the same? Let's just look at the plus operator here. So we have n is equal to 201, and instead of, so initially if I did not know, I would have written it something like this, right? 200, and I comment this and I print this. So it gives me a 4 and gives me a value of 401. Uncommenting this, commenting this, and now the basically CPU looks at this line and this line. It doesn't look at this line, so it doesn't matter. I'm just going to remove it for better understanding, making it how it was originally. And let's see what the value is. So I run it again and it still gives me the same value. So basically I've now reduced the entire statement into a smaller statement. So it does the same for the division one. So 2, now what this means is, do a arithmetic operation of 2 divided by 9 and overwrite the initial value of n. And that's what it does. Same it does for the floor division and the modulus. So 201 divided by 10 gives me a remainder of 1. So it gives me the value as 1 here. Now look at subtraction is equal to, it does the same thing. 201 minus 200 should give me a value of 1. That it does. We already saw addition. Let's look at multiplication here. And it does the same. 201 into 10 gives me a value of 210. Now that's what all the assignment operators are. They are the same thing. You only need to know what the operators do that we looked at here, the arithmetic operations. If you know these, you know all of these. These are just the optimized versions of looking at it. Let's see what do we have next. So we have the identity operators. So they are nothing, they're more or less similar to what we observe, but let's see what they do. So we have two numbers again here, that is 12 and 21. And we are doing a print statement which says number 1 is number 2. So looking at it the English grammatical way, what I'm trying to say is number 1 and number 2 the same thing? Number 1 is number 2. So for this case, it's no. So it's returning me a value of false. Now, for the same thing, what does not do here? So number 1 is not number 2. Let's look at it in the grammatical way again. So 12 is not number 2. It sounds correct, right? So it should return me a value of true, which does the job. Now I'm making an intentional error here. So let's look at the intentional error. So when I do this, the thing that it does over here is called a warning. Okay, it is a syntactical warning as mentioned here. And I'm going to explain that in a bit, that why does this happen and all. But if you see, I still get the output. So the difference between an error and a warning is that maybe logically what you're trying to say here is correct, but Python syntax kind of understands it maybe a bit differently. So it throws you a warning here. So mainly it throws you a warning here because you're assigning values instead of references. So variables are basically references for the values. So when I say number 1, basically what I mean is number 12. Correct? It is kind of like your roll numbers in your class. So your roll numbers are basically references of your name, or they are references for you. Correct? So when I say roll number 1, I basically mean
the person who is roll number one and not the number one, correct? So that's what it does here. So it doesn't consider the values. So if I do the very same thing here, we already saw that, but let's just see what it does here. So I just change the values and make it the same as the one I mentioned earlier on top, and it shouldn't give me an error anymore, or sorry, a warning anymore. So it is logically correct, but maybe syntactically wrong. So I'm going to keep the error here so that you can understand, and do not make the errors here. Again, so warnings. These are warnings, but yeah, kind of considered as errors because doing a general Python application development, you wouldn't want your clients to see something like this. So let's do a membership. Let's look at the membership operators. So that is in and not in. So here I have a list of values. So this is another data structure called list. We are going to look at it in the upcoming videos, but for now, just consider that these are a sequence of numbers that are there, and what I'm trying to ask over here is 12 present in this sequence. So do not get confused. It checks 12 and not 1 and 2. So it should return me a value of false, which it does, and not in does the same thing as is not. It basically returns the opposite value of whatever is the actual value. So just to remove the confusion, I'll do is I'll just see that if 2 works for my case only. So what I'm trying to do over here is what I'm trying to say over here is that is 2 present in the sequence. Now I know that it's present in the sequence. Let's see what it does. It basically returns true. So it says that yeah, it is present, and you can go ahead and do whatever operations you were willing to do. So that does the job. Let's look at the logical operators now. Now these are pretty interesting operators. So for the AND operator, basically both the sides need to be true. So what do I mean by both the sides? So basically there are two questions that I'm asking the particular computer that, okay, is 1 equal to 1 and is 2 equal to 2? So it's basically going to say yes, 1 is equal to 1 and yes, 2 is equal to 2. So it should return me a value of true. Now, the next statement is, I'm asking it, is 1 is equal double equal to 0? That what I'm trying to say is 1 and 0 the same thing. And in the second question I'm asking is 2 and 2 the same thing. So 2 and 2 is the same thing. So obviously this is going to return me true, but 1 and 0 is not. So when I run this, it's going to return me a false value. The same thing happens in the third row and it returns me a false value again. Now in the fourth row, it's obviously going to return me a false value because both the values are wrong. But you need to understand this particular case that if both the values are wrong, it doesn't matter, and will check if even one of the values do not match, it doesn't consider the second one, as we saw in the second and the third case. Let's see what OR does. It returns true if either of the operands, right side or left side, is true. So it basically says that, okay, if left side is true and right side is true, I'm going to return a true value. If even one side says that, okay, even one side is correct, I'm going to say, yeah, it's correct. Okay. So even for a single side is going to return me true. But if both the sides are wrong, it's going to return me a false. So it's kind of the opposite of AND. It's not exactly, but kind of. So it returns the same thing for the first two outcomes. So 1 is equal to 1 and 2 is equal to 2. It returns me the 2 for both the cases. But AND is way more restricted. It says that even one of them is wrong, I'm not going to consider it. But OR considers even one of them. So even if one of these conditions are true, I'm going to consider it. But if both are wrong, I won't consider it. Now, not basically converts the ones to zeros or trues to false and vice versa. So let's look at that. So the first print statement is 1 double equal to 1, which should return me true, which it does. Now I'm putting in the same particular condition here and I'm just applying not in front of it, which returns me a value of false. Now it basically just reverts the value whatever is inside. So basically what I'm getting inside is true and not just inverts it and says, okay, it's not true, it's false. So now 1 double equal to 0 is false as presented here. And what the not does it again flips the value and returns true. So that was all that you need to know for the basics of Python. We're going to look into the other details in the upcoming videos. And I hope that you got each and every aspect of the structures. The other thing that I would like to mention is a few of the markdown things that I've used here. So if you go on to double click this particular thing, you're going to just control enter, make it the normal thing that it was. And if you go to this section and double click on it, you're going to see what I did here. So this is called numeric listing. So if I do not put the number here, what it does is something like this. It makes the entire thing go haywire. So you need to do numeric listing and that makes the thing normal. So that is one of the things that I would like to mention. This is non-numeric listing. So it still does the list, but it put these are bullet points instead of numbers. That's the only difference. And you would see that I had given a tab like thing. Yeah. So this is with the help of the greater than sign. It is usually helpful for paragraph shifting. If you want to specify a particular thing within a paragraph or between two paragraphs, you should use these particular things. So if I have something that I need to over specify, I give a double thing and this is a line and it puts the value inside it. So it is kind of over specifying, but you can use it just for knowledge purpose. And I guess that was it. You should know about the warnings. We understood that. Yeah, and that was it. So you know a bit of tricks from uh, the markdown, and you know what the basics of Python are. So that's all for this video. Today we're going to look into the second section or the second part of Python basics, so that we can have a holistic approach and have at least the bare minimum that we need to understand and code for Python. The first thing that we're going to look into is the variable name constraints. So I think I did not mention this in the last video because we were just getting to know the various operators. Here we're going to talk a lot about the variables, so I think it's way more important to talk about it in this video. So there are a few constraints. First is you cannot have the variable name starting with you know a number or a special character. So the only special character that is allowed in a variable name is the underscore, as we have mentioned here. Something like a hashtag or @ wouldn't work. It's wrong. And we cannot start with uh, a you cannot start with you cannot start with a special character or a number for that matter. And VAR and capital VAR are treated as two different variables. So even though we read it in the same way, we called it VAR with a V small and VAR with a V capital. We read it as var only, but they are considered as two different variables in in Python or in other programming languages which are case sensitive like Java. So that was more or less it. I've mentioned it here so that whenever you feel okay, why is this happening, you can always refer to this section. The first thing that we're going to look into is a print statement. I think we already have looked into it more or less, but still. So we see that I'm printing my name over here, and I have a function or a parameter to the print function called end.
And there are two parameters, end and sep. Sep means separated. So by default, the value for end is /n and for sep is a space. So that's why when I change it to /t, I'll just remove this for the time being. When I change it to /t, you don't see a difference. But uncommenting this and reprinting it, you see that it comes in the very same line. Instead of if I remove it and then do it, you see it comes in the next line. So that's how the end thing works. You can even have, two front slash ends so that you have a space in the middle to make it look more proper, nothing else. So that's one of the things. And separator is just a tab instead of a space. So instead of having my name as Rishabh, if I did not do this, if I did not mention this, let's have a look at what the output would look like. So it would look something like this. It's not very formatted. It's kind of difficult to read. So I'll just change to what it was, and you see that it's way more proper. And you can even do this and try out. You see that you have the same sentence and they're separated into different lines. So instead of having two different print statements, you can have it in a single line. So that's what it was. So that was the basic of print statements. I think it's pretty basic, and we have also looked into a few print statements in the earlier video. So I think this is enough for print statements. Then we have the conditional statements. So conditional statements are three types. We have if statements, we have elif, which basically mean else if, and we have the else statement. So the sequence is every conditional statement will have an if statement. It may or may not have an elif or an else statement. So those two are optional, but if you consider to have a conditional statement in your code, there has to be one single if statement. And I'm specifying one because you can have multiple if statement as well. We'll look into when and why do we use it. So you see that we have a variable called temperature, which is 10 at the moment. And I'm saying that, okay, if temperature is less than 0, it's freezing. Is this the North Pole? So it's kind of a funny statement, but it basically means that the temperature is really low and I'm feeling cold. Now, after that, I have a temperature which is less than 50. And it says that, okay, it's hot, but I have an AC, so it's cool. And then finally, the else statement comes into play, and it says that it's so hot, it feels like I am on the sun. So let's see what it does when I am printing this. It says that, okay, so 10 is definitely not less than 0. So this is cancelled out. Sorry. This is cancelled out for sure. And coming to this, okay, so it's definitely less than 50. So that works. Now, what happens is once this is correct, it doesn't go further. It doesn't check the further conditions. And we look into that in a better example because, less than 50 is definitely really hot, even though if you have an AC. Let's just look at just changing it to say 49 says that, okay, it gives you the same output, but changing it to say 51 gives you a really, really vague answer, which is not correct, right? So we need to have more divisions and we need to understand it better. So I think this gives you a better example. So say there is an arbitrary negative value like -100 that's like really, really cold, and you have it till 0. So we consider that particular range to be very cold. Then we have 0 to say around about 20, 21, something like that. We have it's cold. Okay, it's bearable, but it's cold. Then we have somewhere around greater than 20 to say 30, and it's normal, understandable again. And from 30 to 50 is hot, and anything beyond 50 is very hot. Okay, so it's the same thing, but in a way more formatted manner. So we have different print statements, as you can see. I'll just space them out so it's easier for you to view and understand. And you see that, okay, I'll just print it out so it's better. Okay, I'll just have -10. Sorry. and I'll press that. It's freezing as if it's in the North Pole. So okay, that is working. Let's see if it is what does it say that when it is 10? Okay, it's cold, but I'm warm in the quilt. So it's basically is considering this particular else if statement. So you see, if this is wrong and this turns out to be right, it doesn't even consider the other else if and else statements. So that's one of the things that is observant. The best way to check out if each and every if, else if, and else statement is working, you should try it. You should try to change the value within these values that you have put in as a range and try it out. So I'll just put an arbitrary value, say between 20 and 30, that is 25. It works. 35, and it also works. I'll just say 55 now at the end, and yeah, that works as well. So that's just one of the examples to understand how multiple if else if statements work. And you're going to look into the complex versions of it in the upcoming sections, but this is more of like a basic understanding of what it looks like. So let's just have another thing where I demonstrate the same thing but having multiple if statements. So why is that necessary? Okay, so I have, sorry, I'll just copy the statement again and paste it. And now technically, as we saw earlier, if I have minus 10, it basically satisfies this particular condition and it should just print it's freezing, it's in uh, is this the North Pole, and it should stop, right? But that doesn't happen. We have both the if statements being printed. Now, sometimes, not all the time, sometimes you require this kind of a setup where you need to check multiple, uh, sequence of conditions, and you need to check all of them, irrespective of what is true or what is not. So I'll just keep it here for your future references. So the third kind of statements are looping statements. So there are two major categories of looping statements. One being the entry control loops and the second being the exit control loops. So there are various kinds of loops that come under it, as we have mentioned here. So you have for loops and while loops under entry control loops, and there is do while loop under exit control loops. Now, Python doesn't have anything specifically called a do while loop, but we'll see how can we create that. And it's just for your knowledge that Python doesn't have a specific do while loop looping structure, but other programming languages like Java has it, and if I'm not wrong, C and C++ also have it. So I definitely C has it, but I am not very sure of C++. So to understand how these work, let's look at a few examples. So for looping, we need to pass in a starting value, and you have the condition. Basically, it is like less than that particular number, and then we have the iterating value. So it's more of like how many times do you want to iterate or skip. So basically, do you want to go from 1 to 2, 1 to 2 to 3, 4, and 3 to 4, or if I change this particular value to 2, basically what I'm saying is I want to go from 1 to 3 instead of 2. So I hope you get that part. And let us see what happens. Okay, so basically I have a range from 1 to 10, and it's printing from 1 to 9, but it should print 10 as well, right? But it is not, because it's a condition that says that you need to start from 1, and then you have a condition that is less than 10, and then you have a condition of plus 1. So that's what is happening. So when I do it, if you want the 10 as well, you just need to make it 11, and that should include the 10. And if you want all the odd numbers starting from 1, you just do this and you get the value. And the best way to have all the even numbers is start from 2 and do the same thing. So that gives you all the odds and even values. So it's better if you try it out while you're looking at it. That will help you out understand how these things are working. You need to try them out yourself. So now coming to the while loops, print the number till the number is less than 10. Now, for loops are generally used when you know the particular range that you are looking into. So I knew that I need to look into the range 1 to 10, or for this case 1 to 11, or less than 11, that makes it 1 to 10. So I know the range is defined, but in this particular case we use while loops when we are not sure of the number of times the loop is going to run. So for that, we basically use while loop. So if you get this particular question in a in your exams, or say in an interview, if you're preparing for one. So the basic difference between a for and a while loop is they are both looping structures, obviously, and they both are entry control loops. The major difference is we use a for loop when we have a specified range, and we use a while loop when we do not know the number of iterations it's going to go on for. So that's one of the things. So here we define the I stand basically is the general variable for iteration. So I is equal to 1 and I is less than 10. And I'm printing. So this is the condition that I'm passing to the while loop, and I'm saying that any value. So the loop is going to run till the value is less than 1. Less than 10. I'm going to start from 1. 1 is less than 10. So it goes inside the loop, prints the value, and adds the space at the end, and doesn't goes to the next line. It just adds the space. And I say I plus is equal to 1. Remember what we did earlier, what it does. It basically means that what I'm trying to say is I is equal to I plus 1. Just a small refresher. Let's see what it prints. Okay, so it prints the same thing. Now, if I want to have 10 as well, I do the same thing here. I make it either this, or the other solution is equal to 10. That should do the same thing. So we understood the basics of for loop and while loop, and I hope you understood why do we use it and when do we use it, because it's quite important. And in general coding terms also, it's quite important to look them in that way. So after that, we have the do while loop. And if you see, the structure is more or less similar to what we have in the while loop. The major difference that you see is the if condition and the break statement here. Now, the break statement acts as a general brake in a car. When you press the brake, the car stops. And if you do not, the car is still going to run. So basically, if you consider the while loop to be a car, and if I pass it through, so the car is going to run till I press the brake pedal. In this case, if I do not pass in the brake parameter, it's going to run over and over again. So when I run this, I basically get 1 to 11, which is strange because you see that the value over here says that if I is greater than 10, you need to break it. But why didn't it work for the end value? This is because till the 10th iteration, I have the value 10, 10 over here. I print the value 10. It checks if it's greater or not. It's not, so it doesn't break the looping statement. The I value comes here, makes it 11, goes back, prints it, and then checks it. So instead of doing this, if I just take it and shift it here, removing all the excess blanks, and then run it, you see that it does the thing that we want it to do. So I intentionally made that particular change to illustrate this particular problem. You see that uh, the only difference is the if statement from the while, as we discussed, but we have this particular thing for do while is you enter the loop without any conditions, so it's going to run and run.
but it only exits when the condition is true. In this case, when when I is greater than 10, it breaks, as we saw, and it stopped printing after 10. And just because I had the I statement below, you could see that uh, we still had an extra iteration for that matter. You got my point. So if I just take it back here and do this, oh, I'm so sorry. You see that the infinite loop is going on because it doesn't break. I'm gonna go on till I stop it. You see at the end that there was a keyboard interrupt. I stopped it on purpose. That's another application of it. So I basically wanted it outside the if statement and print it so that 11 comes back. But anyways, you got to see a infinite loop run. Anyways, so that's the basic idea of it. And I wanted to illustrate it back because you see that there's an extra iteration going on just because the I statement increases at the end. So if this would have been a general while loop, going back to the starting point to the loop here, it would have checked and stopped the loop immediately. But it still enters the loop an extra time. So that's what do while loop. So we have a small pattern question here, which is quite common in most of the uh, exams, or you want to say in any of the coding competitions. They have a lot of pattern questions, and they are pretty interesting to solve as well, and especially in Python. So this is this is the legends way of solving it. I just press enter and you see that it prints the same uh, structure, or you can say the pattern. But this is not the way you should be doing it, because this particular thing only works in Python. So to make your code more optimal, or you can say platform, I wouldn't say platform independent, I would say programming independent. Like you can use this particular logic in each and every programming language you encounter. So you would basically do something like this, where you have one for loop, because this particular structure, I know how many number of stars I want and how long it's going to run. So it's going to run from 1 to 5, because the maximum number of stars, if you see, is 5. And I am going to have a nested loop. This is called a nested for loop in this case, where you have another loop inside the loop. So for the first time, the value over here is 1, and it goes inside, goes in the J loop, and it says I want to run this particular loop from 1 to I plus 1. Now, initially my I value is 1. So it does 1 plus 1, that is 2. So it's basically going to run from 1 and less than 2. So less than 2 is 1. And so it gives you this one particular star at the starting. Now it goes out, goes to the net. I'm specifying the end to be null. So this is a space. This is a difference. You have a space here, and these are just null values. Basically, it means that I don't want it to be anything. I want it to be nothing. By default, remember the end value is basically slash n, which takes it to the next line. Now, the next line thing is done by this particular print statement. Now, I'm not passing any parameters to it, because by default, end value is slash n. So that does the job. Now going to the second iteration, the value becomes 2, and 2 is less than 6. So it goes inside the loop because it satisfies the condition. And you see that the J loop runs from 1 to 2 plus 1, that is 3 now. So it's going to run uh, for the first time with value 1, is going to increase it to 2, and because 2 is less than 3, is going to run 2 times. Now it's going to run, because it's going to run 2 times, it's going to print 2 stars with no spaces in between, and that's how we get this one. So I hope you got how you go about solving these pattern problems. This was the basic one. So this is your homework question, where you print the opposite of this particular pattern. So you need to make a few changes here, and you'll understand how to print them. You can type your code here. And this solution will be given in the PPT, but I highly recommend you to try it out first. And even after trying multiple times, you are not able to, then generally or definitely go back and look it up. And you can try out different questions. I'm going to talk about a particular website where you can practice Python to be more fluent in it. But before that, let's just finish off this video. So you have something called the user-defined functions. So what do they mean? So there are general base functions that Python have, and there are a few functions that you can write for your own ease of working with the particular code. Let's look at it and we'll understand what is going on. So we run this particular code and we see that the maximum value is 23. And why is that? So I hope you know about the multiple assignment as we covered in the previous video. So basically I'm passing num1 to be in the the maximum, to have the maximum value, and then I'm checking if uh, num2 is greater than the maximum one, and I'm saying that okay, maximum is equal to num2, and I'm printing that. Now because it's in the order and the second value that you encounter is greater than 23, it basically says that okay, it's 23 is greater than 12, so your maximum becomes 23, and I do not look at the else if statement and I go here. Now remember I was talking about particular structures where you need to have multiple if statements. This is one of those typical cases. So because I have an else if statement here and my if statement before this is true, I'm not even going to consider the else if statements or the else statements beyond it. So what I do over here is I do this and it turns out to be correct. So this is a typical situation where you have multiple if statements, but it's fine, but we're going to optimize it to have a better understanding. So this is how a basic non-parameter function looks like, where you have def is the particular key, it's more of a reserved word. We call them reserved words like if and int and float. So you cannot have a variable named float. So these are a few things that you cannot use a variable as. So I'll add that point in the top section where we have talked about the variable names that you can provide. But so def is a reserved keyword that basically specifies that anything that is beyond this is the function name, and after brackets, so basically you pass different parameters in the bracket, but in this particular case I do not need it. And you call that particular function like this. So basically you say that okay, I just want to call the display function. So when I run this, basically what happens is it doesn't even consider this particular statement here until unless it goes here. So when you say def, it doesn't run this particular statement. It just goes outside it and checks what is the next statement. So even if I do this, it should still give me the answer. So you see, it makes it way more easier for you to print a particular statement that you want to. This is just a basic example and not an ideal one according to me, because if I have to have multiple print statements, I will print it multiple times, and for this, if I want to do it 2 times, I'll do it 2 times as well. So where does the difference come in? Let's see how do we overcome that. Okay, so before that, let's just look at the default parameter settings as well. So instead of passing nothing to the particular function, we just have num1 and num2, and I cannot do this now. Sorry. Okay, I can do it because I'm specifying the values here. Okay, So if I do not pass any particular values, what this particular statement says is my num1 and my num2 is 1 and 2 by default. But if the user wants a different value, I'm just gonna enter 4 and press enter, and it's going to update the num1 value to 4 and the num2 value remains same. I can do the same for num2 and now the value is 5. You can specify both num1 and num2 to some value, and the value should change accordingly. Now, these are the default values and these are the updated values. But what happens if I do not have default values set up like this, and I do not pass anything to the particular function? Right? It was working here, right? But let's see what happens here. It's going to throw me an error saying that it's a type error saying that sumCheck, the function, misses two required positional arguments, num1 and num2. So because I've specified that this particular function has two parameters, I need to pass two parameters to. Now I can either specify it like num1 is equal to 12 and num2 is equal to 13, sorry, 13, and then press enter. Or I can just say 12 and 13 and that does the job as well. So you do not need to specify the num1 and num2 values. If you just pass the particular values, that does the job as well. So there's a concept called global variables and local variables. Now, what they basically mean is global variables are something that you can access throughout the entire, you know, for in this particular case, the entire notebook. But a local variable is confined to the very function that it is defined in. Now, if I run this code and I see that the value outside the function is getting printed first, and then the inside function is getting printed just because I have the print statement and then I'm calling this particular function, and that's how the execution sequence is. So if you see, the print statement outside the function has a num1 value of 2 as I've defined here, but when it goes inside the function and I've specified number 1 here, it basically considers the number 1 value from here, but it doesn't destroy the particular value. So even if I'm printing the num1 after the display function, you'll see that it still considers the number 1 value outside the function, like basically the global variable. So how do I access global variables inside the function then? So let's see how it works. So I'm running this particular code and I see that the num1 value over here is 2, and it prints that, okay, printing outside the function num1 is 2. Okay, so this is working fine. Then I'm calling the display function, which calls this particular function, and I have something called global. So when I mention the keyword global, again, it's a reserved word. That's why it has a different color than the normal text. So when I mention global, basically what I'm saying is this variable is a global variable and I want to change the value for the global variable. So now when I'm printing the num1 value inside the particular loop after changing the num1 value to 3, it is doing the same thing. It's printing the local variable num1 value as 3. So it was doing the same thing here. So that's fine. That's understandable. But when I'm printing it for the second time outside the function, I see that the value is changed to 3. Now this happens just because I've mentioned the global num1 here, and it specifies that this particular variable is a global variable and I'm changing and I'm overwriting the num1 value, not a temporary variable that is defined inside the display function, but this num1 is a num1 that is there present outside the display function. This is a base. Basically, it's a global variable that I'm trying to work with. That's why it changes the value and prints the value 3 instead of 2. So I hope you understood the concept of global and local variables. So we have a question here saying you need to find the max of three numbers. So we have a function called max in the Python basic functions, and all the numbers that you pass in as parameters, it basically looks for the maximum number and returns the value. As we saw in the user-defined functions, the max function does a similar thing. Now, when I print it, it comes out to be 34 as expected, but this is a one-line thing. But we need to understand how does the max function work. Before that, I would like to have a small tip that I would want to show. So you see that when I do this, it basically turns green, showing that it's a function. So you understand that it's a reserved keyword. But that's not what I'm trying to show you. So Jupyter Notebooks has this particular function where you can understand what the function does and what are the parameters that you pass to the particular function. You just go inside the brackets, like as displayed now, and you do Shift Tab, and you see a doc string comes up. This is basically the document string. And if it's readable for you this way, it's fine, or you can just press the plus button and it's going to expand. And you see that you can pass in all the values like these, and with the string iterable argument, the biggest item, it gives you the basic description of what the function does. And it's a built-in function or a method. It shows that it's a built-in function of Python. It belongs to the base module, like all the functions that come along with Python. So that's how you do with all the functions that are there. And even if you're importing libraries, we are going to learn that in the upcoming videos. Even when you're importing libraries and you say forgot a particular, forgot the parameters that a particular function takes. So you can just do this and it's going to tell you what the particular function does. That's one thing. And understanding that it belongs to the base, it belongs to the built-in function that comes in with Python. It's fine that we use it, but we also need to know how to go about using it, or how does it work actually. So you have the same numbers and the same assignments. The other thing that I would want to mention, I'm specifying it over and over, not because I cannot access num1 value in this particular cell. I can access num1 value even in the cells previous to this if I have run this particular cell. But I'm just specifying it over and over again so that you need to understand this section only, and you do not need to find, okay, where did I assign number1 value? No other reasons. You can just assign number1 value, number1 or number2, 3 value, whatever you want to assign, or whatever variables you want to name them. You can assign it anywhere in the code and access it anywhere in the code, considering that they are global variables. Again, no, you cannot access temporary variables. I'm specifying it over and over again because it is important concept, and people do get confused a lot in that. Anyways, so we see that the maximum value that I'm putting in is 0. And we have 12, 23, and 34. And we are doing I won't say a nested if statement, but we have a cumulative if statement, which is checking if num1 is greater than num2 and num2, and num1 is greater than num3. And I do the same for num2 and num3. And I'm basically assigning the maximum value to them as and when the condition is satisfied, and I'm printing the maximum value. It's a pretty simple code if you look at it, but there are a few flaws. But let's look at it if it's working or not. Okay, so it's working for this particular state. Now, what if I do a thing minus 32, minus 23, and minus 12? So basically, minus 12 should be the biggest, but let's see what it returns. Okay, so it returns minus 12, which does the job again. And let's look at the optimized version of this thing. Now, I'm mentioning that it has an intentional error. Let's see what it does. So this basically prints the 34, but what if I do minus 12, minus 23, minus 34? Yeah, let's enter. So because I'm assigning minus 12 to this, it basically does the job. But say I assign it a different value, what does it do then? So this is going to give me 23, which is the next biggest value. This is the more optimal way of looking at it. So instead of having so many, clustered if conditions, multiple checks, to make it more simpler, you can assign it the same values as this one. I'm just going to copy this and paste it here. You can assign it the same values, and you do what you do is basically assign the first value as the maximum, saying that okay, so this is the maximum. Now, what it does is it basically reduces one of my conditional checkings. So if my num1 is the greatest, it's going to be greater than num2 and num3. So I just need to check if num2 and num3 is greater than num1 or not. So that's exactly what I'm doing here. So if num2 is greater than the maximum, then the maximum is num2. And I'm changing the maximum value here just because I want to go ahead and check it with num3 as well. So considering if uh, my num2 value was greater, now I'm going to check my num3 and num2 value. That's exactly what it does here. And when I press and when I run the particular cell, it's basically says that minus 12 is the greatest value, which kind of makes sense. I'm just going to remove the negative value so it's easier for you to understand. Now it should give you 34. Yeah, it works. So that's how you optimize this particular code. Now, this is fine, but say if I have to check for a different set of values, what I need to do is need to assign the numbers and then write this entire section again and then print the maximum, which is quite redundant. To reduce the redundancy or to remove it completely, what we do is we do the same thing, but inside this particular function. So if you see this particular section is exactly copied in here. The only thing that we have an extra over here is we do not have a print statement. We could have had a print statement as well, no such necessity, but we have, we are basically returning the value here. So this again a keyword. Uh, Basically what it does is the whatever value you get over here, say in this particular case it's maximum, so it returns the maximum value and sends it to the particular calling variable. In this particular case, I'm not calling it into a variable, but let's just look at it in general, what it does. Okay, it does the same thing. So it starts reading from this particular line, it assigns the values. It says, uh, okay, so I'm assigning it to a particular variable, which says that value returned by the function. And then I'm, calling this particular function by passing in the numbers. And then I'm printing whatever is there inside this particular variable. Generally, you should not have this big variable name, but I'm just, I just wanted to be clear what does this variable have inside it. So just for that reason. So, and that does the job, right? So even if I want to find the maximum of three numbers anywhere outside the particular uh, cell, I do not need to rewrite this entire thing. I can just call the maximum function. So that's exactly what user-defined function does for you. So after that, obviously, we have a homework question which says that you take in three numbers as input from the user, make a user-defined function to sum them up. If the sum is greater than or equal to 100, then print beyond century and the total amount, else print uh, we are yet not there and the total amount. So you can again type in the code here. And I've mentioned that the answers are there in the PPT just so that you have a place to go and check up if you have done the right coding. Or you can also check the various variants, so you can have a different approach, and which is completely fine. People have different approaches, and your code might be even more optimal than mine. So go out, try, and that was the basics of Python. We are going to look into some other concepts of Python. Today we are going to learn about the data structures in Python.
before we dive into that, there are a few concepts called, firstly, I would like to discuss indexing and the length of particular data structure. So indexing is something that, when I say indexing, the first thing that comes to your mind is an index in a book or some index basically which refers to the value and to the location of that particular value. So over here we have a name called Luther, and these are basically the indexes as specified. So L is in the 0th index, okay, by default, or so there is no change of settings. So any data structure in Python starts from 0th location. And if you're going to see, the number of letters in this particular word is 6, but it goes up to 5. And the very reason it goes up to 5 is because 0 to 5 makes 6 letters. And that's why the length of the word is 6, but the last index is 5. So you just need to remember that the index always starts from 0 and it runs till length minus 1. That was a basic understanding of indexes and length. Let's just look at a data structure called string. So basically, the string is a list of characters, or you can say, a lot of characters arranged in a particular way and are grouped together. So in this particular case, you see Luther is basically a list of all the characters. When I say list, basically I mean, many letters added together in a sequence. So which makes your data structure as well. So when I say string, you need to understand what are the characteristics of string. So the characteristics of string is it is iterable. It means that you can iterate through it. You can go about accessing each and every value through the indexes, and it is not mutable, which the better word for that is immutable. So let's look at the examples to understand this better. We have the iterable example here where we have a name Luther as specified here, and the print statement is basically a formatted one, and it says what is the letter in the first location, and I press enter and I see that it says U. So now in the first location the value was Lu, exactly. So it is saying it is working. So when I do ND and I change this to second, I'm sorry, did I do something wrong? Okay, yeah, sorry, my bad. I didn't make the change here. So when you press this, you see that the value over here is T. So when you want to access a particular index, or you want to access the value for that particular index, basically what you do is you place in the index inside square brackets and with the particular variable name in front of it. And what it does is basically it says that, okay, this is the variable and you need to check the second index for this particular variable and return me whatever is in there. And for this particular case, it returns T, which is in the second index. Now, let's see what immutable does. Now, there's an intentional error here because I said that it's not mutable and I'm trying to alter the value here. Let's see what it does. So it basically gives me an error. So everything is same. I wanted to know what is the value in the first location, and I changed the value to V. So instead of U, I would have had a V now, but it's not doing that, saying that the string object does not support item assignment. So basically what it means is you cannot change the value once assigned. So if I comment this and then print it, it's going to give you the same thing that we were looking on the cell above it. So just remember this intentional error here, and I specified it just because you should not run this and say, okay, if there's a something, there's a wrong code that has been circulated. So it's not that. It has been intentional because I would want you to understand that you do not assign any
values once it's already assigned to the particular string. So that was about strings basic. Now we look into the string functions. So you have a function called count, and as specified before, you can go inside the function and you can just press shift tab to see what the function is about, what are the parameters and how you go about using them and all that basics. That is one of the things. Now I can either see what is the count of L here. So the count of the character L is 1. Okay, that works. What is the count of the value LU? Okay, that's 1 as well. Okay, I can see that LU occurs once. Okay, let's just see if it works this time. It says 0. Now, because there is no sequence L and then lowercase u, it returns you a value of 0. Because you're making a search that is case sensitive. When I say case sensitive, basically what I mean is uh, L, so LU is not equal to, so basically you specify not equal to, like basically specify not equal to like this here in Python. And it's basically not equal to LU for that matter, or it's not equal to lowercase l and a capital U. So you just need to understand that, and that's why I had taken up this example for that very specific reason. Let's look at the various cases and character types. Running this, I see that Luther is upper is giving you a true value, and because the if value is true, it's returning upper, so it's upper obviously. And it checks if it's alphabet. Okay, it's an alpha. These are alphabets, so that works, and that's printing as well. It also says that it has a combination of alphabets and numbers, which is not wrong exactly, because it does have a sequence of alphabets. Now alphabets, so the function is al number checks that the string that you have passed to it has either alphabets or numbers or both. So when I say Luther 1 and then press enter, you see that is alpha is returning a false value now, because the string that is passed to it just doesn't have alphabets. It has alphabets and numbers. But you see that the is digit function is passing your false value as well and not printing numbers. It's just because the particular string doesn't have just digits. So if I had just one in the particular string and would have run that, but these two conditions would have turned out to be true. Let's look at the other function that we missed out, that's lower. So LU Luther comes out to be here, and we see that the same functions as upper come out to be correct. So that was a bit of playing around. You can obviously tamper with the code and look for yourself how you go about using them and which particular sequence gives you uh, outcomes as you want them to be. So completing that, we can see that you can change cases in the string as well. Now I have an arbitrary string here with alternate cases. So L is capital, U is small, T is capital, H is small, and you go on that way. Let's see if I press enter, what does it do? So you see that the cases here were not sequential. What this did is it converted everything to a smaller case. That's what lower function does for you. So the lower case does that. So now I'm changing the name to uppercase. So it changes everything to uppercase. After that, we have swap case. So initially we had L as capital and U as small. Uh, and here we have the L as small and the U as capital. That's what it does. And capitalize basically changes removes all the formatting. It converts the first letter to a capital one, and keeps everything else in the lowercase. So that's what it is doing here. Even if I have a lowercase L here and I press enter, you can still see that the L over here is capital. So that's how you change the particular
cases in. So that's how you do string formatting. Basically, you want to change the particular case to a specific case. Say I want all lower and I want all upper and I want to swap the case. So these are the functions that you use. Now, I would also like to extract the strings. In a few cases, you need to extract a particular part of the string, which is called substring. So that's what we are going to look into here. So Lex Luthor was a villain in the Superman comics. So this is a statement from the Superman comics. If you have a reference to that, it's basically, even if you don't, it doesn't matter. It's just a sentence. And then we would like to do some string manipulation. I'm going to comment this out and print this. So basically what this says is I want all the letters, or you can say all the characters present in the particular string from the 0th index to the to the second index less than 3. So it's going to give you a total of 3 values, correct? So you see that it is 1, 2, and 3. I'm sorry. So this is 0, and then you have 1, and then you have 2. So it's gonna return Lex. Okay, so that's understood. So now I want to have 3 characters starting from 11 all the way to 14. Okay, let's see what does that give us. So it basically gives us was that is present here. So let's count the values. So we know that the index of X is 2. We have 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11th position has a W, which is correct. Then we have 12 and 13 and 14. The 14th is the blank. Everything below it is considered. So we have 11, 12, and 13. So that gives you the output. Now let's just look at the other statement here. Okay, so we have characters starting from 11 all the way to 14. Well, this is something that's wrong here. I didn't intend to put that here. So I basically want all the values starting from 1, all the all the way to 14, with a skip of 2 in this particular case. Yeah, that's what I want here. So you see that it basically runs all the way till here, and the values are skipped. So I want the first value here because it starts from 1. So I want E. I do not take an X into consideration. I take the blank. I do not take L. I take U. Then I take H. Then I take R. Then W, and so on. So that's how it goes about it. And let's see what this does. Okay, so basically, if you see, we had the sequence here that was going from 11 to 14. Here we have 14 to 10. Anything that is greater than 10 is considered. But here we have a skip of -1. It's not basically a skip. The iteration value is -1. So it's basically going to take the indexes in reverse. So it's basically going to take in the index in the 14th location, that is S first. Then it says, okay, -1, that is 13. Okay, I'm going to take in 13. And then so on. And it basically says, and it returns you was. So because of the negative indexing, I have the reverse of the particular. Now, if I want the entire string to be reversed, instead of doing, uh, okay, I want the starting index, then I look at the ending index, and then I do -1, I can just do this. So these particular blank spaces means that I want everything, but in the reverse order. -1 specifies that. So if you read it using a mirror, basically the sentence should look like this. So that was about the various substring formats that you can do. So if you want the number of words in a sentence, you have a particular sentence here, and you can use the split function. Now, the split function basically takes in an argument which basically specifies which is the character you want to split it via. So when I press enter, you see that the length. Okay, so there's a length function also associated with it. Let's just look at what does the split look like. This, and I see that the words are Lex Luthor was a villain in the Superman comics. So if you count the particular words, it should turn out to be 9. Now, this is not an ideal case because you can have spaces in front, behind it. But before that, let's just look at a different character and then see what does that do. So you see that I had L before it, so that's considered a word. Everything else till this is also considered a word. Sorry, this THE. Yeah. So that's the second split. Then you have sub, and then everything after E till Bobets. So that's what it is doing. It's still showing you 9 because I did not put in E here. Now I'm going to show you 4 as it is here. But what I was saying earlier was it is not the ideal case because if you have, say, a space here in the middle and then I press enter, you see that the word count increases by 1 because it considers a null value that is entered here because of that extra space. That's something that we need to, encounter and remove. We're going to look into that. Now, how do we do that? Now, because it was not that specific here, let's look at a more detailed version of it. We'll keep it this way. Let's illustrate the error. Okay, so I have replaced the spaces with an underscore here so that you can understand where I have put in extra spaces. In this case, underscore. So you can see that I have an extra space here, extra space here, 2 spaces here, I think 1 space here. So you have 1 before Lex as I specified. You have one extra space after villain here. You have 1 extra space after that is here. And you have an extra space after, I think you have 2 extra spaces after comments. Yeah, that is specified. So basically, it's not giving you the correct answer. So how do we go about it? Let's make it a question, obviously. So count the number of words present, but in this particular case, I'm specifying that it's correct for all the cases. Okay. So we take in a sentence as with the same number of problems. So I'm taking up this sentence, but now because we already know where the spaces are and what are the issues, I'm just reshaping them as spaces because that's how the normal problem is going to look like. So we have the original sentence that has been printed here. Let's just comment out everything. Let's see. Okay, so you have a space here, you have 2 spaces here, and you have some space here, and the length turns out to be 52. Okay, so length of the sentence is 52 now. Let's see when I do strip, what does it do? I'm just going to take this sentence and print it here. Let's see what does it do. So now it turns out to be 48. So what did strip do basically? If you see the particular output, I have 2 blanks here and I have 2 blanks here. But in this case, if I try to highlight this particular sentence, you'll see that there are no blanks either on either sides. So that's how the value turns out to be 4 less. Okay, so that takes care of the spaces on either sides, but we still have the spaces in the middle. So what I do is I have the list of words, again splitting it by the space. I'm just having I just taken a new variable called new sentence and assign it a blank variable. This basically means null. It has nothing in it. And I have, I do not want the print statement here. And I just I loop in using all the words. I loop in using all the words that are present in list words. So list words should ideally have all the uh, words that are present here. Let's just look at the thing that is there in the list of words. So I'm coming this out for a moment. And you see that everything, all the words are present here. We are almost there, but you see that there are a few extra spaces here. Now I need to remove that. That magic happens here. So we have a we already have the variable assigned here, and I'm saying that for I in list of words. So now you see I'm not using the word range here. So what this does is this considers the entire list and makes it iterable in a way that the first value of I is Lex, the second value of I is Luther, the third value of I is was, and that's how it goes on. So I'm just checking if I is an alphabet or a number. So if it is an alphabet or a number, what I'm saying is then just add the new sentence and add I to it and add that extra space. So let's just look at what the new sentence looks like after I have done the pre-processing of print the new sentence. I do not equal list of words here now. I print it. Now it is Lex Luthor was a villain in the Man comics, but you see that I still have an extra space here. Now that is because of the extra spaces that I wanted to have in the middle. It created an extra space at the end. So that's fine. That's not an issue. I have a function called rstrip, and that removes the particular space the from the back. Now you also have something called the lstrip, which basically specifies itself. So if rstrip removes the spaces from the right side, lstrip removes the spaces from the left side. So instead of having a space at the end, if I would have specified it something like this, and if I would have done an lstrip, if it would have given me the same output as an rstrip with the specifications before. So you see now there are no spaces. So it does the same thing, lstrip and rstrip. So in this case, I'm letting it be with lstrip, and after having the new sentence, I'm not done yet. I still need to count the number of words and what is the length. Let's see what the print statements do. So I have so let's just go through the entire output again. So I have the original sentence here. I'm having a few spaces here and some in the middle and some at the end as well. So the total character length is 52. Now, after pre-processing the sentences, I have something like this, which gives me a length of 46. Now, what I do over here is I just take in the same function as here, the length split thing, and I pass it the new sentence that I created with the character length of 46. And now that gives me the correct value as we looked here, correct? So even though if I have as many spaces, so if I add in a few spaces here, a few spaces here, and then run it again, you see that. So you see that the value changed to 56. The length of the pre-processed sentence still remained 46. Okay, I'll just do it again with replacing spaces here. See that the value changed to 54, but after the pre-processing, the length of the actual string still remained 46. So that's how you go on to, you know, correctly do the thing. But again, we would want to modularize the code. So I'm doing it in the way you should be doing it or you should be going about it. So instead of directly making a particular function, try to solve the problem first. Once you have solved the problem, as we have solved it here, and use print statements extensively to understand what is happening after that statement. Like we looked into what is the value of the new sentence, or what are the strip values, what are the split values,
what are the words after I'm using split. So use print statements extensively to understand and even explain what you're trying to do. And then go for modularizing the entire code. So you see that I'm pre-processing the word in this particular section. Is the same code I've just copy pasted and sectioned it out so that it's easier for the user to understand. And here I'm taking the user input, and now this is the process sentence, and then I'm passing the process sentence to the word count function, which basically prints the word count of the sentence that is passed to. So let's see what it does. I'm going to run this particular section. I'm going to take in the same code. I'm going to take in the same sentence here so that we can understand and check if it's correctly doing what it's supposed to do. And then I press enter and it gives you 9. So that's how you modularize the entire code and go about it. So here we have a homework again for you guys, where what I'm asking you to do is you need to count the number of numbers present in the sentence, uh, use the user-defined function and develop it in such a way that it takes any sentence as an input and gives you the correct result. Okay, sorry for the error here, and gives you the correct results. So basically what you need to do is you need to work on something similar, but instead of words this time, you need to look in for digits, or you can say numbers for that matter. So we looked into the function isNumber. You can use that. That's a small hint for you guys. But do try it out and write your code here. The answer should be present for you in the PPT. So after doing that, we have a different data structure called the list. Now the list can have heterogeneous values. So what I mean by heterogeneous values is heterogeneous values in the form of the data type. So you can have int data values and float data values in the very same data structure. Now we're going to look at the examples to understand it better, but you need to look at this part. So it is iterable as a string was, but this time it is mutable. So let's look at it one by one and understand what the characteristics are. So I have a list of values here. It is from 1 to 5, and I am printing the values in the list. And then I want to look at the index value to what is the value inside that particular list at index value 2. And I press enter and see that in this, sorry. I don't want to look at the index. I want to look at uh, I want to find the index for the value 2. I don't want to look at the index. I want to find the index. If I have to look at the index, it's something similar that we did. We just do this. Sorry, look at number 2. The and then I present. And now you see that in the second location I have 3. I have presented here. So this particular function index basically takes in a value and returns you the particular index for that particular value that you pass here. So I want to press in 5 here and then press enter and see. So basically it says that it's in the 4th index. Now let's see something that is outside this particular value and it's not present in the list. Okay, if 6 is not present in the list, it's going to return you that. It's going to return you an error. So that's what I wanted to demonstrate. I'm looking at 5. Yeah, so multi-characters now. So that's what multi-characters look like. So you have different data types like name 1, name 2. You can also have, say, float values. You can also have integer values, and it's not going to throw you an error because it can tolerate multi data types in the very same structure. So you have multi data types characters can be added to the same list, press enter, and shows it, and it runs without an error. So you have a list here, the same list as specified above, and you append the value 6 to it. So remember, I had added the value 6 and I was looking for it, but I couldn't get it. So now you just cannot have a list underscore of underscore number. And I know that
the last index is 4. So I just cannot say something like this. What I'm trying to say is I just cannot have something like, say, 5 is equal to, and I say 6. So basically what I'm trying to say is in the fifth location or in the fifth index, I just want to have the value 6. Now I just comment all of this out and press enter, and you see that there's an index error. So list index out of range. And that does it because I'm already specifying the list as 0, going from 1 to 5 and having an index of 1 to 4. So, sorry, having an index of 0 to 4. And that's why it's not able to assign a different value in the fifth location because there is no fifth location. So it's not going to work that way. So if you want to add a value at the end, you just need to use the append function, and that does the job for you. So the values in the list, this, and press enter, and you can see that it prints the values in the list, and the index of 6 is 5. It gives you the value here and doesn't throw an error like we saw earlier. Let's see what it does for this particular piece. Let's comment this out for the time being. So I am appending 7 and 8 to the list, and I'm just looking at the list. Let's see what it does. So I'm appending 7 and 8. It got added, but why are these extra packets there? Doesn't make a lot of sense. But I still want to see what is the index of 7. So I press enter and it says 7 is not in the list, but it is there in the list, right? Like it should be present in some way or the other. Or I can just say, let's see this. Does this do? It's still showing me an error. Why is it doing that? Because it's still in the list, right? So it shouldn't throw me an error. Okay, let's just see what this has to do. So this doesn't throw me an error. This shows that in the fifth index, you have two values, 7 and 8. So what append does is it basically adds in anything that you pass to. So if you want to have separate locations for each and every value that you pass in, you basically need to use the function extend. Now instead of append, I use extend, and let's see what it does. So now when I have when I want to access or have a look at the index of the value 7, I basically get 6, which basically what I wanted initially. So that's the difference between append and extend, and that's how you go about using it. So there is something called nested listing, and to understand that better, let's look at the illustration here. So you have the list values as specified here, and this is one cell. So this is one cell, this is one cell, and this is one cell as well. So what I'm trying to demonstrate here is something like this, where you have two values in the same cell. So, and you have the sub indexes. So if I just consider this to be a list, you see that it has the 0th location and the first location. Now, considering this to be a list, it will have a 0 and a first location, and so on. So that's what basically nested lists mean. So you have lists within lists. So you have the index value 0 and sub-index values 0s and 1 for it. You have the index value as 1 and you have sub-index values as 0 and 1 for it again. Let's look at how you go about looking at it. So the elements in the first location is 3 and 4, but the element in the first location of the first location is just 4. So I wanted to look into this section. So this is the first location as mentioned here, and the first location in the first location is 4. So this is 0 and this is 1. So it's going to give you 4. Okay, I hope you understood that part because it's quite interesting as well as important. And you're going to look at how you go about using them. To print all the values in the list, I did this. Okay, so that does the job. So I have a same nested for looping structure here. So I take in the length of the nested list and I pass it to the range. So now what it is basically doing is it's basically doing 0 to length minus 1. Length minus 1, basically I'm specifying it length minus 1 because it's basically says that it is less than the length. So if the length say is 10, it's going to run only till 9. So that's what it basically means. Yeah. So, and I have the J loop, which runs from 0 to the length of the index values or the list that this particular value gets. So if my I loop gives me a value of 1, and if you want to see the first index has 3 and 4 in it, so the length of this particular list will be 2, and it's going to run from 0 to 2, which will have an index of 0 and 1. So that's basically what is happening here, and that's how I can access each and every element in the list. Let's look at the question to practice and get our concepts more clear. So you need to print all the first elements of the items present in the nested list. So I have a nested list present here, and I want to print all the first elements. So I run a loop as I would, and then I'm putting in the value. I'm putting in the value 1 for the sub index, so that I just get the first. I just get the values in the first location in the sub index category. So I'll just run this, and you see that that works. So again, I'm just providing you with a homework here, which yeah. So the homework over here is you need to print all the values. You need to iterate. You need to use something similar and print all the values in the 0th location. It shouldn't be difficult. You need to just change one thing. That's the hint for you to work on the particular code. And I'm going to leave the section empty here to work for you guys to work. Now, the most common questions for list for basic Python programmers is sorting. So there are a few ways to sort it, but we're going to look at the difficult way first before looking into the faster way. So let's consider this to be the list. And I again have two sets of lists running here. This might look a bit complex, but we'll just divide it and try to understand it. So I know that I'm going to run the list from length minus 1. So why am I specifying it? So considering the example before, say the length returns me a value of 10. So my for loop will run from 0 to 9, correct? But if you see, I'm basically saying j plus 1 here, or j plus 1 here, and there are other indexes that basically specify that I'm trying to look into the index that is after the index that I'm currently looking into. So when that happens, say I'm in the 9th index and this condition comes in, basically what I'm trying to say is I want to look into 9 plus 1, that is 10. Now it's going to give me the same error as before because there is no 10th index to look into. So what I'm doing is I'm reducing the index to 0 to 8 by saying length minus 1 here, which is going to reduce the value to 9. And now the for loop will run from 0 to 8. So when it comes in the 8th iteration, so when the j value is 8 and it does 8 plus 1, it provides me a value of 9. Now I have 9 in the list, so it works that. So that's why I have specified minus 1 over here. So running the loop in the second section does the same thing. So basically it's the same loop running again. So I want to iterate the entire loop, the entire list as many number of times as the number of elements present in it.
So the concept is by the end of all the nested iterations, the entire list will be sorted. Let's just look at it. So what I'm doing here is basically swapping, but it's kind of an easy concept if you look at it. So you have a temp variable where you're storing this particular value, and you are storing the next value in this particular section because that's greater than the one present in the current value, current index, and you are replacing the next index's value to the one that was present in the current index because we stored the current index value in temp, correct? So that's how you swap it. Let's just understand it from the sidelines here. So say my current j index value gives me a value of 8, and the next index value is lesser than what 8 is. So say the next index value gives me j plus 1, gives me a value of say 10, gives me a value of 7. Now I want to swap it. So basically what temp does is it stores the jth value. So it does this, and what the jth value will look like now is I'm going to take in whatever is there is in j plus 1. I'm just going to paste it here, which does this. So now my values for j and j plus 1 are saved. That is 7. Now I need to change the value for j plus 1, right? So I do j plus 1 is equal to temp. And I do not do j because now they both have the same values, which so if I just say j over here instead of temp, it basically is assigning it the same value as it currently has. Now that's the very reason I stored the value before overwriting the value of j plus 1 in j, so that I can replace it whenever I'm done with putting in the value of j plus 1 in j. So that's what it does here. So let's look at the sorted list. So you see that the smallest number is 2 and the highest number is somewhere around 5,324, and it does the sorting pretty neatly. So that's how the sort function that we're going to talk about here works in the background. So what it basically does is if you want to have it, so by default it's in the ascending order. So the reverse is by default set to false, and it returns you the same list as we did here. And if you want it in the descending order, you just say reverse is equal to 2. In this particular case, you just change the particular sign. You change the particular sign to a reverse, and it should return. Yeah, it returns you the descending order of the particular. So I'm just going to let it be the one that actually and keep it that way. Yeah, so that's how it goes on to work about. So that was what this was about. Let's look at a different data structure called tuple. Now, tuples can also have heterogeneous values. It is iterable, but the main difference is it is immutable. So the structure looks somewhat like list, but you have round brackets instead of square brackets here. And let's just run this to understand this. So I have an alphanumeric tuple which has these values and a numeric tuple which has these values. So I'm printing both the values to look at to have a look at it, and it doesn't throw me an error saying that it can take in multiple data types as its container values. So that's out of the way. So it does take in heterogeneous values. So that's true. And I want to see what is in the index of 1. I said that it is iterable. Let's see if it's true. Yeah, it's iterable. I can have a look at what the index 1 has. So that's what I'm doing here as well. So I'm checking if I can do it in the alphanumeric section. Yeah, I can do it in the alphanumeric section as well. For the alphanumeric tuple, I mean. And the next thing that I have is
the only functions that tuple have is index and count. You can have a look at all the current functions that this particular data type has. So this is a tuple data type, right? Now, how do I check that? I just do type and see it. But before that, I'm just going to comment these out and I press enter. You see that the value, the function returns that it's of type tuple. So now that I know it's of type tuple, I would like to know what are the functions present. So I press the dot. Or if you consider full stop, you can just press full stop if you consider that, but I'm just going to say press dot. And then you press tab. Now, when you press tab, you get this drop down kind of thing, which gives you a list of all the values that is there. One being count and index as shown here. So keeping that out of the way, that is for all the data structures, not just this. You can even have it for lists and see all the functions that are present there. And I would actually recommend you guys to go ahead and look up all the functions in the list data structure and in the string data structure. So getting that out of the way, let's just see what this does. And I press enter. So the index of the number 2 is 1. That's correct. I have it in the first location. And how many times do I have the number 2? So I have it 2 times and that's what it is returned. So that's okay. So what makes it different than list? So I'm having I do have an intentional error here. Let's see what the error says. It's a type error and it says that object type tuple does not support item sign. So I cannot say, okay, I have the first index. I just want to replace the value of it to 2. Or say, okay, I already have it to 2. I'll just replace it to 3 and press enter. But it doesn't do it because you cannot change the value that you've already assigned to it. That's what immutable means. That's what we even saw in strings, correct? Okay, that's another thing that you need to know. If you have this particular section and maybe you have a long error or maybe a very, very long output. So the best thing to do sometimes is just hide the output. So you can just double click on this and it hides the output. So that's one other thing. So apart from that, let's look at the last data structure in this particular uh, video is dictionaries. So before going there, I would like to talk about key value pairs. That's the basic concept in dictionaries. So it doesn't follow the general indexing pattern. So it's a unstructured data, unstructured in the way that it doesn't have a sequential index. You pass the index values, which is referred to as keys here, and the values inside it are referred to as values. So it has a key value pair structures, and the values are overwritten uh, in there in a if a new value. Sorry, uh, if there is a new value assigned to it, it is iterable and mutable. So let's just check out each of the conditions that I mentioned here. So I have a dictionary that contains the student names and their marks in the math subject. I'm just going to print it out and you can see this is how it looks. Now, if you see, they use a different bracket. It's called curly braces, or you can say you can refer to it as whatever you want to, but they are called curly braces. And this is how the data structure looks like when you print it. Now, let's see what is the marks for the student whose name 1 is the name. So I just do this and it is iterable. So that confirms that it is iterable. Now I want to change the value or maybe, I just want to add the value of name 1 and, assign it a value of 75. Now, considering that it already has a name 1, let's see what it does. So I am printing the value of the student with name 1, and it says that it is 75 now, and I'm printing all the student names present in the particular dictionary with the help of the function keys, which returns all the indexes or keys in this particular case, and it says that it has all the values over your name 1, name 2, and name 3. You see that there are no two name 1s here. So you have only name 1 as name 1 here. There's only one name 1 here. And the last thing is you print all the student marks, which I'm using which I'm obtaining by using the function dot values, and that returns you 75, 80, and 90. So initially name 1 had 70, and that got updated to 75. So it is mutable, but it does override the value. So you cannot have two keys with different values, or you cannot have two keys with the same name. That's what it basically means. So you can have two keys with two different values. So like name 1 has a different value, name 2 has a different value. You can even have the same values, like name 1 can score 70, name 2 can also score 70, but you cannot have name 170 and name 180. So that's kind of illogical also at the same time. But yeah, so that does the basic understanding of dictionaries. Let's look at the list thing, like all the items present in the list. Let's see. So I'm listing out the entire list here, and I'm using the items function to do the same. Now, why am I doing this? Or what, in that case, if it's doing the same thing, why do I have a different function that does this? Let's look at it in a experimental way. So I'm doing an intentional error here, which I've mentioned. So it basically says that I cannot have key and value, and then I'm doing in math students here. And what it basically says that there are too many values to unpack, expected to. So what this particular error means is, if you want to see here, if you just count the number of commas, I think that will help you out. So you have one comma here, you have one comma here, which basically segregates or segments this particular section to this particular section to this particular section. So you have three sections here, right? And you're passing it to, you're passing it to different value variables to store the value in, which the computer is not able to understand. That's what unpack means. You have a name and the particular marks assigned to it, but Python doesn't know how to go ahead and unpack it, or split it into key and values. That's where the items come into play. So when you say student.items, you see that there are two things here. So you have name 1 comma, and then you have 75. That makes it one value here, one value here. Then you have the second big value, which has sub values of this name 2 and 80, and the same goes for name 3 and 9. Now when I run this, I get the values correctly. Like I have name 1 75, name 2 80, and that's exactly what I wanted, right? So that's how the function items is used and is important. Just because it returns the same print value doesn't mean it kind of has the same impact. You see that this is a dictionary output and this is a list output. A list can be unpacked. A dictionary in Python cannot be unpacked in a default way, like just using the in function. You need to use in the dictionary variable name and dot items so that it can unpack the values to key and values and assign them accordingly. So we have a question here which says that you need to return the name of the students with marks greater than 75. So we didn't test it out initially, but just let's just have a look at it. So when I say that I want to have the value for name 1, it gives me the value 75. So that works. But what if I want the key value for for the person who scored 75? When I press enter, it doesn't
provide me with anything because there is no key value with value 75. So how do I go about getting the name one? So you cannot actually go ahead and use the values and try to access the key names, but there's a different approach to it. Now, the question over here kind of does the thing, kind of specifies on that problem. So I unpack it in the same way as I did here. And I basically say if value is greater than 75, then print key. It's as simple as that. So any value that is greater than 75 and those values are 80 and 90, I just want the subsequent key values for those particular conditions, and that does the job. So with that, I think you have a basic understanding of Python in general and the data structures also. Now, these are very, very important, and there's a particular site called HackerRank, which I'm going to provide you the link in the PPT in general, but I'll also add in the link here so that you can go ahead and access that. You need to make an account there and you can practice all the Python codes there, which helps you understand firstly the language better, makes you code better, and you can also see the various solutions that people came up with. So I didn't knew about this particular solution of patterns that we discussed earlier in the for loops, not in this particular code, but we discussed the pattern question in the earlier particular notebook, and I didn't know how to. I actually didn't know you could actually multiply I and get the particular structure. So that's a new thing that I learned on HackerRank way back, like a couple of years back. But yeah, I did learn it from there. So you could also go ahead and try it out, and you'll see that there are a lot of things that you're going to learn, new things that you can implement even in machine learning and the other things that we're going to learn that we're going to learn after this. So that would be it.
So in this video, we are going to learn about something called NumPy. So what is NumPy? NumPy is a fundamental package for scientific computations in Python. It is a Python library that provides a multi-dimensional array object, various derived objects such as masked arrays and matrices, and an assorted routine for fast operations in arrays, including mathematical, logical, shape manipulation, sorting, selecting, IO stands for input output operations. Then there is a discrete Fourier transform that is used in audio analytics, just for reference. And then we have basic linear algebra, basic statistical operations, random simulations, and many more things. So what does NumPy stand for? So NumPy stands for numerical Python. Basically, as the name states, it is basically used for numerical computations. And the array structures, when the array structure is computed or generated through the NumPy library, they are iterable and mutable, just like lists, but something is different. So the fourth point highlights that it can only have homogeneous data in it. That is, all the elements have to be of the same data type. So in list, we used to have, say, a string and a decimal and an integer all in the same list, but somehow NumPy doesn't, accept that, and it automatically converts it to the higher order of the data type. We are going to look into the example, so don't worry about it. So beyond this, when we discuss why arrays are why NumPy arrays over list and tuples. So why do we use NumPy arrays over list and tuples? Basically, there will be some terminologies that you may not understand now, but just keep them in the mind, make a note of it, and when we progress through this video, you will understand what those things mean. So firstly, vectorization. So vectorization describes the absence of an explicit looping, indexing, etc. So those functions, you don't need to do that. It obviously happens at the back end, but you don't need to specifically code that in. You're going to look an example of this as well. Just make a note of it. And it is faster than list or tuples. We are going to check this out as well. It is convenient for a lot of tasks for numerous dimensions. So when the number of dimensions increase, it is easier to use a NumPy array over the other data structures. We are going to test this out as well. We are going to talk about dimensions in detail. So if you're not able to understand the points right now, don't worry. We're going to look into them. And it consumes less memory, so that is an added advantage. And this is the official NumPy documentation that you guys should look out. And I would recommend you to look this up after you complete this entire video so that you get the reference of what they are saying. At the moment, if you go on to read it without going through the entire video, it might look something very, very new and absurd. So just for reference, again, let's look at how do we go on to install the particular library. So if you have downloaded Anaconda, went through the steps as we discussed before, you do not need to do this because you do have NumPy already installed on your particular Anaconda environment. But just for reference, just to check it out, even I have it, but let's just check it out. What does this code say? So I'm running this now and it is executing. It might take a while or two, but it's basically going to say that you already have the NumPy. Yeah, so basically it says that requirement already satisfied. NumPy is in this particular location. So basically it says that it's already installed, so you don't need to reinstall it. It also gives you the version, and that's it. So if you already have it, it's going to show you a statement like this. But if you do not have it, it's going to show you a statement something like it's going to install it one by one and then going to say successfully installed. That's the only difference, nothing to worry about. And this is how we import a particular library. So we basically say, okay, I'll just remove this for easier readability. Yeah. So we're basically going to say import. We use this particular keyword. Again, it's a reserved word. That's why it's highlighted this way. Then we write the name of the library that we want to import, that is NumPy. And as is a keyword that helps you make an alias for the very same package. So writing is, so basically we have a function called array for NumPys, which helps us create arrays. So instead of writing NumPy all the time and dot array all the time, what we do is, just for simplicity and for just to make the things easier for us, we just write np.array, which does the same thing. So it's more of like referring to this particular package with this particular name, nothing else. It's as simple as that. Now np is the generally accepted abbreviation or alias for NumPy, but you can always give another names. You can even write you can always write ABC, and that should work fine as well. But it's generally accepted, and you should keep it this way so that when you upload your code somewhere and someone else is going through your code, he or she understands, okay, so basically you're using a NumPy array without scrolling up all the way and to see which particular library is abbreviated as ABC or any other abbreviation that you're giving. So I just like to give a print statement at the end saying that all the packages have been successfully installed. If there is any error, say I just write U and then I and then I run, it's basically going to give me an error that U is not defined and it's not going to print this particular statement. So if there is any package or any fault in the middle, it's going to give me an error, or it's just going to say this, making the user understand that all the packages have been successfully installed. Now let's look into the arrays and how we can create arrays from lists. So now onwards, when I refer to 1D, 2D, 3D, so these basically mean 1 dimension, 2 dimension, and 3 dimensions. So D stands for dimension, just for future references. So we have a list that says 1, 2, 3, 4, 5, and this is our list variable. We print the list. We print the type of the particular variable, and it gives us lists. And then we print what is there in the list, and it prints out the entire list here. Now, when we go on to convert this particular list into an array, we use the function array, np.array, as discussed earlier, and we just pass in the list variable. You can also write it somewhat like this, and it gives you the same output. Basically, you're passing the list as a reference. You can also write it this way. It works the same way. And you see that the type is a numpy.nd array, and it's not a list, just because we use this function and we typecasted it to a array data type. Sorry, data structure. And so that this is how a 1D array looks like. It's almost similar to a list, but it doesn't have the commas, but you use the same square brackets for it. Now let's look into creating a 1D array from a tuple. So you have the same thing over here. You making a tuple, you're printing the type of the tuple, and then you're printing the tuple values. And you use the same function over here. You use np.array and the tuple variable. You can just give in the values like this. It should run fine. It's basically the same thing as we discussed earlier. Instead of a list, we just have a tuple now. So you see a tuple and the tuple values. You see that the data structure is now in the array and the values are such. So this is how you create a 1D array from a list or a tuple. For general purposes, we generally use lists and we don't use tuples. There is no so hard and fast rule, but it's generally the thing that we go on to use, nothing specific again. So now remember, we use this term homogeneous data, and I said that we're going to get back to it later. Now this is where we get back to. So you see that the list over here has integers and it has decimals as well. So when I print the type of the list, list var, it obviously gives me the type list, and I go on to say, okay, so list var, could you print the values of list var? So it prints out the entire thing. So you see that 1 is an integer, 2 is an integer, 3 is an integer, 4 is an integer, 5.5 is a decimal value and it prints the same way, 6.0 is a decimal value and it prints the same way. But when I convert it to an array here and print the type, it gives me an ND array as you know, as expected. But when I print the array here, you see that the values have changed now. So 1.0 is not written, but it basically is assumed that it is 1.0, 2.0, 3.0. So each and every value that was an integer is now converted to a decimal. So that's exactly what NumPy array does to your data. So if you have integers and if you have float values, it basically converts everything to the float because it has a higher order. Now let's see what it does when you have character types in your data. So you see that you have string data type. So you have string data type and you have an extra. So it was the same list. I've just added in an extra character E here. And you see that the list doesn't change. But when I convert the same list to an array and print out the type and the values, you see that the entire thing is now changed to an array and all the values here are basically string. So strings or characters are basically referred to or printed as single quotes and the value. So you see that this is how an integer looks like, and this is how a string or a char type character looks like. So that's how we create one-dimensional arrays in NumPy. Now let's understand dimensions in general. So dimensions in array look something like this. So we have another function called shape, and we're going to look into how shape works and how do we interpret it. But to have a brief example of the same, let's just take this as an example. So we have a 1D array which looks like this. As we saw earlier, we have 7, 2, 9, 10 in a single row. There's only one axis. But when we have a two-dimensional array, it's more of like there are two rows, or you can say there is an axis which runs like this horizontally, and there's an axis that runs vertically. And the shape over here is 2, 3. So here we have 4, 0 saying that there is no axis, there is just a single axis, and there are 4 elements. You will just see that the shape over here is 2, 3, saying that it has 2 rows and 3 columns. And over here, it says that it's a 4, 3 matrix, but there are two such matrices, making it a cube or a cuboid-like structure as represented here. So that's how 3D arrays look like, but NumPy doesn't print it that way. This is just a visual demonstration of it. We'll look into how 3D arrays and 2D arrays look. So, but this is how they generally are interpreted as. So let's look at 2D arrays, and basically there are multiple 1D array that will make it 2D array. Let's just print it and see. So you see that this is one array and this is the second array. Okay, and that's how a 2D array looks like. Let's see how a 3D array looks like. Let's print this. So you see that this is one 2D array, and that's how this is one 2D array, and this is another 2D array as we saw here. So we have this particular block as a 2D array, and the other second one behind it another 2D array, which makes it a 3D array. So that's how a 3D array is represented, and this is how a 2D array is represented. So how is NumPy better? So add each list element. So we'll look into it via this example, obviously. Element index to index and create a new list. So we need to add it index by index. Okay, so that's what the question means. So we are making the same list over here, and we have another variable called sum_list, and we're just looking at which is the shorter one. Sorry, it won't be the longest one. It will be the shorter one. Shorter way. So we just are looking for the shorter length over here, and we go on to calculate the min length using the min function. So we calculate the length using the length function for both the lists. Look out for the min one, and I'm going to explain why. And we go on to iterate through the entire thing, and we add it. We add it to the sum list after adding each and every variable of the ith location. This is the basic for loop, and then we print the sum list. Let's just see how it works. So you see 6 plus 1 is 7, 7 plus 2 is 9, 8 plus 3 is 11, and so on. That's how it goes on. But how did it exactly work? And why did I take the smaller length? So let's say that if I have a greater value here, say 9, and then I press enter, it kind of doesn't do anything, and it considers, okay, I'm just going to read till here instead of reading 9 as well. But when I do something like this, it basically has another value here. And now why am I doing that? It's because if you do not do it that way, if I just say, if I consider this to be my length 1 and I'm just running it till here, it's going to throw me an error saying that array index out of range. So when it basically finds that there is no particular value to add into, or there is no particular index to iterate for this particular list, because I'm doing list 1 of I, which is able to find 9, but when I do list 2 of the which is this is the 5th location, and when I say what is it add it to the 5th location of list 2, it basically finds nothing, and it says that array index out of range. So that's the reason you need to have the min length and go on to work about it this way. But there's an optimal way of doing it as always, and we need to look into that. So this entire thing remains the same, but we go on to do list, and then we use a function called map, and then we use a function called lambda as well. Now this is too much to grasp all at once, but we're going to break it one by one and then understand what is happening. So we obviously understand what the list function is doing. It's basically creating a list of this entire thing, obviously. But what is the map function doing? But let's understand what does the map function take in as argument. So it basically takes in a function and an iterables, if I have to put it that. So it's basically saying that you need to take in a function and you need to have an iterable statement here which you need to map to this particular function that you're providing here. So this is a function that, so this is an easier way of understanding the same thing. So instead of having def and then writing sum and then passing it to values x and y and then doing x plus y and then return s, say if I'm printing s is equal to yeah, and then I return s and then go on to do this entire thing, it's going to be time consuming, right? Instead of having 3 lines of statements, I can just have it in one. That makes the job really, really easy. And even though the function does the addition, it doesn't do the addition of list index by index. For that, you need to have a separate function. By this, what I'm saying is lambda is a function and I have 2 values, x and y. What I need to do with these 2 values is I need to add them. Where do I get these values from? I get these values from list 1 and list 2, and they are going to just have, they're going to take in 1 values from each. So when I pass in list 1 and list 2, basically is going to take 1, 6, add it, send it, map it to the list, add it to the list. And that's how it's going to go about. Let's see how it works. Oh, it works the same. It's obviously it's going to work the same way, but let's see what it does when I throw an error. Okay, it still works considering that it stops here and it doesn't go forward saying that, okay, I did not find a value in list 2, so I'm not going to print anything and map anything to the function because there is nothing to return from the function. So lambda is a way where you can make small functions, but remember that you need to use it specifically only when you have these single line functions instead of having a separate function for multiplication or addition or say some basic functions similar to this. You can use lambda, but definitely go on to modularize your code because this is when you want to use this particular function just once here. So if I want to have the same function in the next line, I cannot use this. I need to write this entire statement again. So it's a function, but doesn't have the advantage of a function as we discussed. So the function has an advantage of recycling the code. I won't say recycling, reusing would be a better term. So we can reuse it over and over again, infinite number of times, as many times as we want to in different places. We just need to have it in the memory by running it once. So Lambda doesn't do that. It's for simple tasks like such as illustrated here. So getting that out of the way is just an optimal way of looking at the same. Now NumPy takes it a step even further. So remember the term vectorized where I spoke about how you do not, so basically it's going to iterate list 1 and list 2 and add in the values as it should, but we don't need to worry about that. Like over here we needed to have a different map function, a different lambda function, and then the entire thing goes into a list function and then you're going to print the list. Instead of that, we just have 2 arrays and we use the plus operator and we have a sum list and it gives us the same value. And even if we have say a if we have arrays with different lengths, it gives us a dimension error saying that it's not going to work this way because it has different dimensions. So you cannot go on to optimize that, but this is what it does. And you need to either run it the same way where you say that, okay, I need to run it till the length that is lower than that. But what I wanted to illustrate through this particular code is that you can just have a single plus operator to achieve whatever this particular code is doing or whatever I'm doing in this particular loop. So you see that how easy it is where the Python NumPy library is doing the iteration and indexing for you. And you just need to worry about the logic of the code that you're working on and not the unnecessary logic of how the indexing is working on how am I going to iterate it through. So that's the added advantage, and that's what vectorization means when I was speaking about it earlier. And let's see the condition to check. So when I say array 1 and array 1 is greater than equal to 3, so let's see what was array 1. Let's just print this and see what it prints. So basically what I'm saying is this is my array 1 and it has 1, 2, 3, 4, 5 and I'm saying is array 1 greater than or equal to 3. Now this is going to create another array and it's going to create an array of Boolean values where each and every value which is greater than or equal to 3 is going to be true as represented here. So you can see that 3, 4 and 5 is represented as true and 1 and 2 is represented as false. So that's one aspect of it. Let's just look at, so this is quite, no, I won't say annoying, but it's quite ambiguous because I need to go, okay, so the last three values. So what was NumPy array 1? Okay, so what is the last three values? It's quite difficult to, go on checking up and down. So what I do is I take this particular array and send it as an index to my array 1, the initial array 1. So what it's going to do is it's going to see what are the values that were true and it's going to print them out. So it's easier for you to view them. We are going to, there is a lot of applications for these things. It might look, okay, it's very, very simple, but there are a lot of applications where you should be using this and it makes the work really, really easy. So simplifying the above code, instead of writing 3 lines of code, you can just do something like this and it does the job for you. Anything that is greater than 2, you can just print that and have the same output. So that's an easier way of looking at it. Instead of having a different condition, making a Boolean type array and then passing it to the index that will print you the values that are greater or satisfy that particular condition. You can just put in the condition here inside the brackets and it's going to provide you with the values. So operations on higher levels. So higher levels, what I mean by higher levels is higher dimensions. So we have the first array, we have the second array, we are printing it out here. And when I say print final array, I am basically subtracting array 2 from array 1 and I get the output as a full array of 2 dimensions of values 10. It makes sense, right? We have 11 minus 1, that is 10, 12 minus 2, that is 10, and so on. So if you have done a bit of math, you would have realized that this is more of an matrix subtraction where each and every value is subtracted. So this is if you consider this to be a matrix and this to be a matrix, it basically is doing a matrix subtraction and it's giving you the value. So let's look at the functions now. So we have the array function and we have the arrange function, and I'm just this is a complex nested function okay, so I need an array but I need to pass in a list to the array, so I'll have the list function, and I need a range of values ranging from 1 to 15 with an increment of 2, so I need to give a range function to it. The range function will give me the values. I need to typecast it to list. The list is then again typecasted to an array. Now this is the complex function which can easily be taken care by this particular function called arrange, which basically takes the starting index, the ending index, and the iteration value. So you can even for easier, or if you just want to remember it better, you can just remember it as a range, which will basically refer to as a range, and stands for array, so array ranges, something like that. But you see that it does the same thing for you. So I just illustrated it in 2 different ways. And we have the arrange function again, but for decremental factor. So instead of having an incremental factor here, it also works for a decremental factor, just representing that. Now, sometimes you need arrays with just zeros in them. So you see that I need an array of just zeros for 1 dimension. So I have a 1 dimension array and I'm saying that I need an array of just zeros. So 0 array 1D is the name of the variable and np.zeros is the function. So zeros is the function and I'm passing it 5. So when I pass it the value 5, it basically means that I need an array which contains 0 and has 5 elements in it. So you can see that it does the job pretty well here. Then I go on to print the array with 2 dimensions in it. So I am just naming it in a different way for easier understanding. I have np.0 and I'm passing it 5,5 inside a tuple. Okay, so let's just understand this for the time being. You can see that I'm passing it inside a tuple. You can also pass it in a list if I'm not wrong, and it does the same thing. Yeah, it does the same thing. But why am I doing this? Let's see what happens if I just do this. It throws me in and cannot interpret 5. So it's basically saying that I cannot interpret this 5. I could interpret this 5 obviously, but what is this comma 5 here? I don't understand that. So that's why you need to have it within the square brackets or the rounded brackets for that matter. And when you press enter, you see that you get a array of 5 cross 5 with all zeros. Now initially I had something over here as a D type. So you see by default the D type is float, but when I specify the D type as int, it basically creates a 2-dimensional array as specified by the shape here, and it converts the entire data type into an int. Even though float has a higher order, I am specifying that I want an array of the int data type, and it's going to give me that. So there's another function called ones, which also does the same thing. And just because the parameters are same, I'm not going to explain this over. It's just the same thing with just the different types, and I'm having the same data type here. So that does the same job. So after seeing these functions, the first thing that should have come across your mind would be, so do we have functions for all the numbers? Like, do we have a function called 2s and then 3s and 4s and all that? So basically, no. These are specifically given for various computations where you need a complete matrix of zeros or a complete matrix of ones. But if you need a complete matrix of say 2 or 3 or 4, there's a function called full, which basically again means you need a full array of the value that you provided. So I'm providing it the value a shape of 5, and I want it to fill in values of 5. So if you see that over here we were filling it the values of zeros and ones by default because the function said so. Just consider this to be another function which takes in the shape as it did here, and it also takes in the value that you want to fill it. So fill value is the parameter for that, and this is what it prints. So this is a 1D array because the shape is of a single dimension, and I asked it to fill values of 5, so it's doing that. Then the second example, you see that it's filling in the values of 3, and I'm providing it a shape also of greater than 1, that is 5, 5, that is a 2-dimension array. So you see that it's 5 cross 5, 5 cross 5 here. Yeah, it's 5 cross 5. And I'm asking it to fill values of 3. It is doing that. So instead of having redundant functions like 2, 3, 4, 5, and on and on, we can have, we just have a function called full, and it does the job for us. Now, sometimes you need random values, and random does it for you. So there's a random module, and you're using the random function of the random module inside it. And basically what you're saying is I need a array of shape 3, 3, and basically it's going to provide you an array of 3, 3 as expected. But if you go on to see the values, they are not greater than 1, and they're obviously not 0. Okay, so basically your random function generates values between 0 and 1 as demonstrated here. And that's how you go about creating random generated values from this particular function. So let's see what does it do when I print it again. So we have 0.99 something, 0.58 something, 0.90 something in the first. So let's see if I run it again. Okay, so the values changed
quite a bit. So I had 0.90 something here and a 0.99 here, it changed to 96 and so on. If I run it again, it's going to change again because it's randomly generating values as and when I run it. So it's fine and it's obviously what we require, but sometimes we need to generate the random value and fix it as well. Because say you have a random generated matrix and you're making interpretations about it and you're writing the inferences, and when you close it down and you open it the next day and you run the entire thing, you see that the entire matrix has changed and the inferences that you have made out of it is completely absurd. So how do we do that? So basically we use a function called seed for it, and we'll look at it how it works. So now we have another function called randit as well. We are going to look at both of them together. So we had random here, which created random values in uh, float data type. Randint creates integer type random values. So I'm giving it a range of 1 to 15. I need 10. I need 10 values, and the data type should be int. Okay. So when I do that, it's going to print this. Let's see if I remove the data type int, what does it do? Just comment this out. It still does the same thing because this is what randint does. You don't have to specify it, but again, it's just for the explanation, nothing else. So you see that it does the same thing. I remove the integer type in here and it gives you the same thing. But I ran it 3 times and I'm running it again just for your convenience. It was 40, it's 41 now. And you see that the value haven't changed. If you did not observe, I'll just run it once again. You see that the value is 914, 9 here, it's 212, 6 here. I'm running it again and it remains the same. Now it generated values randomly, right? So how is it keeping it fixed? It's because of the seed constraint. So basically for this particular seed value is going to generate this numbers only. So it is random, but it is fixed to the seed here. It might sound a bit confusing, but let's see what it does for a different seed value. So just remember, okay, I'll just copy it here and paste it in a different. So for seed 2, it gave me values as such, and I'm going to comment this entire thing out. Let's make it to seed 21 and run it again. So the values changed obviously because of the random function, but if I run it again, it's going to remain the same. So it does satisfy the point that I did make earlier, that the random values are generated obviously, but they are constant to the seed value passed here. So now going back to the seed value 2, let's see what it does. So the seed value here was 9, 14, 9, 7, and it's the same here. It was 2, 12, 6, 11, 5, 13, and it's the same here. So that's exactly what I wanted to prove, and I did that. So seed values are important when you need to have the random numbers generated, but to be constant across and to make inferences better out of it. So that's one part of it. Now coming to the next function, which is important because it's used quite highly. So you see that we have identity matrix. If you do not understand what is an identity matrix, it's as represented here. You see that all the values are 0 instead of the diagonals. They are all filled in with ones, and it's only the diagonal that runs from the left to the right side, from top to bottom. It's just going to be that. So even if I have say an identity matrix of order 5, it's going to give me the same thing. Now generally an identity matrix is a square matrix, but if you want it to be of a different order, I'm sorry, I'll just see what the shape is. Yeah, sorry, it has n and m. So I pass m as 5 and n as 3. Generally, as we saw the documentation, so n is an integer value that tells me the number of rows. M is again an integer value which tells me the number of columns, but by default it is n, which does satisfy the point that we made earlier, or we understood earlier, that it is a square matrix. So when n is equal to m, the value will always be of the same shape across. So just that, but you see that it's still the same diagonal which has values with 1 and the remaining values stay 0. But this is just for reference, but generally we are going to have a square matrix with the diagonals as 1. But this is important. I mentioned it as important, so keep that in mind. Now we use something called as linspace, which is again a really important thing. Now we use linspace when the range and the size of the output is known, but the step size is not known. So we see that we have the range values here, and we do not have the step size. So what do I mean by the step size? So earlier we were making arrays mentioning that, okay, I want to start off from 0. So I have 0, and I want to end at 10. So I have 10. And then I want to increment it or have a step size of 2 or 3. So it's going to give me every second value or every third value within that particular range. But we use linspace when we know the range, considering that I know where it starts and where it ends, and we know the number of values that we need to have from that particular range. We do not know the step size. So the step size is generated automatically. So over here, I'm basically saying that I need a range of 1 to 40, and the number of values that I want in an array is 5. So it's going to give me this particular output as shown here. So let's see what it does when I have 4 as the third parameter. So you see the difference now changed to 13, correct? So 1 plus 13 is 14, 13 plus 14 is 27, 27 plus 13 is 40. So it automatically understands, it automatically takes in or makes the particular step size. You don't need to specify it. That's again an important point that you need to understand. Now we go on to use the reshape function. But before that, I would just like to show you the shape function to understand that. So I have, I'm just storing it to an array 1, and I'm doing array1 dot shape. And it's going to show me 4, 0, which basically means that there's only one axis with 4 elements in it. And print it for future reference. Here are 1. Yeah. So that does the job, and it does have 4 elements in it. So that's understandable. Now, what if I want to have, okay, I'll just do it 6. And so this is what my original array looked like. And I'm doing the same thing here. You see that it's the same function here with the same data type and everything remains same. But there's this reshape function that we have. So I'm reshaping it to 2, 3. So now what I'm saying is I want 2 rows and 3 columns. So what it does is it considers the first 3 values and says that, okay, this is the first row, considers the second 3 values, and okay, says this is the second row, and it makes the 2-dimension array. Now, what if I reduce it by 1 and see that if it doesn't make a complete, so basically when I say 5, you won't have a particular value, say you won't have the last value. It's going to be something like this. Now, it doesn't work out, but let's see what does the error show. So you cannot reshape array of size 5 into 2, 3. So basically, when you are specifying a shape, just multiply it, say 3 into 2, and it's basically going to give you 6. And you should have 6 values to reshape it into that particular shape of an array or dimensions of an array. So that was just the explanation and the error that is thrown by mistake. So you need to keep that in mind. So there's a sequence as well where you have, if you want a particular sequence of array to be repeated, and that's what it does. So what I'm saying is this is my sequence. So this is my sequence that I want to be repeated twice. And I'm printing that here. So that gives me a 1D array. So you see that 1, 2, 3 is repeated twice. Correct. Now over here, I'm specifying the same thing. I am asking this sequence to be repeated 3 comma 3 times. So this is not a matrix of 3 comma 3. People use, I usually used to get confused that okay, it's saying that I need a sequence of 1 2 3 and I need 3 columns and 3 rows. So basically my output should look something like 1 comma 2 comma 3, 1 1 2 and 3 and 1 2 and 3, which is completely wrong because this is the tile function. Okay, now tile function takes in the number of repetitions in the row and the number of repetitions in the column. So that's what is different here. So you need to keep that in mind. And you see that 1 2 3 is repeated thrice in each row, and it has been, the entire thing has been repeated thrice, which satisfies this particular condition. Now we have a question where we are generating two arrays as shown below and then adding them together and to create a new array. So you see that I have an array over here and it's 2 4 6 8, and so instead of creating it manually, I use the tile function as we just discussed, and it gives me the particular array as represented here. And then we have the np arrange thing, which says that okay, so everything is at a step size of 2 and it's ranging from 2 to 18. So basically I need anything that is below 19, so I specify that, I specify the step size, I also reshape it, and let's see what it does. So it does make the first array as given in the question. It does make the second array as given in the question. And just by using the plus operator, I get the, some version of the both arrays. So that was a pretty easy question. Now I have a second question for you guys as homework. As always, you will find the code for the same in the PPT, but I would generally want you to try this out. So it's an easy thing. Just do not copy paste this particular array in your code. I would want you to use the functions to generate this particular array instead of just copy pasting it. And if you just go scroll up and try to figure out how do you create these, you will definitely find it out. Now we are done with the major functions, but again, as I mentioned, there are a lot of functions, and going through each and every one of them is a difficult task. So always do read and refer the original documentation, which I've linked at the top of this particular Python notebook, which gives you an understanding of which function goes where and when do we use what, and what are the combinations that you can do to have a better understanding. So let's look at the structure now. So I'm using the same tile function to create this particular array, and it's of type, I wanted to know what is the data type of this particular array, and it says that it's in 32. I'm like, okay, cool. And then we are seeing the data shape, which says that it's 3 comma 3. Okay, so now I'll just print the array as well for easier understanding. You see, and the function as well, so that it's separated. Yeah, so I have this particular array. You can see that the shape is 3 comma 3. That's what it's showing here. And then I have the number of dimensions. Okay, the number of dimensions 2 because it's 3 cross 3, and you can see that it has the 0 axis and the 1 axis, so that understands. So these are the few functions. So ndim is the function that gives you the number of dimensions, and these are the few functions that come in handy when you want to just observe or understand what the structure of the array is. Let's look at indexing, subsetting, and slicing. Sorry for the errors. I just want to have, yeah, I want to index. I want to see how you index the particular array, how you subset it, and how do you slice it. So I want to understand or want to get what is the first row of this particular array 1. So it's 1 2 3. Okay, that's cool. Now I don't want that. Let's see what it does for the 0th element. I want the 0th element for in the first row. So you see that the first row is 1 2 3. Okay, let's just print this as well.
So you see that the first row is 1, 2, 3, and the 0th element is 1. So that's what I'm getting here. And this is how you do it. Now there's other way of doing it as well, where you specify it with a comma, and that also does the job. And I want the first 2 elements to be printed. And let's see, how do you do that? Sorry. You see that it's 1 and 2. I want the first row and the first 2 elements. So anything that is less than 2, so 0 and 1 will give you the first 2 elements. Now let's see, how do you reverse the particular first row? So I get the first row with comma 1. I'm saying that I want everything and I want to reverse it. When I say -1, it basically reverses the entire thing. So these are the few basic things. Let's look at the homework question here, where you need to print the 0th row again. So the 0th row is, yeah, I printed the first row for this particular case. It should be the same because I've created the array with tie. But you need to have a different index, so you need to look into that. Now print the 0th value of the 0th row and print the last 2 values of the 0th row again, and then print the reverse of the last row. This is the first row, you need to have the last. So this is the second row. Yeah, need to have the reverse of the last row. And this is the array. If you want to use the tile function, you can always use it. But for this particular homework and this particular homework only, because I'm testing you on these questions and not your knowledge about the tile function, you can copy paste this particular array, make a new array, and then work on these particular functions only. Now we look into the testing. So basically, earlier I said that it is faster. It is faster than using a general list. So here it's just another module, and this is another module in the Python basic modules, like it's a pre-built module that we have. It's called time. It basically starts the timer and it stops the timer, and you can uh, it doesn't do that. Basically, it just gives you the time. We can use it in a different way and check out what the time was for the computation. So here I'm performing a general list. I'm creating a list, and again, it might be new to you, but it's basically a for statement where I'm saying that I want to add in all the values of I. And what is my I? My I is in range of 0 to, I think it's 200,000. Yeah, it's 200,000. And this is in the range of 0 to 200,000, and I want each value. So now my length should be 200,000. So my list 1 is of length 200,000. My list 2 is of length 200,000. And my J, basically I'm raising it to the power of 2. So 1 raised to the power of 2 is 1, 2 raised to the power of 4. 2 raised to the power of 2 is 4. And that's how it goes about. So now you have 2 lists of length 200,000. I'm starting the clock here. I'm doing a list multiplication function using the same list lambda function here. Instead of just an addition, now I have a multiplication. I'm passing in the list 1 and list 2. I'm stopping. I'm taking in the time right now, storing it to a variable. Now the total time consumed should be the end time that I'm storing in this particular variable subtracted from the start time. Let's see what it does. Okay, sorry, I forgot to run this particular module. Yeah, so it says that, okay, it took you 0.02 seconds to run and compute this entire code. Now let's look at the same for arrays. So it's the same 2 lists which I'm passing to an array, creating array from the list that I created earlier. And I'm starting the clock here again, doing a multiplication. We do not need to write such a big code for multiplying it. We vectorized, NumPy vectorized the code for us. So we just need to use a multiplication function and it does the job for us. And we end the timer here, like taking the end time and store it to this particular variable. And we do the same end time minus the start time. And let's see what it does. So you see that it took 0.00009 seconds. So it's almost, I don't know, it's really, really small compared to this.
So let's see how small is it. I'll just take this particular thing. Name it as list time. Take this particular thing. Sorry. Name it as array time here. Now I want to print the difference between them. So basically, because array time is smaller, observingly, I just take in the list time and subtract the array time to it to understand how fast was it. And it says that it was 0.0279 seconds faster than the list time. So that's how we understand that NumPy array is faster, and we explored the basic functionalities of NumPy array, but there are a lot more, and I would really recommend you to go through the documentation and understand what are the various functions and how do you use them, try it out. And yeah, that was all for NumPy array.
So in this video, we are going to look into another library called Pandas, and let's see what does the documentation definition has to say about it. So Pandas is an open source BSD license library providing high performance, easy to use data structures and data analysis tools for the Python programming language. Okay, that's the basic definition, that it is data, it uses data structure and data analysis tool for Python programming language. It's a basic library. So what are the major application areas? So it's data manipulation and data visualization, and this is a documentation link obviously, but there are two main data structures that Pandas takes in. One is the data frame and the series. So we're going to look into each of them, but before that, let's just go on to run each and every cell and go on to install Pandas library. Now, if you have downloaded Anaconda and you're using the Anaconda's Jupyter notebook, this is not required because you should be pre-installed with the particular library. But just in case you have downloaded Jupyter separately, you need to have this particular file here. So you just press Control Enter to run this particular cell, like always, and it's going to take a bit of time. So, and it says that the requirement is already satisfied. These are the locations and so on. So just in case if you did not have this particular file, it would have downloaded the entire thing and said that you successfully installed. So that is the first step. Second, we're going to import the pandas library. It's done the same way. Like instead of having numpy as np, we have pandas as pd. Again, you can have any string over here representing this particular library, but pd is the general norm that goes around. So I would recommend you guys to use the same. Now let's talk about the data structure called series, as we discussed over here. So what is series and how does it look and how do we create and work about it? Let's see. So we have the same name, Luther here, and we are basically trying to make a series from a tuple. So I have a character series here. I'm doing pd.series and I'm passing the tuple inside. Let's see what does this particular cell do. Okay, sorry, I forgot to run this particular cell. Rerunning that, yeah. So you see that it doesn't come as an array-like structure, it comes in a column-like format. So the indexes by default start from 0. Now we'll look into how we work about indexes in the upcoming cells, but just remember that by default it starts from 0 and the last index is length -1 as always.
And the object, the D type is object, basically signifying that it's a string data type, but that's the data type, and the type of this particular variable is pandas.code.series.series, like it's a series data type. That's what a series data structure. So that's what I wanted to differentiate here. So the data type of this particular series is object, and the data structure for this particular variable is series. So that's what a few things that you need to keep in mind while you're working with this. And let's look into creating the series from a list. It's done the same way. You see that the series is created the same way. You have the same values here. Instead of just a tuple, or instead of round brackets, you have square brackets here. The entire thing remains the same. The key difference is that it's an integer series now, and I'm not specifying integer anyways. I'm just entering the integer values, and it automatically takes in the integer value. It doesn't change anything. It says that it's in 64. 64 basically is the bit reading size, byte or bit reading size that your computer has. Mine is 64, so it's saying in 64. And there you can change it to in 32 as well. It doesn't make a lot of difference, but yeah, so by default it's in 64 for this particular series. Now again, the data type for this particular series is int, but the structure that we are looking over here is called a series. So that's how you create a series from list and tuples. Now creating a data series from creating it by default, uh, you don't have a particular date thing. So NumPy did not have that. So Pandas does have it. So we go on to say, okay, I need a date series, and I do pd.date range. That's a function, and I say that the date starts from first. So we're going to see this is in the month, day, and year format. So basically, when I say 01, the initial 01, it basically says that it is January. Then you have 01, that is the day, and then you have 2020, that basically is the year. So that's what it is for these two parameters. And by default it's that, but you can obviously change it, work on it with different parameters. You can check on this and how you go about to do this. We looked into how we go about to read about various parameters and work out with it. I would let you guys explore that part. So seeing how the data series is, let's just print it out and have a look. So it comes out like this, and it says that it's a date time object. Now it's not just a series. It's from pandas core indexes, date time, and date time index. So it's a date time index thing. It says that the D type is also date time. So these are the few things that you need to keep in mind. What is D type, and what is the type function that gives you, what does that give you? You need to look into these things a bit carefully while you're working with them. You might get confused, but just remember that the type function that we use over here gives you the data structure. In this case, the data type and the data structure that we are looking into is the same, but generally, as we looked earlier, it can be different, or usually is different. So when you're working with series, you can work with various data types inside it. But in this case, when we have a datetime index format, the D type and the particular structure is in the datetime index format. So this is the datetime format, sorry, and this is the datetime index format. So you still have a discrepancy there. So just a few things, pointers to keep in mind while you go ahead. Coming to what all can we do with the date series, let's just have a look at it one by one. So all the years, so my date ranges from 2020 first month first day to 2020 first month fourth day. So I have a total of 4 days, and it ranges from the 1st of January to the 4th of January 2020. But if you see all the years are 2020 here, this is exactly what the function also returns. It's date series dot year. So this is the variable that I'm storing the particular value in, and when I say okay dot year should give me all the year values, and it's doing that. Just in case, say if I have a different year over here, and say I'm running the range from the 1st of January 2020 to the 1st of January 2021, at that point I'll have uh, a range of 366 to 7 values, and I'll have one of them will be 2021 because my last value is 2021. So that's one of the things that you should keep in mind. Looking into the second print statement, says all the months. So just because all the data in this particular date time index belongs to the first month, it's returning 1 for all the 4 values. But it's kind of difficult to understand, so not in our case, we are kind of smart people, but just in case we want to know the particular month that this particular index represents, you can use month underscore name for it, and it gives you the names for those particular months. It's just easier. Instead of coding it all together, you can just use the function. Now coming to the fourth print statement, which says all of the days. So which are the days that we are looking at? So you see that it ranges from 1 to 4th, and that's what we are getting here. It's the same thing. The function name is dot day, and let's see what does the next one do. All the day names. So what was the day on the 1st of January 2020? It was a Wednesday, and consecutively it was the next day was a Thursday, and then a Friday, and then a Saturday. So that's how it was. And let's see what the last print statement does for us. So which day of the year are they? So in this case, you're going to get a similar output because the values are kind of similar, but the output may be same as for both, but this signifies the day of that particular year. So if you say 31st of December 2020, it basically will tell you 366 because considering it's a leap year, and it's going to show you 366 here. But for this particular case where you're talking about the day that uh, belongs to the date time index, it's going to show you 31. So I hope you get the difference between these two, and I think the print statements are pretty well understood. The functions are also not that difficult to understand. They are pretty much self-explanatory. So we'll move ahead. So now we have indexing. So like all the others, we have indexing in this particular data structure as well. So considering a series, so this is an integer series with the same structure as we looked earlier. So we are looking into the 0th element in the series, and we do integer series square bracket 0, and that gives me the value 11, which is the 0th element here. Now the next print statement tells me I need the first 4 elements in the series. And how do I do that? I basically have square brackets 0 colon 4, which basically tells me to that basically says that all the indexes with value 0 and less than 4 need to be printed. So you see that the values from 0 to 3 are printed. Works. And then we have the first and the fourth element in the series. So you need to realize that this statement and this statement is different. So we have the first four element, and here I have the first and the fourth element. So okay, so basically the first element and the fourth element would be, yeah, I think it's working fine. Yeah, so basically we are going to do indexing something like this and pass in a list of the indexes that I want. So I want 0 and I want 4 because it's the fourth index and the first index. So 0 gives me 11, and that is the first index. And then I do 0, 1, 2, 3, and 4. So basically I should have written 3 here if I want the fourth index as such. So I get 14 here, which is the fourth element in the particular series. That's how you go about it. And let's see, how do we renaming the indexes. So basically, remember I told you that the default values for indexes start from 0 and it ranges up to length -1. So we can also name or restructure the indexes, and we do it in this way, where we have PD, we define the series as we discussed earlier, and then we have a hyperparameter called index, and we pass in the list. Now remember that the list over here, the length of the list in your indexes that you're passing should be equal to the actual series length, which is quite important. So that's how you do it, and let's run it and see what happens. So now when you see when we were accessing 11th, when we wanted the value 11, we basically said integer underscore series, and we mentioned 0. Now, even though it is the 0th element, well, technically now it is not because we re-index it. So now it's the 101st element, or it's basically uh, showing that 101 has the value 11. So if you want 11, you need to pass 101, not 0. So that's what we are doing here. And it shows that the first element is 11, which does the job. And it doesn't do any formatting to the values, just changes the indexes. So if you even do 103 over here and change this 103 to 102 over here, it basically goes on to replaces the value and go on to correlate them as you have entered. It doesn't change it. Okay, so 13 is bigger and it should go up or something like that. It doesn't change the values. Let's see what happens when we have two indexes with the same value. It should give me an error. Okay, it does not, but let's see what it does for 103. Okay, so basically we can have two similar indexes and it gives me two values. So 103 has 12, 103 also has 13. So that's how you can distinguish them. But it's kind of confusing, so we will keep it the way it was, and we have separate indexes for separate values, but you can have the same index for the same index for different values. Yeah. So a simple way to achieve the very same thing, instead of so in this particular case, we have say around about six values. Yeah, we have six values and we have six indexes. But in general cases, we basically have a lot of values. 20,000 is like considered to be small. So it's quite big, in that way when you go on to write each and every index. So the easier way to do is you have a range and you pass it and it does the same thing for you. It creates the same index. So that was about series.
Now, once we are done with series, we discussed that pandas has another structure called data frames. So data frames are more of like tables, but let's see how do they look. So how do you create a data frame? Now, data frame needs to have a header. So
that goes here and the values. So these are not the row values, these are the column values. We'll have a look at the output first and then I'm going to discuss how it would. So you see that the index again is starting from 0 and it goes up to 5. Sorry, it goes up to 4. The 5 being the total length, it's 1 lesser than that. And you see that the name has all the values that I've passed in here from students 1 to 5, and that's what comes here. You have the roll numbers starting from 1 going all the way to the 3. That's what's happening here. And same goes with the mathematics. So it is more of like a tabular structure, and this is one of the most used data structures for data science or data analyst or any kind of thing that requires data. You basically look it into a look in tabular form. It's just easier to visualize and go about and go ahead with it. So that's one of the added advantages. So how do we create it? We basically create a dictionary. Now the dictionary key values are the column headers, and the list values or the list that you're passing as the value for this particular key needs to be the column value. This is the list for the column and it's not the rows. Just need to remember that. So sometimes so if you see we have an index and we also have roll number. So indexes should be kept unique, because as we saw earlier, you can keep it, so that was in series, but I don't think you can do that in pandas. We'll test it out. But it's best to keep it unique so that you can uniquely identify each row. So that's why the indexes do not repeat. You see that it's not all zeros or 0, 1, and then all ones or something like that. So they are unique for a specific reason so that you can uniquely identify each row. And so if you have a particular column that is unique throughout, so say if I in this particular case, there are the student names over here are different. You will see that the student names are different and I can uniquely identify each student with the student name. But sometimes what happens is there are a lot of people having the same first name or the same last name, or the entire name is same. So you cannot keep name as the index. So we check that out. And now we have the roll number column, which is technically unique because each and every roll number is unique. If you go on to look in your own class, each and every roll number that is provided is only referred to one person at a time. So there is a roll number 1, there will be no roll number 1 in that particular class, because roll number 1 refers to the roll number 1 person or the person who has roll number 1. So we can actually substitute the index with roll number. Let's see how do we do that. So instead of creating the value inside, like a key and the roll number thing inside, what I do is I create the roll number outside, creating an index, and I create the rest remains the same. But over here, you see that there's a parameter called index, and I'm passing the value roll number to it. Now, doing that, you see the roll number column values appear here. So that's an added advantage where this is so even if you go ahead and see if you want to do some machine learning task or data analysis task, having all unique values doesn't make a lot of sense. Correct. So each and every value is unique and it's not going to give us any insights. So it's better to keep them as the index values so that you can easily refer. Now 0, 1, 2, 3 index may be difficult for the teacher to identify, but the teacher might know who is roll number 10. So that way it's easier for them to identify. So that's another thing that you need to keep in mind. So this is called re-indexing, and we chose the roll number column to re-index the entire thing. So we just say re-index according to roll number. Now that was how you create a particular data frame within the Python environment. But sometimes no, it's mostly all the time you basically have a particular data set somewhere and you import it into your Python workbook or Python code. So the most common file format is CSV. You also have JSON and Excel. So there are various functions for it. We'll just have a look at it. PD dot, and when I say tab, it gives me a list of all the functions as we discussed. We see that Excel file is something, Excel writer is another thing where you write the particular data frame into an Excel file. There should be other functions as well. You can always look it up in the, you can always look it up. See, read CSV, read from clipboard is also there. So when you do Control C, it basically saves your copied thing in a clipboard. So that is what is referred to as a clipboard. And then you have Excel as well. And there are various other things that you can read your data from, SAS, SPSS, SQL, and all that. So that was just a overlook of what all can you read the data from. But we are going to use CSV because that's the most generally used data format. CSV stands for comma separated values, and you will find a particular file named dummy underscore data.csv in the resource folder where you should get this particular uh, file as well. And so my current working directory, or the place that I'm working in at the moment, like this particular uh, file is in, it's in desktop, right? So you can see it's in the desktop file. But why then? The reason is, why am I going on to access it through the entire thing? Okay, let's see what does it happen if I just do this. I press enter and it still loads the data. The very reason it does this because they are in the same location. Now, it's a good practice to write the entire path of it, keeps you in the habit, firstly. And secondly, it's best to do this way when you have multiple CSV files with multiple versions, maybe, and you need to know which particular data or dummy file you're basically referring to. So it's better that way. So you need to write the entire path. Now they can be written in 2 or more formats. I prefer the one that's on top. This is the one. You see that the difference is not much. You just have a R in the front, and you see that all the slashes are inverted. So when you open a file, you go to properties and you copy the path of it, or you just copy the path from the file browser. It basically prints as such. But this particular slash is escape character or escape sequence, and it doesn't understand it. So let's see what does this do. It's going to give me an error showing that Unicode error. So you see that it gave me an error because this particular slash is not recognized as a path slash. I either need to do something like this, where I say that you need to escape or understand that this is the path of it, and it's going to run. Now again, this is extra work. I don't want to do an extra work. So when I write an R in front of it, basically what I'm saying is this is a raw string, and do not consider this to be a formatted string. So it doesn't consider the slash to be a Unicode that is used to do some other function like escape the particular value. So when I do this, you see that it still runs and gives me the value that I want it to. Now you see that I have a particular I won't do this, and let's see what does it do. Yeah, so you see that I have this data frame which has IDs as separate, and all the values come here. There are various names and genders, but you see that IDs are kind of on the wrong way. So I do not need an index and an ID as we discussed earlier. So how do I go on to set the ID as my index and go about working with it? There's a function called setIndex, which does the job for me. And when I do setIndex ID, it basically says that, okay, so the data frame that this person is loading has a column named ID, and you need to set the index as ID. So when I run this now, you see that the ID is in the index column, and all the values, the first name, last name, genders are in the column sections as they remain. So the very reason of doing it is the same as we discussed earlier. So this is how you load a data from a CSV file, which is important. So I'll just write this as important. You need to look into this. It's quite important. You should understand how it's working. Why is this file path written as R? How is this working without an R? And how do I use without using an R or this particular statement? So I'm just going to copy that as well and keep it for your future references. The easier way of doing it is just having two sets of slashes. That does the job as well. So these are the three ways that you can work on with it. And yeah, that's how you read a CSV file. This again, repeating myself, you can also use read underscore Excel or SQL or other functions that we look into. Now coming to the functions part, we see that there are a few functions that you need to know, because that helps you understand the data better before analyzing it or visualizing it. So you need to understand how the data looks. Now, because we only had 10 rows over here, it's kind of easy for us to visualize. Okay, it's just 10 rows. Okay, I get it. But usually you have rows ranging from anywhere between 20,000 to 50,000, and you cannot view all the records. It just goes on scrolling and scrolling and scrolling, which is quite difficult, right? So you have a function called head, and when you press enter, it gives you the first 6 records. Now it's giving you the first 6 records because I'm passing the value 6 here. If I do not pass the value 6 here and I press enter, you see that the default value of rows is set to 5. And if I just want to have, say, the first 2 rows as my outcome, I've just pressed that. So if you want a particular set of rows that is not 5, so say you want something lower than 5 or higher than 5, you basically specify the value, or you just have a look at the top 5 records just by passing this without any parameters. So that was the head function, where you see it basically just shows you the first 5 records. There is a similar function called tail, which does the same thing, but from the lower end, it shows you the last 5 records. And when you specify a particular number, it shows you those many number of records starting from the lower end. So it's the same thing, just from different ends. For your reference, I'll keep it the same way. Yeah. So that's how you want to visualize how the general data structure is. Basically, this is one of the first statements after you import the data. Like, once I've imported the data for my machine learning practices, and after that, it's easier to understand the data by using this particular function or this function. You can use them alternately, or you can use them both at the same time. Now, the next function that goes in is this, where it tells you the information about the entire data frame. So you see that there are 10 entries ranging from 1 to 10, and you have the number of data columns are 3 that are mentioned here. So the column names are mentioned here as such, so you can refer them to as 0, 1, and 2. And you have the null count, which says that, okay, there are 10 values, and there are 10 values in this particular column which are not null. So basically what it's saying is there are no null values. Now, null values are basically empty values. So if I have to give you an example with this particular row, say that if the male value wasn't present in the gender column for this particular row, this particular value would have been NaN or NA or null for that matter. Basically an empty value which needs to be filled in or removed. So in this particular case, all the values are not null. We have values in all the columns, or to be more specific, all the cells. And you see that the D type is object. Again, it's the data type of that particular column, and not and I'm not referring to the data structure. So in this particular case, we have 3 columns. It's easier for us to go through, okay, object, object, object. But usually you look into this particular line, which gives you a list of all the data types that are present. So it gives, if there are integer or say float values, it gives you, it just says, okay, you have these many more number of data type columns as well, and it gives you the number in brackets as represented here. So it also tells you the memory usage of this particular data frame. It says that it uses 320 bytes for this particular data frame, which is quite low. But when you go on to have a higher dimension of data, it's kind of going to increase exponentially. Let's look at the shape of the data. So we saw that there are 3 columns and there are 10 entries. The shape automatically becomes 10, 3. But this is another function that just gives you the value upfront. Now looking into the describe function, it basically tells you what how the data is distributed. So for this particular case, we don't use it for a categorical variable, but so I'm sorry, we do not use it for a string type or a object data type. But in this particular case, we just have object data type. So it says that it gives you a bit of information about that. We generally use it for continuous or discrete values, say integer or floats. But in this particular case, you see that the top value over here is this, and we'll see that it was you see what is the top value. Okay, so this is the top value. You see that it's Dodi, Macaulay, and Male. So that's what is given here. We have a frequency of it. So you see that the top value male has a frequency of 2. And then how many unique values are there? So there are 7 unique values here. There are a few values that are repeated. And you see the count of each value and the count of each column over here. So you have 10 values in the first column, 10 values in the second, and 10 values in the third one. So that's pretty obvious. And you use this to understand the distribution of the data. Again, you use it for integer or a float data type more often than categorical data type. Now the next particular function is columns. So it basically tells you or gives you a list of all the columns. Okay, I think it gives you an index. We'll just check that out. Yeah, it gives you an index, but always you can, just typecast it and have it in the form of a list. Now, why would you have it in the form of a list? It helps you maybe if you want to iterate through the columns for some reason, you can use it for that particular condition, or even when you label encode it. Now, this might be a new terminology that we haven't understood yet, but just keep it in mind, and we'll come back to it in the upcoming videos. So we can also use it for that particular purpose. So that's one aspect of it. That tells that finishes off this particular function. And we have, okay, now we're printing all the values from the rows. So we have a function called values. Let's see what that does. Okay, so it returns me array-like structure. Let's see what type is it. Okay, let's just check that out. Type this. See, it's a NumPy array. It was pretty visible here, but just for checking purposes. Yeah. So we see that it's a NumPy array, and it returns you a NumPy array. Now, accessing a NumPy array wouldn't be difficult. That's quite easy. We already know it, but we want to access the 0th index of the particular array. How do I do that? So row in the 0th index is this particular thing. If you want to have the first value of that particular row, it's easy. You can either do 0, 0, and it gives you the first value of that particular row, or you can just have you can just have 2 sets of brackets and it does the same thing. Now, we have already discussed this in the NumPy section, so I won't repeat myself. It's just the same thing. Values just gives you the NumPy array, and it's all NumPy after that. Now there's a function called count, and it returns you all the non-null value counts for that particular column. So we already saw that there are 10 values which are not null in all the particular columns here. But this is just another function that does the same thing. If you do not want to use this particular function and you just want to know the number of not null values in each of the rows, you can just use this particular function. Now, remember when I told you that we do not use describe for categorical variables and we use it for mostly integer type or float type variables. We basically use value counts for the categorical or object type variable. Now you might feel that I'm using the variable category a lot of times. You'll understand why when we go on to start coding and understanding why objects are basically categories. Do you see that this is the object data type, particular row, and I have two males and I have by gender as 2 as well. I have gender fluid as 2 as well. So it basically gives you a list of all the unique values in that particular column, and it also gives you the frequency of each of those unique values, which is quite important for us because when you have, say, a particular column where you need to understand what is the distribution of the uh, the particular column. So say if I have another gender column which has just males and females, I would want to know the ratio of the two columns. And to understand the ratio, I need to have the count of the male and the females in that particular column. So this particular function would help me a lot there. So I hope you understand what value counts does. It's quite important and highly used in data understanding. Now, selecting rows, we can do this where, so basically you might be wondering why can't I do just 0 and it should give me the same thing, but it doesn't do that. It throws you an error saying that it cannot tolerate it doesn't understand it that. So you need to provide it a range so that it does this if you want to do it in this particular way. But there's another way of doing it. We are going to look into it a bit ahead in this particular file. But if you just want a particular row, so you want, say, the first row or I would like to say, if you want the uh, first row, first index, if you want to visualize the first index, you're going to see this. The ID will be 2 because the index goes in that way. It starts from 1. So basically, you're referring to as the second row as the first index. So that's what it is doing here. And it does the same thing. You just need to pass a particular range to it. Even if you want, like over here, we are basically passing 1. I want all the values from 1 to 8, and I want them at a step size of 2. So let's see what does this print. You see that the indexes 2, 4, 6, 8 are printed here, and that's how they go about. So you want all the values from 1 to 8, it does that, and it has a step size of 2. So it jumps 2 and gives you the output. Now those are the ways of indexing it, but there are other ways as well. We're going to look into them. So selecting the columns. Now I have mentioned as preferred, but you can use it in a different way as well. We're going to look into that. But why do I say it's preferred? Now, in this particular case, because I created the data frame, I made it in a way which can be accessed in both the ways for easier explanation. Let's look at how they work out. So you see that the series output for this particular column looks like this, and we know it looks like this, so there's nothing new about it. And you see that the type is a series. Now, whenever you refer to a single column or multiple columns, it basically comes out as a series. So that's one way of extracting a particular column. This is the second method where you see there's not a lot of difference. Instead of brackets and gender in quotes, you have dot gender. Okay, and it gives you the same outcome. Now, the problem with this particular way of going ahead and accessing the columns is, say, if you have a column named uh, okay, let's just have age groups, and I say age groups is one of my columns. Now you see that there's a space in the middle, right? Now the space in the middle creates an issue. So when you do dummy df dot age groups, it basically just considers age and does not consider group and gives you an error. Instead, if you had an underscore like this, which makes this an entire word, you can go ahead and use this. The very reason I am asking you to get accustomed to this particular method is it is general and can be used everywhere. So even if you want to have the first name as such, I'll just have the first name, and you see that it works fine. And in this case, it will work fine as well because there is an underscore. But just if in any cases you did not have the underscore, you wouldn't be able to use it in this particular method. So you should keep that in mind and should prefer this over this. But I understand it's kind of easier to just write dot gender sometimes. So you can use it, but don't get too comfortable with it. Now, how do I select more than one columns? So I just do this, and you see that the value now is a data frame. Sorry if I said that if you have more number of columns, that gives you series. It doesn't give you a series. I'm sorry, it gives you a data frame, and you need to keep that in mind. Sometimes you do create errors like this, like I just did. So considering that each and every, so whenever you are taking out one single whenever you're taking out one single column, it gives you a series as an outcome. And whenever you're taking out, say, more than one column, say you're taking out two, or you want to access three columns, it basically you are trying to create a data frame by slicing it. Okay, so over here you're saying that you're okay. So you see that there are two brackets here, two sets of brackets here. Basically, this is the bracket that we are creating here as well, where you want to say, okay, I want to access this particular index of the data frame. Now, the first bracket does the same thing over here, but now I want to access more than one columns, right? So I need to pass it a list of all the columns. So this is the list, and this bracket signifies the list of the column, and that's how you get the output. And you see that the data type over here is now data frames and not series. Now, coming to the indexing part, remember when we looked into this particular example where we had 0, 0:1 just to access one particular row, and it was quite irritating, obviously. We have a particular function over here that we're going to discuss. It's called indexing. Now, it's either label-based indexing or position-based indexing. Now, you can use any of them based on your convenience, but let's just look at it. So I'm just printing the data frame here for easier referencing. I don't want to scroll up all the time. Now I want the 10th value of the gender column. So I say, okay, df.lock. I want the 10th value from the gender column. And I know that it's male. Let's see what does this give me as an outcome. It gives me male. So it was pretty easy to understand, right? So I want the 10th value from the gender column, and it gives me that. Now, printing the 10 row values. Now I want the entire row. So I press enter, and that gives me the entire row in a structure like this. It's obviously still a series, but it gives me an outcome of the row. Now remember when I said that series are basically columns? Well, when you use df.log, you get a series as an outcome, but it's not the column value. You see that it's a row value which is converted to a series, and it gives you the class that is coming. That this particular thing that you created, or the thing that you accessed, will be from a series data structure. And you get the entire row here, right? Like if you want, I wanted the 10th row, and you get the entire 10th row. So getting that out of the way, let's look at how you use iLog. So I run this, and you see that what I'm trying to do here is I'm trying to select a single element. Now I'm using indexing. Now people who are really comfortable with the NumPy arrays, and they want to extend the same kind of indexing, they usually prefer iLog, because it's index based locations, and I wanted the 0th row and the first column. So basically the intersection of the both. I want the first value from the first column. Basically it should be this particular value. Let's see what does it do. I'm so sorry. 0th column first. Yeah, sorry, the first column will be this. Yeah, sorry, this is again, the indexing starts from 0. So this will be the first column, and the value for the first column is Macaulay. Yeah, It's a macaroni. It's a pronoun. You can pronounce it anyway. Yeah, so it's that. And if you say you want to print the 10th row values, let's see what does it do. It gives you the same outcome. So the 10th row is the 9th index. That's what I've mentioned here just for your reference. So if I want to have the similar output using iloc, I just do 9 and it gives me the thing. And if we want to see the type of it, let's have a look at the type. You see that it's a series. So that's the two, those are the two ways you go about using them. And you can use them either way. You can use either lock or iloc, whichever one you prefer. But remember that lock is better in one way, that you need the 10th value from a particular column. So it's way more logical to look at it and understand. If you say, if you want this particular column, you need to know, okay, so this is 1, 2, 3, 4, 5. Okay, so it starts from 0. This should be 5. And okay, so this is 0 and 1. So I need 5, 1. And it's quite difficult. And, I won't say it's difficult, but if you're way more accustomed to this particular setting where you know the indexes and you use them, please go ahead and use it. But it's just easier when you have a label and you know the value from that particular label you want to access. It's quite easier that. So I usually prefer lock over iloc, but I use both of them whenever I want. And let's see what we have next. Printing the data frame again, just for future references. And we have a conditional state. So we have a few homeworks as well, but before that we have a few conditional statements, which is again very, very important. Now, I do not want to understand the entire data, or the entire data may not be of use for me. I want to understand how many values or how many rows does the gender have a value as male. So I press this as enter, and it's a very logical thing where I am saying that, okay, dummy.gender, and I want male values from that particular data frame. Now this gives me an index or a range of index, and I'm basically printing the range of index using dummy_df. So you see that it's pretty logical, not very difficult to understand. Coming to this particular statement, I'm basically saying I want all the values which has an index greater than 3. Now it's going to provide me a list from values starting from 4 till 10, because 10 is the last value. So I can just use it here, and it gives me the data set starting from 4. So these are called conditional formatting, and you can use them in various ways. You have a homework here. You need to extract the rows where the index is divisible by 5. So you already have the code here. You need to change it a bit. That's a hint for you guys. Now find the count of all the unique values present in the first name column. So you have the first name here, and you need to find the frequency of all these values. Now we looked into a function that does it. Now that's a hint for you. You need to go through the code and you should get the answer. Anyways, if you do not, again, just a reminder that the code is there in the PPT. You can always refer to the PPT as your lookup thing, but do try it yourself. So that was the basics of pandas. There are other functionalities that we are going to use and understand and implement and understand them. I just do not want to talk about it randomly. So once we start off with the machine learning aspect of it, we're going to look into the various other functions that come hand. So that was all for this particular video.
So in this video, we are going to look into the data visualization aspect. Now, fitting a machine learning model is not that difficult. When we go on to look into the machine learning models, you're going to realize that it's just a function that you need to import, at least in pandas. But understanding which function or which model fits the data best, we need to understand the data in and out. For that, data visualization helps us quite a bit. Now, when I when people usually say what is data visualization, the first thing that comes to people's minds are, okay, it's a graphical representation of the data. Well, that is not always the case. You can visualize the data in table formats as well. And when we look into the examples, I think you'll get what I'm trying to say. So over here, we're going to look into a data set that is related to heart diseases. So we are going to see the various columns that are listed here and what they mean. And you're going to see this data set. I'm going to link this particular data set in the code, and you can see that I've linked it here. So you can just go to this link and download the data set. Yeah, so I have a basic definition of the entire data and what is the actual goal. You can go through it in your own time. So let's look at the features. So you have age, you have sex, you have CP, that stands for chest pain. You have rest BPS, that is resting blood pressure. And anything above 130 to 140 is typically a cause for concern. Now you have COHL, that is cholesterol level. You have FBS, that is fasting blood sugar, and so on and so forth. Now we're going to look into each of these in detail, and we're going to visualize them in particular, and then also see the relation between various columns. So let's dive into that. You can always go through them. These are just general informations about the data, which you can always go ahead and run a few lines of code and understand. It's just for your future references. Now, these are the two links that I referred to for this particular code. You can always go through. Stack Overflow is the place to be whenever you are facing a particular problem. And this is the matplotlib tutorial that you can go through in your free time. It's easier. There are a lot of plots that I haven't covered here because it's a huge, humongous library. I've just covered the plots that are usually used and are basic, common, and intuitive. So I've used them. Now I have these libraries, and if you don't, you need to import them. We saw how do we go on to import. So you need to change it to code and run this particular thing. I'm not going to run it because I already have matplotlib. Now Seaborn also should be there with you, but if you do not have it, just replace matplotlib with Seaborn and you will have it. And I've used the magic function for matplotlib inline, which basically plots your graphs without the function plt.show, which is usually used when you're using, say, ID like spider or something. You need to have this particular function to actually plot the graph. So if you term this, or if you just mention this, it just plots in the same line or in the same notebook. So we go on to import the data here. Just because I have it in the same location, I haven't mentioned the entire path, but it's a good practice to mention it. I've just not mentioned it here for easier understanding that I'm using the very same data set. You can see that it is hard.csv here. Now, I use the head function to understand how the data is distributed. I see that most of them are numerical, or I guess everything is numerical. There is no need for changing categorical values, but they are categorical in nature. What do I mean by that? So when I talk about, say, the target variable, the values are 1 and 0. So it's not one particular person or 0 people. It basically means 1 basically signifies that he has heart problems, and 0 signifies that he doesn't have a heart problem. I have mentioned these values here. Let's see what target has to say. So has disease or not. So 1 is yes, 0 is no. We need to predict the attribute. So that's how you're going to refer. So each and every value, say FBS, what does FBS stand for? You do not know. You go back here, you check for, okay, it's fasting blood sugar, and 1 stands for true and 0 stands for false. Sorry. Yeah, 0 stands for false. And you can always come up here and check. It's easier, nothing else. So we come to the EDA part. I've just mentioned a few questions that are basically saying what we are going to do here. So what are the questions that you're trying to solve? What kind of data do we have, and how do we treat different types, and so on and so forth. Now we take a data sample. Now, if you want to use this particular parameter, you can use it, or you can just mention a particular number. which should give you the sample size, which is the same thing. So it doesn't make a lot of difference. So it basically takes a random sample from the data set and shows you, okay, this is how the data looks. A head will only give you the first 5 records. A sample will give you arbitrary number of records that you have passed in here. So when you run it again, you see that the values change here, the indexes change here. So that's just it, just to visualize how the data looks. Again, I told you that it's not the graphs are not the only way you can understand how the data is. You can also have tables. So plt.figure figure size is basically you fix the particular figure size to this particular dimension so that it's easier. And I've also mentioned about Plotly. Now, Plotly is used for interactive graphs. Now, you use interactive graphs when you're specifically creating dashboards, and it is easier for you to change the values and see what is the change in the graph and so on and so forth. But we're going to stick to the main graphs here. Now, I have another package called Mrs. It's I'll just spell it out. It's MISSINGNO, and it's abbreviated as MSNO. It basically I've just used to check it for this particular data and how the data is distributed. So we see that the data has these many number of rows, and there are no null values. If say a particular target variable had a null value, the bar would have been lower. So this shows that there are no null values, just that. You could easily use a different function. Say if I want to, you can just use the info function for it as well. So if you have say data and you do info, and that gives you that there are not null values. You can also have say data. You need to mention the column, but let's just see if this works. Some. Yeah, this works. So it basically says that these are the columns and these are the null values in it. So this is also a way of representing it, but this is best when you want to understand the particular thing that there are null values or not. But when you're making a particular presentation and you want to say that there are no null values, it's best that you represent it in this particular format. It's easier for you to explain your particular findings. Now, going to bar plot, and we're going to see count plots. Now in Seaborn, count plots are easy because they are just bar plots plus count plots. We're going to look into that. So this is how a count plot looks from SNS package, and it's quite counterintuitive. So here I'm taking into consideration the target variable or the target column, and I see what is the distribution of my values with rows with value 0 and rows with value 1. And I see that there is more or less an equal distribution. There are a bit lower number of rows in with 0 as a target, but it's fine. It's not that big a deal. When you have class imbalance, it basically means that say you have 20 records of 0 and say 120 records of 1. So there is a high class imbalance there. And there are ways of looking at it. We'll look into that as well. But this is how a count plot looks. Now, say you're not very familiar with the SNS package. You can also do it via matplotlib, but you see that there are quite a few lines that you need to plot in for the very same thing. And this is not highly recommended, at least not by me, because you see that the values over here, they are not zeros and ones. They basically come as continuous. So that's not a good representation. I would recommend you to go with this particular plot instead of this, but I've made it this way so that you can understand that you can also do the same thing via matplotlib. Now going ahead, so finding relation between target and other categorical variables. Let's see what happens. So here I'm first, I am using the count plot on the sex column, and I'm using the hue as target. So basically what hue does is it splits the bar into two based on the target. So this is what the actual sex count plot looks like. But when I use the hue function, it basically creates a legend. This is called a legend. And it says that, okay, so the red bars are basically the number of rows that are 0 in the sex 0 column. Sex 0, if I'm not wrong, means female. and the number of males, the number of people with a heart disease in the female section are the light bluish or the grayish blue color bar, and the same thing goes for the males. So you see, I have plotted the same thing here. So you have the distribution of sex here, and then you split the bar into two based on the target variable. So just to understand, I've plotted it one underneath the other so that it's easier for you to understand, and I've done it for all the columns. Now I I know that it's not that easy for you to understand all of this at once, but just try to figure out that you have a big, huge bar, and you need to divide it between some people who have a heart disease and some do not have a heart disease. Now, you're not going to divide it arbitrarily. The values will be given, but you need to show it in a way that is easier for you to explain. So when I say, okay, these are the number of people with chest pain, 0, 1, 2, 3, it doesn't make sense. But where I want people to actually understand how the data is distributed, considering the target variable. So I need to say that, okay, so people having chest disease with value 0 have 0 as the target variable. So they do not have heart diseases compared to the light bluish section, which means that they do have heart diseases. So that's one thing that you need to keep in mind. Now, going forward, we see that we have taken into consideration the CA column here. Let's see what does the CA column mean. Coming to the CA column, yeah, we see that the number of major vessels is 0 to 3, and they are colored by the fluorescence, and it's basically the valuation and the major vessels 0, 1, 2, and 3. There should be 4 values. Let's see what the show. Yeah, it has 4 values, 0 to 3, and sorry, yeah, your value is 0 to 3 here, taking consideration CA, yeah. And again, we have the same distribution based on the target. So I have done this for each and every column here, and I'll highly recommend you to go through each and every one of them. But it's basically the same distribution for each and every column, and I've tried to interpret what do they mean. And I've done it for each of the columns. You can see that the count plot is there over here, and you have a count plot on the top as well, but this has a distribution according to the target variable. Done it for this particular column as well, and then this one as well. And let's go ahead and see histograms now. Histograms again are a very important thing where we need to understand the distribution of the particular data, and it's really, really important. And you see that the value over here doesn't have a X and a Y. So it is basically a univariate analysis. You need to understand the variables of a single particular variable in the data set. So say you want to understand the distribution of age. So you see that the age is here and the frequency comes here. So you can understand, okay, age has more or less a normal distribution. And this is a basic histogram plot, and you given the X label and Y label using these particular functions. Again, it's very counterintuitive, and you can always refer to the matplotlib library. It gives you the very same information, but here we have we also mentioned the title as well, and we have done it before, but I'm just mentioning it here because it's important. You always mention the title, the X label, and the Y label. And over here we are plotting the histogram, so plt.hist, and the column that you want to plot the histogram for is mentioned this way. Now, Seaborn has something called the DIST plot, DIST, D-I-S-T plot, DIST plot, and you can refer the documentation here. Again, it's similar to the count plot. Again, it gives you the histogram, and this is how the histogram looks. So it gives you a line as well as the bar representation of it. The syntax is more or less same. I've just used the subplot function over here with the figure size 16,1 to plot this out. But the basic thing is that I'm using the DIST plot on the cholesterol variable for the data, and it gives me something like this. Now, it's kind of interesting to look at, and it might be important for you to visualize it this way. But sometimes we would want to just see the line or just the bars. So what do we do then? So there is a parameter that we can change. There's a parameter called KDE. So when you set it as false, it doesn't give you the line. You just have the bars here, correct? And say if you just want the line to represent the distribution, you can just have the normal KDE plot. You cannot say, okay, I'll just make the bars also negative and if false and then go ahead plotting. It doesn't make sense. So you use the KDE plot for that. It gives you the same thing. And now looking ahead, you can actually plot two different plots using KDE. So you say that, okay, I want to plot the KDE plot for data for where sex is equal to 0. And I'm changing the color to purple and then labeling it female, as you can see here. And then I do the very same for the male. I've colored it orange and I've labeled it male so that it's easier for me to understand, or for anybody I'm explaining this particular diagram to. So you see that the data, both the variables actually are negatively skewed, which means that the tail is a bit longer towards the left side. And it is again distributed using the male and the female thing. So it's again, it's useful for you to explain. Every graph that you make is for explaining the public, or for explaining what you're trying to express using this particular graph. Coming to the plot function, you can use this particular KD plot from SNS again. And here I've grouped it by FBS and then did the very same thing. You have sugar and no sugar kind of two sets, and it goes ahead with this. So you group it initially. So this is the group that I have. I named it G, and then I'm using get group where the group is 1 and get group where the group is 0, and then I'm plotting them. Okay, so use the line for the sugar and the area, shaded area for less sugar, or whatever the thing is. It's Thalashi, I guess. Yeah, so that's what it is. And you have the legend for the very same, making it more intuitive for the viewers. Let's go ahead and see what happens here. So now I'm grouping the data by FBS and then doing sugar and no sugar and plotting the very same. I see that the distribution is a bit different compared to when I was grouping it by FBS. Sorry, I was grouping it by FBS, but what did I do different here? Let's see. Okay, I'm plotting the cholesterol levels here, and I'm plotting the age here. My bad, I did mention the axis as well. Yeah, so basically you see that based on the age, it's quite different. The graph becomes different. And so you basically make the inferences just on the lower section using the markdown button. And you mentioned that there are more chances to have sugar at the age of 55 to 60. And this is what it mentions, right? So you see that the peak is the highest here. So that's how you go on to represent the other data. I have mentioned the KD plot earlier, and you do the same for the other data sets, and it's basically the same thing. Now you come to the where we are using the AXV line. Now this is the average line. So if I just consider the purple line here, which represents that it doesn't have any heart diseases, you see that the purple line is at the mean value. So the mean value will be somewhere around 58, 59. And the same goes for the yellow line, which represents the heart diseases, and the value will be somewhere around 52, 53, somewhere like that. So this is again helpful for visualization and explaining your particular thing, that this is your considering this your distribution, this is what the mean value is. And again, so it gives you the mean age here. So the mean age of a person having heart disease is somewhere around 52, 53, and a person not having the heart disease is somewhere around 58. So going ahead, we see that we have a histogram plot where I've passed in the data and the X, and I've also made a hue variable which says that this is, I want the target to be distributed with respect to the target variable. And you see that the age is distributed amongst the target variable. So you see that the PCH lines are basically 1 for the target variable, and the bluish gray lines represent the 0 target variable. So the graph shows that the people with age 41 to 45, somewhere around here, are most prone to heart diseases, which can be contributed to stress, like contributed for the stress factors, considering the stress factors. So once we reach age of 60, chances to get affected by heart diseases reduces. So you see that somewhere around here, the heart disease is getting a heart disease is really low. So that's what this graph shows us. If I have to apply this plot to the two variables, then we can use this plot. So sns.displot, sending in the data using X, and then I make the KDE true so that I can have the graph as well as the line histogram to understand it better. And now I'm distributing it with respect to sex and not the target. So I see that, okay, what was pressed BPS? I think it was blood pressure. Let's see, what does it mean? Yeah, it was resting blood pressure. Okay. And it should be 130 to 140. Yeah, so somewhere around here is fine, but more than here is not that great. So that's what we are trying to see, that the major people do lie in the range, which is more or less fine, and sex 0. So you have lower number of females and higher number of males in this particular diagram. Coming to this particular diagram where I'm having the data and I'm using this particular column, it basically has 4, which makes it too clustered, and it doesn't give us a huge amount of interpretation. Now I've made this graph specifically to help you understand that having too much in one particular graph makes it difficult for you to interpret anything. So it's fine to have it when you interpret it, and if you might interpret it because you know the data inside out and you got a lot of insights till this point. We're almost halfway through the particular notebook, so you must know what the data means and how the data looks like. But for anyone who is looking the notebook for the first time, or he just scrolled to this particular section, this particular graph will not make a lot of sense because it has a lot of information in a single graph. So it's best to have it in multiple formats or multiple distributions. Now, having a disk plot in this way makes it even better so that you can understand, okay, so this was the 0th column, the column with 0 values, and this is what the distribution looks like. For 1, it looks something like this. For 2 and for 3, it looks something like this. Now, this makes it way more clearer and interpretable for even others and for yourself. So that's how you should go about working on it. Now, coming to the section using heat maps. Now, I've used heat maps over here for a different reason, but I generally prefer using it for correlations, but we can also look at in these factors. So the heat map is a correlation between age and the resting blood pressure levels. And you see that the relation is quite dense in this particular area where the BP is somewhere in the range of 120 to 140, and the age is somewhere around, say, 50 to 60, or somewhere around that particular range. And you see that it's really dense. The heat map basically tells you how dense the data is, or how highly correlated the two particular columns are. So you can again use the hue parameter to split the data and to understand how does each and every target variable in this case has a distribution in that particular. But again, coming to the very same factor that having too much in a particular graph doesn't make a lot of inference. So you split it.
You split it again and you see that the distribution for the target 0 looks something like this, and for target 1 it looks something like this. So here we observe that even though BP is touching 200, that person is not likely to have heart disease. Initially, we made an assumption that the BP should be around 120 to 130, that is the normal range. But even when it is touching 200, they do not have heart disease. So it's possible for the BP may not turn out to be a very important deciding factor. So these factors being important or not important comes into consideration when we are building models, but it's good to understand which columns make a lot of, makes an important call for the target variable. So moving ahead, we have it for the cholesterol level and age. That also gives you quite an understanding. And again, plotting it in two separate graphs makes the entire thing looks better. I have the inference here, you can go through that. But the main agenda of this particular notebook is to understand how you plot it and what do the plots mean. So this is what it looks like for cholesterol against age. And coming to the graphs again, where we have the KDE plot. Now over here, I'm plotting the KDE for this particular column and target. And I'm also displaying the average line. So it's easier for you to understand which is the average line, what is the average for that particular distribution. Again, it's pretty interpretable. I've also given the inference here that it shows that the people who have heart disease have a higher maximum heart rate. That is the column value. We have it against the sex for this particular graph, and you can always refer towards DataScience. They really have good blogs and blog posts. I usually read a lot of articles from here, and they're really amazing. People do put in a lot of great articles. So I refer to this particular article to understand this graph better. You can also do that. Now the KDE plots can also have the shaded true, which gives you an area plot, which basically says that, okay, this is the area that falls under this particular section. So it makes a lot of sense, right? So this is the area that is common for both. Yeah. So both of them have old peak as 0 to 2, and it decreases for the target variable 1, but it remains somewhat constant till fourth value for target variable 0. So it gives you a better understanding, nothing else. It's the same thing, just that the area is shaded now. I have the same histogram plot, it's the same thing. So relatively to a histogram, KDE can produce a plot that is less clustered and more interpretable, especially when drawing multiple distributions, but it has a potential to introduce distortions. If the underlying distribution is bounded or not smooth, like histogram, the quality of the representation also depends on the selection of good smoothing patterns. So it's more or less that you basically using a smooth histogram gives you a better inference than using a barred or a binned histogram. So looking into scatter plots now, which is very important for linear regression tasks to understand how scatter plots are and plotting them for various other things. So here I've put in the marker as 0. There are other markers as well. You see that you can use other markers as well. I think there was a plus marker as well. Sorry. Yeah. So if you want to know what are the different markers, you use the same trick. You go inside the brackets, press Shift Tab, press the plus button, scroll down, and you try to find the marker option, which should be here. You have the X and Y, the format, the data. It should be somewhere. Okay, so you have dash filtered. Okay. Yeah, you see here, these are the markers. So you have 1, 2, 3, 4 as well for square markers. You have it for hexagonal mark. Let's try out the hexagonal mark here. Okay.
And this is a hexagonal mark. If you cannot see or visualize it, this is an hexagonal mark. It's not a square. Let's look at a different one. Is it the same thing? So I hope you understand what it basically means. It's the same thing. It's not that difficult for you to understand it. Same thing. Yeah. So the C1 scatter plot uses different parameters again, and it's more intuitive in nature. So you can even use the shade for the very same and try to identify or have the legend for the same. Again, it's best to have a single scatter plot until unless you are using some clustering algorithm. You should not plot multiple, or you should not use the hue function to plot multiple values to over understand a particular graph. So instead of having shades, it's best to have maybe different patterns. Now, because the graph over here is a bit small, it might be difficult for you to understand, but having different patterns gives you a higher intuition. Having different shades might confuse you a bit, and this is another way of interpreting it in the better way, where you have different shapes representing different sizes of the very same shape representing different things. So it's better to use it these ways. Now you can use two different hue variables as well, where you have the target as well as you style it according to the sex, and you have different values and a combination of the both. So a circle and a blue circle basically means that the target variable is a female. So a blue circle somewhere here means the target variable is a female, and it doesn't have any heart diseases. And a circle and orange dot or orange circle basically means that it's a female and she has a heart disease. And X and the target variables mean the same thing, but just that the gender is different. So that is also a good way of representing the data, helps you understand how the data is distributed. So plotting two plots side by side also helps you understand how the data is distributed. Here I have the thing as density. Let's see what I've done here. So I've again used a subplot. Now the subplots are basically used, I think you've already observed it earlier, but subplots are basically used to plot multiple plots in the same section. You can either plot it one underneath the other or one beside the other, and it's the same thing. But scatter plots, I've used it for X variable over here is old peak, and the Y over here is age, and I'm using the target variable to differentiate it. And obviously, I cannot use two variables for the KDE plot because it's a univariate graph. So I just plot that out, and I see how the distribution looks like. Again, you can do the same for the other columns and try to understand it. It's just to understand two different plots side by side to understand, okay, so if this is the target variable here, and I see that the target variable is overlapping here, does it overlap here as well? Yeah, it does. So that's how you understand the two things, nothing else. Now coming to box plots, it's basically used to identify outliers. So in a box plot, basically use the box plot function for the data, and for the column, you do the very same thing. You pass the column name inside the data and it gives you the particular data set. Now you can use the rotation function to rotate it a bit when you have a huge column names and you want to fit it in. You basically rotate it a bit and that does the job. Now over here we have cholesterol as the variable. And you see that it has a few outliers. Now, what do I mean by outliers? I think we have discussed it before, but just to understand it again, outliers are basically that do not follow the general distribution. So I have a normal distribution. This particular line is defined the normal distribution. So this is the 95 percentile values. So this particular graph shows you the 95 percentile values, and this particular box gives you the quartile range. So any value coming inside this comes inside the interquartile range. The line in the middle shows you the median value, and the line beneath it, the box value, the lower length of the box gives you the quartile 1, and the upper value gives you the third quartile.
So that's how we interpret the box plots, and these dots basically represent the outliers. You can have some beneath it as well, but basically it shows you the distribution. Now, if it's difficult for you to understand the distribution using a box plot, there are other ways of looking at box plots as well. And we have swarm plots as well. So that also gives you a good idea. So you have box plots from Seaborn. So this is a box plot, and you see that you have outliers on the top as well as in the bottom for these particular sections. This is what a swarm plot looks like. Sorry, this is a strip plot, and this is a swarm plot. Yeah, and you can also plot it together to have the understanding. So you see that there is one dot over here and a consecutive dot on the right hand side saying that it's an outlier. You have an overlap here. You have a few overlaps here and here. But you see that most of the data do lie inside this particular section for all the distributions. So let's look at the code. It's the same thing. We just pass in the x and y values. We use the different functions. That's the only difference. This is the swarm plot, the strip plot. Yeah, we have the strip plot and the box plot plotted together. And I'm using the tight layout, so it's tightly, centered, aligned in a particular section. It doesn't flow out or it's not stretched across. So, as with many other Seaborn functions, you can add hue parameter. You can add the hue parameter here as well. It's the same thing. Now, so this is the data for the, what was this particular column? Let's just see. Maximum heart rate achieved. Okay. So that is represented by Halach. If I have to pronounce it that way, I'll just refer to the maximum heart rate achieved. Let's go back, scroll all the way down. Here I was. Yeah, so this is the maximum heart rate achieved distributed according to the target variable. And you see that each and every box plot shows, again, box plots are univariate data visualizers. So you cannot have a block plot against, say, age and maximum heart rate. So you can have it for the maximum heart rate in general, and you're basically distributing or splitting the heart rate values with the target variable. That's what it is doing. Here you have it with respect to CA and the maximum heart rate value, and you're using the target variable. So that's how it's basically using. You're using the palette to set to. These are various sets that change the color, and this is how you represent the graph, and it's basically interpreted the same way. You have outliers here. This is the entire distribution, and you go on to understand it. So in general, people who have higher heart rate, they have higher chances of getting diseases irrespective of their CA. That is the number of major vessels. So that's what I interpret out of this graph. Now coming to the violin plots, which is also highly used, and I highly use it for understanding the distribution. I think it's a bit squashed here. Let's look at these. So yeah, this is how a SNS violin plot looks like. So you see that this is the graph, and this is this is the box plot, and this is the violin plot for the same. You have so this basically has the histogram as well as the extension. So instead of understanding it through the box plots, you understand it through this way, that there are a few outliers on this section. You have a few outliers on this section and this section as well, but it's really near. You have some of the outliers which are here are really far, which we can see here, and the data is positively skewed, which also makes sense here. So that's how the data is represented in a violin plot. Now you can again use the hue parameter for here as well, which you can have it represented in both the ways. Now I would prefer this over this, but any of them work. So they basically mean the same thing. You have the values of 0, 1, and 2, and you are basically splitting it based on the ASX. And over here, you're basically splitting it according to the target, and you have the same values. So the blue portion means the 0 target, and the orange portion means the
target 1. And over here, the blue violin plots mean sex 0, that is female, and the orange plots mean the orange plot means that they are male. So you can represent the hue variable in both the ways. So you see that it's represented in both the ways. Split is equal to true, and basically that's why you're splitting the violin plot into 2 here. Over here, it's by default, it's false, so it doesn't do that. Now, joint plots are also really a good way of understanding the data. So you have the distribution and the scatter plot with respect to both. So it is kind of interesting to look at. So you see that I have set the values like the style and the color here, and then I use the joint plot to understand the data. You see that the data is mostly centered, or has center over here in the lower section of it. But yeah, so the graph, the histogram gives us the intuition, and you can always use a scatter plot along with it on the other side of it. But it's best to use a joint plot when you want to do both. Why to plot two different graphs? You can just use a joint plot to understand both of them. So let's look at the different styles of using the plot. Yeah, so you can have the line as well, which also tells you that this is the line that goes in the middle, and the smooth histogram looks something like this for these particular columns. And it's the same thing. I've just played around with the parameters, and you can do the same, and you can see that there are various things. So you have the REG thing that is basically fitting a regression line between these two, and it's telling you that the regression line would fit somewhere like this. The regression line also tells you that the value is positively related. There's a positive relation between these two. Now we're going to understand linear regressions in the upcoming videos, but a basic understanding of what you can do with the joint plots. You can also represent it this way. Yeah. So this looks like a honeycomb, but it isn't. It just tells you where the data is mostly centered along. So you see that it's centered along the lower sections, and you can also plot it this way. So this is more of like a contour plot. So for the parameter for that is KDE, and it basically says that, okay, so this is where the data is centered along. So I was saying centered, and this is what the centered actually looks like. So if you consider this to be a mountain, mountains are represented like this in 2D structures. So this basically means the left angle of it. This is the right angle of it. And sorry, this is the front view of it. This is the side view of it. And this is the top view of the mountain. So this particular section where the innermost circle is there represents the most dense section. So you can either consider it to be the depth or the height of the mountain. You can also consider it to be the depth, but it means the same thing. So it's basically the relation between the two variables and the concentration of where the data are. Yeah, so we have the matplot representation of the same as well, but why to write so much of code when this particular thing can be done using a single line? So it's the same thing, and it is when you are trying to make a data visualization notebook for someone, or you're trying to do data analysis and you need to represent it and explain it to someone, I would highly recommend you to go with SNS plots, because they are easy to use. But if you want to understand how to plot things better and what all functions are used and how do you go about it, it's best to go ahead with Matplotlib. It actually helps you practice well, and it actually helps you how to go ahead with the functions better. So this was the basic understanding of data visualization. We are also going to look into various other visualization patterns as and when they are required as we go ahead in the machine learning models. But yeah, this is the basic understanding of it. So even if you did not understand a particular section, it's not that difficult. You can always refer to the documentation. I always say that, refer to the documentation, refer to the documentation. It basically, what I'm trying to do is inculcating that habit, because it's really important for you to refer the documentation again. And the corporate world actually requires it and highly recommends it. So it's a good habit to refer the documentation, and you find all the solutions there.
And if you are not able to find the solution there, or maybe the solution is there but you don't understand the solution, Stack Overflow is the best place or the second best place to go after the documentation. So it's not that difficult. The things are pretty counterintuitive again. But if you did not understand any of the functions, if I rushed through it, I'm really sorry for it, but I don't think I did. But even if you did not, just go inside the brackets, press Shift Tab, press the plus button, and you have the code snippet, or it's called the doc string, but you have the snippet of the entire function over here, which kind of gives you the representation of what all things can you do in this particular thing. So if you want to take it as a homework, you can take it as a homework and try out the other values. It will be actually great as a practice for data analysis and data visualization. But I would say wait it out, because we are going to do the same visualization for the classification task. We're going to use the same data set. So we are again going to do a bit of data analysis. So you can practice it and you can go ahead with the data classification task ahead with on the very same notebooks. Doesn't make a lot of difference, but yeah, go ahead and do a bit of visualization. Uh, uh, and I will obviously put in the document in the resources folder, and you can have a look at it over there as well. So this was all for data visualization for a basic overview. We're going to look into them in detail as we go forward. So in this video, we are going to look into data transformations. Now, data transformation is a process of converting raw data into formatted or structured form of the very same that would be more suitable for model building. So we are going to learn how to build machine learning models. But before that, we saw how to do data visualization and data cleaning. So data transformation is also a part of it. And why do we need data transformation? The algorithm is more likely to be biased when the data is distorted or skewed, and transformation data is the same scale allows the algorithm to compare the relative relationship between the data points better. So basically, when you transform the data, you don't change it as such. You change the structure of it, which means the same. It might sound a bit confusing, but think of it in a way, say, basically you're playing in a sandbox and you want to construct something. You want to construct, say, a sand castle. Now you transform the way the sand looks. It is not a plain surface. Now you have a structured uh, building, or not exactly building, but a castle over. So now you basically transform the thing, but it still is sand, right? You haven't changed the things. That's how data transformation works basically. So you make it in a more structured format, which gives you a better understanding. Nothing else. Now we are just going to look into the import statements that I've used here. So I've used pandas, I've used NumPy, I've used matplotlib. Now the new thing that you're going to see here is pandas.api.type, and I'm using is string dtype, is numeric dtype, just to determine if it's string or it's numeric. Nothing fancy. So I have the marketing data set here, and you're going to see that it has 28 columns and 5 rows. And okay, transforming data is also called feature engineering, so just another fancy term for the very same thing. So transforming year births, I think there's a column called year birth. Okay, year birth into ages. Okay, so you convert date today dot years and year birth. So if you go on to see, it's pretty logical, right? So when I go on to ask you, okay, what is your age, you're basically going to uh, go back to the day where you were born, and then go on to add in the years till today. So that's what this is doing. Okay? And that goes on to convert the entire age. That goes on to construct a different column called age and create the values there. I'm doing something for transforming the DF customers into enrollment lengths. Now DF year, that basically is pd.time index. So this is on the function that I'm saying that, okay, df this dot year. I'm basically, okay, do I have df year here? Yeah, df days customer is here. So this is a date that I'm saying that, okay, if this is the date and
I just want the year to be here. So I'm just taking the 2014 as the values over here. Okay. So that's what exactly I'm doing. Putting this column value into a date column, not an object function. Sorry, an object column. And basically what I'm saying is I just want the years, so dot years. Enrollment dot years will be dot today minus years. So that is the enrollment length. So just considering what is the length of the enrollment, I just want to create I just want to create a new column, take in the date for today, and basically just take the year aspect of it and subtract that from the year that I'm getting here and just put in the values. Again, nothing fancy, just a bit logical. So you will get a hang of it as you go on to use it over the time, but having a general idea that this is date time object and this basically makes the algorithm understand that this is not a string and it's a date, so you need to understand that. That's the only thing that it does here. Now transforming currency format into numbers. So I have income dollars and I'm saying df.income.string replace comma with null spaces. So basically if you go on to see the values over here will have dollars and commas, which I do not want. Now this will give me a string output. Now I will not be able to use the number format of it. So if I go on to say which is the maximum income or which person has the maximum income, I won't be able to do that just because it's in the string format. So to convert that to number, I basically go on to replace the commas with a space, a null space. This is basically null. It basically means nothing. So I do not want anything in front or behind it. So that's what it is doing here. And I'm doing the same with dollars and with points as well. So it's just going to keep the values there. And as type as int. So I fill in the values with 0 and that does the job. So I'm just changing the entire thing into an integer form. So it's easier for me to understand. Now I'm also applying the round function that goes on to divide the entire thing to 2 decimal places. I remove the thing. And at the end, I just have this 8.48. Okay, so that is more meaningful to understand rather than understanding this. Okay, so that's another aspect of it. These are just the transformations that are useful, and you should go ahead and do it on your own to have a better understanding of it. But we'll do it over time once we go on to build models, and we need to do transformation anyways before that. So we're going to do it. So don't worry, just have a view of what happens where and where do we use what. That will give you a basic idea. And when we go on to practice them, you will always have homework and stuff to do along so that you have a better understanding of the thing. So that was here. Then we have EDA. I have these columns that I want to go on to view, and I'm creating a histogram for them. So I'm not going to create a histogram for each of the values. So what I'm going to do over here is, I'm going to take the numeric value of I. I'm taking the range of numeric values. This is the column names, and okay, so this is I'm storing it to var, and then I'm doing a subplot. So fig dot add dot subplot 3, 5, I plus 1. So I'm saying that there are 3 rows and 5 columns, and so basically it starts from 0. The length will start from 0. So the first figure that I want to put here should be 0 plus 1, correct? So that's why I plus 1. So basically the first subplot will have the values 3, 5, 1. So basically there are 3 rows and 5 columns, and the first value should be this particular subplot. And basically I'm setting the label as var, which I get the which I get from this particular function. I'm storing the var, and df of var dot plot df kind is equal to history. So basically I'm saying that, okay, I want to plot. This is a direct plot function. I'm not using SNS, that is Seaborn, or PLT, that is matplotlib. I'm not using that. So pandas have its own plot functions. I'm generally just using that. So just to specify what kind of graph do you want, you just say hist. There are some warnings. These are not errors. These are some warnings that come in. Not an issue. You can overlook them for now. And you see that these are the various graphs that get plotted for all the columns that I've listed there. And if you see, there are a few skewed datas here and there. So we're going to look into them as well and try to have a better understanding of how do we go on to change them. So basically, there is log transformation for right skewed data. Okay, you see that most of the data is rightly skewed here, or basically you can say it has a positive skewed graph, correct? So we are going to use log transformations for it. So log transformation is basically transforming the entire data to log to the base 2 to have a better, flow of the entire data. We are going to look into the graphical changes that happen. So I'm going to log transform these particular columns that I've listed here. I plot the figure. I'm just mentioning the figure size to be 24,10. Then I want to say I want to have the range of all the values that are in the log var. So it is going to range from the length of the particular log var, so 0 to that particular value, taking in the individual values into var. Again, that's what I did exactly. And then transform, basically log plus var. That is basically another variable which is just adding uh, basically a prefix to the particular. So basically, if I want to say, take an example like income underscore m dollar, what it's basically going to do is just add in log underscore in front. So the outcome is going to be log underscore income underscore m dollars. Same goes for this and so on and so forth. Now, again, I'm doing the same thing. So basically here I have 2 rows and 5 columns and I'm saying j plus 1. So what do I mean by j plus 1? Again, it's going to start from 0 to that length, 0 to less than that length. So I'm going to say, okay, my first plot is going to be something that needs to be added in. So 0 plus 1 gives you that. And then I want to set the labels as var, and I want to have the transformed value of it. Okay, so I must have done the transformation here. There. Okay, yeah, see. So df.transformed is basically doing mp dot log 10 log to the base 10. Sorry, my bad, not log to the base 2, log to the base 10. And df var plus 1 gives you the value here. Sorry, bad. And then basically that value is that list of values is added to, sorry, numpy array. That array of values is added to this particular column in the df data frame, basically. So now again, skipping through all the warnings, I go on to see this is the data. So initially, if you're going to see, let's just look at one graph and I think you'll understand. So I see that this has a similar bell-shaped curve. It won't be exactly symmetric, but it is kind of symmetric. So what was it? It is MNT gold prods. Let's see what it had here. MNT gold prods, MNT fruits, gold fraud. See the amount of skewness that this particular graph had. It was perfectly positively skewed, and this is more or less normal. So for all the graphs that we see here, the data is more or less normal. Like it might have a few frequencies here and there, like the modal frequency is a bit like over here. We can see that it went, now it is left skewed, like it's a bit left skewed. Again, my bad, negatively skewed. You should always use positively and negatively instead of left and right. So this is left skewed, and this is normally skewed. It has a small skewness towards the left side or a negative side, but it's fine. It's workable. It's way better than what we used to have. So going ahead, we also have clipping, which is nothing but we take in the quartile ranges and then go on to work on the basis of that. So I go on to say, okay, I want to clip age and num web visitors, like on a monthly basis. I think that's what the comment means. And I say, okay, for I in clip underscore was, which is age and num web visitors month, I'm going to transform clipped plus I. So this basically will store clipped plus age. And then the upper limit of that particular value will like dot quartiles will give you the 95th percentile, like the 95th value, the 95th percentile value, and same goes for the 0.5 quartile. That will give you the 0.5% value. And on the basis of that, you can set the upper and the lower limit. Okay. Now, when you go on to say df transform, you're basically going to do dfi.clip. When you say dot clip, it's going to clip the entire value based on the lower and the upper limit and set the access to 0. Basically, it's going to take the lower limit and the upper limit, create a range, and everything that falls in the range stays in the transformed data frame, and everything apart from that is removed. So basically, when I say access is equal to 0, it basically goes on to remove everything in the row format. Like it's going to delete all the rows that do not fall in this particular criteria. And so print dfi dot describe is going to describe the outcome. We're going to see that, and we're going to also see print df transform dot describe, which after transformation what happened, and the figure plots as well. So I want to see this was the actual value for count. Okay, so the name was age. We're just going to look into one, and it's going to be counterintuitive from next. But anyways, so age, correct? And you see that the maximum value was 128 and the minimum value was 25, which is not acceptable. So it would flip the values on the basis of 0.5 and 95 percentile, and goes on to give you 0.33 as a minimum and maximum of 71. So it's going to have a way smoother curve now. Okay, and that is for number of web visits per month and clicked web visits per month as well. So this was the initial curve for age. This was the initial curve for age, and this was the one that was clipped in. So that's a pretty good curve, like better curve, to be honest. Now you would say that this is normally distributed, but no, it is not normally distributed. It is positively skewed. There, if you go on to miss out this value, the 120, 120 label, basically that does create an issue. Okay, so this has a bell-shaped curve, it's nice, I'm just going to use it. So do keep in mind about the values at the end, which are not that greatly visible. Always go on to plot a box plot to have a better understanding. So this was the clip value. This is a non-clip value for number of web visits. Sorry, what was num web visits month. So num web visits month has also skewed data over here, as you can see, and this goes on to convert it in a better format, at least better than this. So goes on to clip down the ranges in the percentile ranges of 5 to 95, which is the accepted range. And yeah, so that was the basic methods that we are going to cover now. There are other methods as well. We go on to scale the data generally when we have huge variation. So basically a person, say if we go on to take a normal statistic, say company wants to understand what is the distribution of the salary. Okay, so this is just an arbitrary example where obviously the CEOs and the higher officials are going to get paid way higher than the low level workers. So there's going to be a huge variation. Okay, so say the lower the minimum wage workers, like the people who help you in an office, like the peons and all that, and all of them, they might be paid somewhere around 15 to 30,000. But going to a developer in the particular company, he might be paid somewhere around a lakh and a half per month. Going to the CEO level or the manager or the director level, they might be paid somewhere around 10 to 20 to 30 or even higher. Okay, so that is where scaling comes into play. So there are two kinds of scaling. I'm just going to explain it in brief, and we're going to look into the practical example as and when we come to it. I specifically did not keep it in this particular video because it would, create a lot of confusion. We're going to see where is it required and when do we use it as well. And you are also going to use it at the end for your projects that we have. Okay, so coming back.
So we can either normalize the data or standardize the data. So I think we looked into probability distributions and hypothesis testing, and we came across Z scores, which basically is nothing but the standard deviations. Now that is exactly what standardization of data means. Okay, so you have a data, you go on to say, okay, the mean is 0 and the standard deviation is 1, and you go on to plot the values for it. Now, the values that you have is basically in terms of standard deviation. Okay, and going to normalization. So consider that you have values ranging from 0 to 100, and you have 10 rows, and each of the values are at an interval of 10. So basically you have 0, you have 10, and then you have 20, and so on till 100. Now the data ranges from 0 to 100. In this point, it's still understandable to not normalize it. But just taking as an example, when you normalize the data, the values are going to range between 0 and 1. So basically, your minimum value, that is 0 over here, will be represented by 0 again, but 100 will be represented as 1. Okay. And 10 will be represented as 0.1, 20 will be represented by 0.2, and so on and so forth. So you want to shrink down the entire data, but it means the same. Same goes for standardization. When you even convert the values in the form of standard deviations, the values might change, but they remain the same even after being transformed. They are just in a different unit or a different standard form. So that was all for standard deviations that you needed to know in brief. And we're going, as I said, we're going to look into them in the practical sessions as we start building.
So in this video, we are going to dive a bit deeper into machine learning and understand the various concepts that run along. So first is the steps in machine learning. So the first step is importing the data, as we even understood that we need pandas library for that. For basic structures, there are other ways of doing it as well, as we discussed earlier. Then we go on to do something called EDA, and after that we do data transformation. Then we select a model, we train that particular model, we test that particular model, and then deploy it. We're going to look into each of these steps in detail. Now, importing the data. So the data can be in various formats. So the first step is importing the data. So the data can be in various formats and distributed amongst various files. Combining them in one is one of the tasks that is very crucial before processing the data. Now, many a times the data is unstructured as well, and we need to understand the flow and pattern and go on to make it consistent across the entire file. Now, there's another concept called data cleaning, where there are some missing values or there are some other problems with the data, and we go on to clean it up. Basically, say you have a column date, which is in string format, which is in the date time format, and in the integer format maybe. So you go on to make it consistent. That is one of the tasks, or as written here, where we have missing values and we go on to clean it. Basically, we handle missing values in ways which we are going to look into. And then we have the next step as exploratory data analysis, where we view the data in various formats, understand the structure, understanding how the values are distributed in the columns, use visual and non-visual methods to understand the data, and make a note of all the inferences and insights and assumptions that we either gain from the visuals or the non-visual representations, or we assume. So assumptions are made and they are not given. So basically, when I view a particular graph, I say, okay, so this might be the case. That's an assumption. And when you see, say, a particular graph and say, okay, so this is what the graph means, that's an insight or an inference. So that's the difference, and we need to make a note of these things and understand the data. Now, these steps are really important And there's another step that we're going to look into just after this particular step. So these steps are really important before doing any kind of machine learning modeling, because we need to understand the data throughout, so that when the model predicts something, we understand why is it predicting that. Maybe it's predicting wrong, or it's predicting something that is right. We need to justify why it's predicting right and why is it predicting wrong. So to justify our answers or to solidify our justifications, we need to do these steps. Now, the next step is data transformation, where there is, if there is any discrepancy in the data, or the column needs some kind of modification, we go on to do this particular step. Now, most of the times you do this particular step, but if you have, say, a pre-processed data which doesn't need any kind of data transformation at all, you might just as well skip this particular step. But for most cases, we do data transformation. Sometimes there are even rows that you need to create, like new rows that you create from the existing ones. Say you have a start date for a particular data set. You have a column called the starting date and maybe an ending date. Now, instead of having two columns, I can have just a single column called duration. I go on to subtract the start and the end, find out the duration, and have a single column for it. So that's data transformation as well. Now, moving on to the next particular slide, which says we need to have model selection. Now, model selection might sound really, really weird, because there are obviously some models that perform really good, like the new ones, which have been developed, or there are some other ways that you can go ahead and use them, and they give you a really, really high accuracy. Now, why do we need the older models, or the simpler models which do not give you a very great accuracy? Now, you need to understand that there are various models. So there is no particular concept of having a best model. A model that performs good on a single data set may not perform good on another data set or a different problem statement altogether, even though if it belongs to the same kind of machine learning task. So after understanding how the data is and transforming it, the best possible way for future computations is to choosing a particular model, correct? Now, just because a complex model gives you a better accuracy, we don't start off with them. That's what we discussed, right? So we start off with a weak model and gradually up the ladder. So we have a weak model, and then we go on to test something else, and we have a different model. And each model is selected, trained, tested, and then even tuned till the point we say that, okay, now this is what the model is going to give you at best. Now, do we consider this particular model, or do we look into other models as well? Usually, there are various models that a particular machine learning engineer takes into consideration while working on a data set. He takes in various models, tests them generally, then tunes them, tests them again, and that's how he goes ahead or progresses. And there are various ways in which you can use all these models together. That's called ensemble methods, and we're going to look into that as well. But to have a general idea, we start off from the weak models, try to make them better, and then move up the ladder. Remember that. Now the next step is training the model. As we understood that we need to train the particular model so that it understands what are the various patterns and goes ahead in making the predictions that we want. So each and every model selected is trained over multiple times in multiple ways to understand why one training set is better than the other, or why one model performs better over the other. So that's one of the concepts of training the model. Now, testing the model. So we can only understand how good the model is by testing its learning on data that it has not trained on. Now, the training data has to be unseen. By what I mean unseen is the model hasn't viewed or hasn't been trained on that particular data, for the very reason that it it has to work on unseen data. So why am I training a model, or why am I making the model in the first place? I need it to work in real life scenario. So that's how I'm going to understand, or the particular programmer who is programming that particular model understands, okay, so this is what the training accuracy is. Okay, so that's how it works on the training data set. And then he uses the same model and tests it on the test data set. And when he gets satisfactory results, he goes on to the next step, that is deployment. Now, after being satisfied with the results, we deploy the model in the real world to see how it works on the data from the real world. And the task doesn't end there. If the model works fine, we try to make it work better. If the model fails to work, then we take it up again and go through the entire cycle all over again. It's a continuous process. You need to understand that it's a continuous process. You just are not done at the testing phase. There are various ways there are various phases that you need to check after that. And even after those processes, you might just need to start all over again. So that was the process part of it. Now we'll look into the types of machine learning algorithms. So this is a major overview of the entire thing, where you have the main types as supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. We're going to look into each of them in detail, but just to have an overview, you have a regression task for continuous variables. You have a classification task for categorical variables in supervised, and unsupervised doesn't have any target variable, so you cannot justify which kind of variable is it. Is it continuous or is it categorical? But there are two ways of doing it. You use clustering and association. The examples for each are listed here. You can go through them. And when we come to semi-supervised, basically they are categorical target variables, and you use either classification or clustering. And the main examples are text classification and lane finding for GPS data. Now, reinforcement learning is something that is very, very interesting. You have categorical target variables, or the target variable is not available. You can have both the cases. Now, you either classify, like in the case of optimized marketing, or you go on to control the particular model. But for example, like in driverless cars, you do not have a training or a testing particular phase. What you go ahead and do is you have a model, and for each and every task, uh, you go ahead and do something that makes the model more robust. We are going to look into that in detail. Now, starting with supervised, when the data set that we are working with has labels in it, which tells us which all column values represent which category, or a continuous value, we perform a supervised task on it. So these are the main two classifications, as we saw. We either have a regression task or we have a classification task. So in regression, is a task when the value that you want to predict is of a continuous type. And in the same case, when you want to predict a particular value that is of categorical type, that's basically a classification. Now, this is the basic representation of how a regression task looks like. So you have all the data points, and we are fitting a regression line to it. Now, this is linear regression. We're going to look into them as well, but to have a basic understanding, this is how the graph looks like for that particular model. And this is how it looks for a classification task. So you see that the category, or the prediction, is based on categories. You have class 1 and class 2. So that's a classification. Now moving on to unsupervised. So if the target variable or the value that you're trying to predict is not available, then we perform unsupervised task. Sorry for the typo. Now, the two ways of going ahead with is clustering and association, as we saw. So clustering is when you group similar points together, and association is when you try to find a pattern and try to recommend, or the prediction that you're trying to make is more of like a recommendation. So let's see how the graphs look like. So this is how a clustering graphs look like. So they are, we can't call them three classes here because we don't know which what does this particular cluster represent. But we know that these clusters represent something similar. That's why they are clustered together. Now in association, basically you see that there are various purchases, and you see that the particular model says that these are frequently selected items in this particular thing. So you see that a bun and milk are selected together, and milk and diaper is selected together. So every time a person buys a bread, he is going to the model is going to suggest that do you want milk with it. And every time there is a person who buys a diaper, he is also going to be suggested to buy a milk bottle because of the data pattern. Now, coming to semi-supervised tasks, we need to understand a few things before we understand what semi-supervised mean and what is the task what is the thing that we perform in that particular task. You need to understand that getting a hands on label data can be really expensive and a tedious task. Now, getting a data set with some labels or no labels at all, and then labeling uh, the data, like a few records of it, is an easier task comparatively. Now, once you have the low number of labeled records and some non-labeled records, basically you take the labeled records, pass it to your particular model, classify, train your particular model on that, and classify the other non-recorded label rows and label them accordingly. So that reduces the manual labeling time significantly. So that's what supervised uh, tasks are mainly used for. Sorry, semi-supervised tasks are mainly used for. Now coming to reinforcement learning. Here, the learning is a continuous process. Every time the model makes a wrong prediction, it is instructed that it made a wrong prediction and that it needs to rectify the same. Cycle goes on till the point the machine can do its assigned task without fail. So there are two interesting facts that I would like to bring out in this particular slide. One, reinforcement learning was a concept that was derived from an experiment in a lab where you had a particular mouse and a particular maze, a small maze, and the mouse seemed to go on with the go on to find that particular pattern that it can you know find the pattern that helps him to cross the maze and find the piece of cheese on the other side. Now every time it took a wrong turn, it uh, the lab assistant or the experiment overwatcher or whoever you the researcher basically uh, took the mouse out of the maze and asked it to start again. So that was a penalty. Now every time it crossed the entire maze, he got the piece of cheese. So that was a reward. So that this is the basic concept. So every time the model makes a wrong decision, it is given a penalty, and every time the model makes the right decision, it is given a reward. And here, uh, image of the grandmaster of that particular time for chess is competing against the IBM machine, and the IBM machine actually defeated the grandmaster, and it basically used reinforcement learning. So I have listed the link in the presenters section, presenters notes section. You can go through that. It's a pretty amazing thing to go through. So that was the basic understanding of machine learning and what are the various types and what do you do in various things and how do you go about it. We're going to have a practical exposure uh, and code each and every model and understand how they work. So we in the previous videos we saw that machine learning has some tasks which are called supervised and some tasks which are called unsupervised. So in one of the tasks where we were looking into supervised tasks where we had the predicted or the predicted value that we want to predict, the outcome value. We have it for some data and we want to predict it for the other rows. And when the data is continuous, we want to predict a value that is going to be continuous as well. We basically use regressions for that. And the most basic model is called linear regression. So we are going to look into that too. So what is linear regression? Linear regression performs the task of predicting a dependent variable value. Over here, we have it on the y-axis, and it's also depicted as y. And it is based on a given independent variable, which is x. We term it as x, and here on the graph, we have it on the x-axis as well. So the regression technique finds out a linear relationship between x, the input, and y, the output. Hence the name linear regression. So because we find out a linear relation between the two, we basically are trying to say, okay, because of this value of x, we have some value of y. So the formula is for a straight line. Since we are trying to build a linear relation between the two variables, we use the formula for a straight line. Now, we usually depict it this way in stats or machine learning. But what this basically means is y is equal to mx plus c. That's what we have done in our maths classes, and it's not that difficult for us to understand. Just if you just relate, the m becomes theta 2 here. This is called the theta, and it becomes theta 2 into x here. And c, the constant, the intercept is the theta 1. I've made a notation of the two here so that it's easier for you guys to relate, but it's the same thing. Okay, so don't get confused if you see this particular formula instead of this. It means the same. How do we update the values of theta 1 and theta 2? So generally in stats, we have a particular formula where we find out what should be the value, or what should be the intercept, or what should be the slope. But in machine learning, it is done iteratively. So you go on to improve the values of theta 1 and theta 2 and make it more robust, and trying to find the most optimal line that fits the model so well that the predictions are really, really good. Now we are going to look into how it works, but let's see what does it do in the back end. Find the best fit line. We need to have the best theta 1 and theta 2 values. In order to find that, we need to minimize the cost function. Over here, it is represented by j, and the cost function looks like this. So the cost function represents the difference value between the predicted and the actual. So we're going to look into how we go on to do, with a small example, how do we go on to evaluate this particular thing. Since the predicted and the actual difference might have a positive or a negative value, iteratively we square the error to make it positive. So instead of just having a negative value and a positive value, which is going to cut out each other. So basically, if I have a difference of -2, a 0, a 10, and then a -2 again, and a -10, basically the summation of this will be 0. Correct. So we want to find what is the absolute error, right? So for that, we go on to use theta 1 and theta 2, and we go on to use something called the MSE, the mean squared error. So how do we understand if the line is best fit? So we have theta 1 and theta 2, and they are randomly selected initially. So we just select some arbitrary value for theta 1 and theta 2, and we go on to optimize it using gradient descent. And we use gradient descent on the cost function. Now, when the cost function is minimum, we consider that to be the best fit line. Now, what is gradient descent and how do we optimize it? It's a concept where you have the theta 1 and the theta 2 value. You see how good your line fits, and you see, can it be optimized? If it can be, you go on to iterate the values of theta 1 and theta 2, make it more, you redo or reconstruct the values of theta 1 and theta 2, fit it back to the line and see if it did it fit the line better, or did it make the line fit better in the data? And you go on to do this till you cannot optimize it any further. You cannot make it any better. That's what gradient descent basically means. Now, there are a few other ways of evaluating it. There is MAE, which is mean absolute error. So taking the absolute value of the error term, basically instead of squaring it, what I'm asking you to do is just take the absolute value. So if you have minus n, you just take n. Okay, instead of squaring it and then having the double the value, it's basically the same thing. Now you can have the same thing using RMSE, that is root mean squared error. So basically you take the root of the mean square error, and what you get is the same value. So if you have, say, an error of 2 or say minus 2, basically you square it, so that makes it 4. And when you take the square root of it, you're going to get back 2, which is again what you initially had, just with just without the negative sign. So I hope you understood why do we use these and how we go about it. I think you'll understand it better when we do a practical explanation of the thing. You'll have a visual understanding of the same. Now, coming to evaluating the model, like how good the model is, there are a few other ways as well, but we use R squares and adjusted R squares along with RMSE and MSE and all those. So in R square, we first see what is the variance in the error term uh, when we fit a line to the mean of the distribution. So say there is some relation between X and Y, and I just fit a mean line. A mean line is just the mean value and there's a line going across it. So that is the worst fit line. So the error terms are going to be really, really high, and it cannot be higher. So that's my base comparison. Like, it cannot be worse than it. Now my line needs to be better. There is an error term. So we want to fit a line to improve the error. Now, when we fit the line, it explains some part of the variation. So we fit our line to see how much variation was explained by the new fit line. The higher the variation explained, the better the line is. Okay. The value is always between 0 and 1. Again, it's just percentages represented in decimals. So it's going to be between 0 and 1. Now, adjusted R square is a modified version of the same old R square. That has been adjusted for the number of predictors in the model. Now, the adjusted R square increases when the new term improves the model more than it would be expected by chance. It decreases when a predictor improves the model by less than what it was expected. So that's how it increases and decreases. Typically, the adjusted R square is positive. It is not negative. And it's usually lower than the general R square. So those were the two other evaluating methods. Now let's take an example to understand R square. So my mean variation for that line is, so I fitted a line in a particular model, not in a model, in a particular data set, and the mean line error gave me 32, as like 32 was the variation. So over here, when I say var brackets mean, what I basically mean is that it is not the variation of the mean. It's what I'm trying to say is my mean line has a variation of 32. Same goes over here. So my new line that I just fitted to the model, to the data set, that has a variation of 6. Now, when I subtract the variation that is there in the mean line from the line that I just created, I get the R square value. So over here, I have 32 and 6. So 32 minus 6 is 26, and 26 divided by 2 gives me 0.812. That means that the line explains 81.25 of the variation. Now, there is obviously some part that is not explained. So you see the value is not 100%. Now, that's because of a constant error term that cannot be explained by the model. Now, it may be because of some noise, or when I say noise, I basically mean that there is some value that is maybe not taken into consideration,
or there is something that is missing from the data that creates this particular error. Now, this error cannot be removed or cannot be like we can't just say, okay, we just don't consider it and say that our model has 100% accuracy. We do take it into consideration because it's important and the actual values are different from what we predicted. So the error term is constant, but we do explain 81% of the general variation, which is quite a high number. So there are a few assumptions to the linear regression model, and basically when you're fitting a particular model, you should meet these assumptions. So there's a linear relationship. So what it means is that there exists a linear relationship between an independent variable x or variables and a dependent variable y. Now there is also a condition for independence. So the residuals are independent. In particular, there is no correlation between consecutive residuals in time series data. So basically what it means is the error terms are not related to each other. So you have an error of say A, and then you have the next error of B. Just looking at these two data, you wouldn't be able to predict what the error of C would be. That's what independence means. Your data should be heteroscedastic in nature, or you can say it should be there should be heteroscedasticity. That means that the residuals have a constant variance at every level of X. So the data should be more or less within a particular range. So maybe say your highest value is say 200 and your lowest value is 10. Now all the values should be in this particular range. It shouldn't be somewhere beyond this particular range. That's what it basically means. Now, normally the residuals of the model are normally distributed. We are going to look into this when we have the practical for the very same. Maybe then it would be easier for you to understand what data are we looking into and why should it be normally distributed. Now, generally what you could see or you would see when you search linear regression models in Python is that they take a very, very strongly correlated model between X and Y and then try to teach you, okay, so basically you fit a line and you go ahead with the entire thing and you have a very good model. But that's not the case generally. So you have a model which doesn't fit well, but you need to explain why it doesn't fit well. So that's what we're going to look into the practical session. Now, coming to multilinear regressions, it's not something very difficult to understand. So when I have a single line and I say, okay, so I want to predict the value. Now it's going to be the mean value, the average value. So if I have say a range of values ranging from 1 to 10, whatever the mean is, I'll consider that as my values. There is nothing to do over there. But when I have two values and one value is dependent on the other, basically trying to depict a linear relationship. So I basically fit a line. Now, when my data is in 2D, I have a line which is again in a single dimension. Now, extending my data to the third dimension, making it look like a cube over here, and having a regression model which is still in the second dimension doesn't make sense. So basically, when you extend your model from the second dimension to the third dimension, your linear regression line also changes from being a line to a plane. Now, it happens because you need to take into consideration the other value as well. So basically, say you have a variable x and z and a variable y, which is over here, x and y, and z is the height. So say z and x are the independent variables which predict the way, and y is the dependent variable. So just to take into consideration the z value as well, you need to have a plane-like structure so that you are able to consider all the points that are there. Now, coming to the formula aspect of it, you did see this particular formula where you had a theta instead of the beta. You can have a different notation for it as well. But just to understand it, we have beta 0 plus beta 1x explaining why. This was when we had two-dimensional data. But say now I have an extra variable here. Now I have z as well. So I will have beta 2 into x2. X is represented as the independent variables. So I'm saying it as x2. But if you want to understand it in another way, you can also write it as y is equal to beta 0 plus beta 1x plus beta 2z. That also does the job for this particular model. Now my data can have more dimensions, but obviously I cannot represent it in a way I represented it here. Humans are not capable of visualizing data higher than the third dimension, but computers can. So your equation goes on to extend till n terms, n being the number of dimensions. And you also see that the error term is included here, which is obviously unexplainable, but also taken into consideration. Now, I hope you got a basic understanding of linear regression, but even if you didn't, do not worry. When we go on to have a practical exposure for the same thing, you're going to have a better and a holistic approach to this particular model. So that was for the theoretical aspect of it. Let's look at the practical aspect of it now. Now, understanding the theoretical aspect, let's look at the practical aspect in this section. So over here, I'm considering the campus recruitment data contributed by Ben, and it's on Kaggle, obviously, as you can see. And here we have the data set. So it's in the CSV format, and Kaggle gives you the option of looking into the column data over here. You can have a view at what columns look like, what are the tasks that you can perform. So you get a brief description about the data set, about the contributor, how it came about, and usually there are a few questions that they ask. So the task is to try to answer these questions as far as possible. Now you can go into the tasks section and see what are the various tasks that the particular person has put up. So there is a KNN algorithm thing. There is some of the things we can use ANOVA, there's random forest, there's t-testing. But what we are going to do over here is a simple regression. So there are other people who also have contributed to this particular data set. Now you can have a view at all of these codes here. There are various people with different approaches, and I would really recommend you guys to go ahead and have a look at these things. It helps you have a holistic approach towards this thing. Now, you can also look at the discussion forum where people ask questions. You can also ask questions, and there will be someone who comes out and is going to tell you that, okay, you need to go through this particular steps to, tackle the problem that you are facing. And it's quite a good platform to make connections. So you can make connections through discussions, commenting on codes, trying to understand codes. Now there will be some people who comment on your code. Be respectful to them, thank them. So these are a few things that you need to learn once you're on Kaggle. So as I discussed that today we are going to look into the simple regression task. So I've already written the code here. Let's go into the editing section. So once you've written a particular code, even though this is not public at the moment, I can view it because it's my code. Obviously, it says that it's private. And this is how the viewing aspect looks like. So if I make it public, a third person, whoever is looking at it coming from Kaggle will have a visual that looks like this. But when I go into the editing section, it's going to pop up in a minute because it takes some time. So you see that the editing section for Kaggle looks something like this. You can change the name by double clicking here and just change the name. I kept it this because it's quite intuitive on its own. So by default, you will have this section telling you about the compiler and what you should do, what you should not do. But just to jumpstart, you run this particular section, and it will take a bit of time to
start off the session. So we're going to wait. So you see that now the session has started, and you get a single line output over here saying that it's Kaggle. It's basically, it looks like a URL, right? So basically this gives you the URL for the CSV file, and this is the URL that you're going to use to import the data set. So I usually like to make a point of all the things that I would want to do. So I also took up the questions that we saw earlier. I also looked at the regression task. So when you go to task and when you go to simple linear regression model, so you'll get a bit of details here. So whatever I could interpret, I just wrote it in a line or two and I kept it that way. And make a habit of importing all the libraries in a particular pace. You do not need to import all of them at once. So I did not import math, but when I required math, I came all the way to the top here and imported math here. Some I've seen some of the codes where people go on to import datas in the middle or at the end or everywhere they are using it. But it's a good habit to have all the import files here. That's a good habit and it's a good practice. And I would really expect that all the students looking in this particular video do it this way. It's expected in the corporate world as well. Now, having headers is also really important in your markdown file. So I I don't know if you saw that at the in the earlier section in the viewing panel that there was this particular section on the right side which said that importing data or the each and every heading that I mentioned in this particular markdown was mentioned there. We're going to look at it at the end maybe or whenever you can just rewind the video a bit and see that you'll see numeric values like 1, 2, and 3 and all the steps that we're going to perform here. So let's just dive into how do we go about solving this particular problem. So I name my main data frame as main underscore df. Obviously, you can name it anything else, but it's better if you write underscore df. It always signifies that it's a data frame and people understand, okay, so that's what your data frame name is. I go on to import that. I'm just going to run all so that we can see it. Yeah. So you see that I have the shape over here. I'm printing the shape so I can see that the shape is 215 rows and 14 columns. And I have a small view of the entire data set, which gives me a brief description of how the data looks like. Now, to have a general overview of the entire data, I use the info function. Now, I hope you recollected from the pandas video. That gives me a brief explanation of how the data looks. Are there any null columns? So at a glance, I don't see any null columns, but you see in the 13th row in the salary section, I have a few null columns. Now, I do not want to sit down with my calculator and subtract 215 minus 148. What I should be doing as a data analyst is have a different function for it, which gives me the exact number of null values from all the columns. Now, over here, I could identify it and I could write this, but it's a practice for all. It's a practice for you guys to go ahead and do this all the time, so that it gives you the exact number of null columns from all. The null values from all the columns, so that it's easier for you to identify. Sometimes we overlook the particular thing. So you see 215, and it goes on, and okay, like fine, I'll just go ahead. So you miss out on this and then you encounter a problem later in the section and you come back here and go ahead and do the same thing. So just to reduce the efforts, it's best to have this particular statement written. So is null gives you the particular null values and dot sum just sums up all the values that come under each of these particular columns. So that's what this statement does. Now, I want to see if the status is also, does it have some meaning? Does it explain the salary having missing values? So status, if you go on to see, has values placed and not placed.
and I saw that not placed has a NaN value. So I was like, let's see what does it say. So I see that the not placed value is 67. Now I created a separate data frame with just the not placed values, and I saw that the shape of it was 67. Now number of rows with status as not placed, just reconfirming that the data frame that I created was correct, and it came out to be 67. Now, after that, I see the number of rows with salary as 0. Now, that was 67 as well. Now, it's counterintuitive that a person who isn't placed will have no salary. That's obvious, that's understood, but we need to check it. We do not go with logic when we are looking at data. Even though it is pretty much understood, we need to solidify our assumption. So when I assume that, okay, 67 not placed, do not have a salary, I need to prove that whatever I am assuming makes sense. So you need to make this proper and have a small note of it saying that, okay, this is why I'm maybe doing this kind of imputation or this kind of removal and so on. So you see that the status is not placed, and I usually have a section called insights after each thing that I would want to do or each thing that I want to see. So I see that I made an insight over here which says that we see that all rows with status as not placed have the salary as NaN, which is logical. Again, I made a statement like that. And then I say, what is the recommended change? So remove the rows as they will affect the regression line, obviously. So there are various ways of imputing the data. You can set it with the mean value, you can set it with the median value. But over here, logically, the option doesn't make sense. Like a person who doesn't have a job cannot have even a salary of a single rupee, correct? So it's best if we remove that particular, if we remove those rows. So I did that. So that's what I recommended here. And then the thing that I did over here is called segregating. So I segregated all the numerical columns and the categorical columns, and I printed them out for easier understanding. Now I used the describe function on the numerical columns. Now, if I took the describe function on the entire data frame, it will only consider the numerical columns and not the categorical columns. So it's best if you segregate them and then use the describe function. So you see I segregated them and then use the describe function. I see that there are three unique values and so on. The frequency for M over, so this is gender. So I consider if there are only two values, there it has to be M and F. F standing for female, M standing for male, and male has a count of 139. So it's good to have a initial understanding of the data set before going into data visualization, only because you understand what all data do you want to visualize in the first place. So we are going to breeze through the data visualization because I know that these are things that you've already seen in the previous videos. But let's just have an understanding of the visualizations based on this particular data set. So I use the pair plot from SNS. SNS stands for Seaborn over here. That's the abbreviation. So I use the pair plot and plot it on the numerical columns. And if you see, the scatter plots kind of are related. So I see that there is a lot of relation between the columns. So there is a column called SSC underscore P, which is kind of related to HSC underscore P, which is not good because it is the independent columns should not have a relation. Coming to the salary column, because of the outliers, maybe because of the people who have a really high salary, the data doesn't make a lot of sense. So I go on to plot the violin plot, which shows me the distribution and the outliers. So I see that the distribution over here is normal, and then I have a huge number of outliers extending to the positive side. So making the entire distribution positively skewed.
I make the same inferences here, and I also recommend the transformation so that when I do data transformation, I remember it and I go ahead and do that. Now I go on to see the same for the categorical variables and the relationship with the status. So I use gender and then I see what is the status. Are they placed? Are they not placed? I go on to see that, okay, gender, male have a high number of placed people than non-placed people. Now over here, I'm using count plot and it gives me the count and not the percentages. So I intentionally did it because I understand the difference. But if you go on to see here, and if I generally ask you, okay, so could you make an inference of the same? So I would say, okay, so if you are a male, you have a higher chance of getting placed over a female. Now that might be true, but over here, you see that the distribution is not equal, correct? So there are more number of males than there are females. But if I convert this entire uh, graph into percentages, you would see that uh, there is a maybe there is a 70 to 30% chance. So you see that there's a 70% chance of you getting placed if you're a male compared to around about say a 50-50 chance. It's not a 50-50, I would more of say a 60-40, and this is an 80-20. And that's the kind of distribution that there is. So count plots are informative, but sometimes having a percentage plot of the same gives you a better inference. Like the percentages are important, so it's best that you use percentages. But if you are pretty comfortable with the count plots, do go ahead and use that. Now, after plotting each and every categorical variable in terms of the status, like are they placed, are they not placed, so that gives me quite some information that what all fields are important, what all fields are required, and so on. So I then go on to check the correlation. Now you will see that I did not specify the numerical columns. So by default, it takes in the correlation only for the numerical columns. And I see that there is high correlation between SSP and HSC underscore P, which we even realized in the pair plot. This gives us a better understanding with the numerical correlation values. And it is important for you to understand that having collinear columns is not good for your data set, so you need to remove them anyway. So you make a note of all these, you make an insight, you make a suggestion that, okay, you need to remove them. And coming to the data transformation part, you go on to read the missing values and do the logarithmic transformation. We're going to understand what logarithmic transformations are. But before that, I dropped the columns, which I had mentioned earlier. And I also dropped the NA rows, because again, they were not informative. And then I go on to plot the data for the salary. So now I initially, if you go on to remove the values which had 0 as salary and then go on to plot it, you would see something like this, a histogram something like this, and a violin plot which is something like this. Now I go on to use log transformation. So what does log transformation do? Now, log transformations help us understand how helps us normalize the data. So so you see that the data over here is a bit more normalized than this particular data, but let's understand how does it work. So I have a number 12, and you see that it gives me 12. Now, if I have, say, if I do the log of the same, it gives me 2.4848. So it basically gives me the log value for 12. Now, you would say that due to the log value, my values over here also change. So over here, I had a value of
say 2 lakhs or 4 lakhs and then so on. But over here I have values of 12, 12.50 and all that. But it normalized the data, right? And now going back to the theoretical aspect, I said that normalization was important for your data set. So it did normalize the data, but we lost the actual value. So that can be retrieved. That is not an issue. So if you do np.exp, that stands for exponential transformation, you see that you get the value back. So you predict the values based on the log, you predict the values on the logarithmic values and you get the log value, and then you go on to transform it back using the exponential function. So you basically you're trying to make the values normalized, and even though it changes the values, it doesn't exactly it's not like you cannot retrieve back the information, just that. So if I have to explain it in a more layman way, basically you're just trying to compress it so that it becomes normalized and you can use a linear regression model, just that. Now I still see that there's this tail and it has outliers, so I need to work on that. So I do a outlier treatment and I use this particular code where I have percentiles. Now remember when we were talking about quartiles and percentiles, I basically said that quartile 1 is one third, or it represents the, sorry, 1/4. Yeah, I'm sorry, it's 1/4, and it basically represents 25% of the data. Now Q2 is the median, which represents 50%. Q3 represents 75. Now the interquartile range is Q3 minus Q1. So if I go on to see the values which have a higher a value that go beyond the quartile range, I need to use this particular numpy function where I use np.where. And on the transformed data set for the salary column, I go on to check if the value is greater than Q3 plus 1.5 into interquartile range, and then transform. I just take on the index and add it here. Now, when I go on to see this, it basically says that so it basically prints the upper values, and you see all the upper value ranges come here when I print it out. So all these indexes have a value that is beyond the third quartile, and I want to remove it. And for the lower bound, there are no values, so we even did not see here. But sometimes there are values on the lower bound as well, so I just kept it here for easier understanding and for also checking it out. Now I go on to remove the outliers. So my old shape was 148 rows and 11 columns after all the data transformation that I did earlier. After removing all these columns, I go on to have a shape of 139 and 11 columns. So now I go on to visualize the salary column again. So you see that the data is perfectly normalized now, right? So I have a histogram that is more or less normalized. I can see a violin plot that is also normalized. I do not have outliers, but the scatter plot doesn't give us a very positive view of it. So the scatter plot is pretty scattered, and it is not heteroscedastic in nature, which is also a condition or an assumption that we make that for, okay, if I'm using a linear regression model, so that is a condition that you need to satisfy. So let's see what is the effect of it. Now, I would want to have a error, not exactly an error, but a misfit, so that I can explain why the linear regression function misfitted. So before that, I need to label encode the values. So each and every machine learning model doesn't understand M, F, and all those categorical columns. So you need to label encode them. Sorry. So you need to label encode them. So I use the label encoder package from sklearn, which is here. Let me just highlight that for you. Sorry. Yeah, I use the pre-processing package of sklearn and abbreviate it as pre so that I can easily use it. Coming back to the label encoding part. So I label encode the entire thing, taking the columns from the categorical columns and then label encode each of them. And then I see how does it look. So it looks something like this. I see that all the numbers are the way I wanted them to be. So that's fine. Now, this is kind of the end of the data pre-processing. Now I go on to do feature selection. Now, once my data over here is also in the numerical format, I can use the heat map or the correlation thing to, or even on the categorical columns. So that gives me intuition of should I or should I not keep that particular column. So I see that the status over here is completely white, which means that it has only a single value. Now remember, we removed all the status values that were not placed. Now we removed that, making it constant. So having a value that is constant throughout the data set doesn't make a lot of sense. So we're going to remove that. And I mentioned that here. Now removing HSC underscore B, as it is collinear to SSC underscore B and has a lower correlation with the salary. So let's see where is HSC underscore B. Okay, this is here. So it has a 0.64 correlation with SSC underscore B, which is not good. And it contributes 0.045 to the outcome variable, and SSC underscore B contributes 0.11. Now, I can see that there is not a very high correlation between salary and the other independent columns, but I'm still going to select the one which have a higher correlation. So in this case, just because these two are correlated, I need to select one of them because one explains the other, and the higher correlation with the outcome variable is a better choice to keep. So I keep in SSC instead of HSC. Now I also remove specialization workx HSC underscore S, as they have a really low contribution to the salary column. So you see that specialization has a negative of 0.67. Now, I'm not removing it because it has a negative relation, but because it has a really low correlation. It is lower than 0.1, which is really, really low. And 0.1 is not my threshold. Ideal relationship would be anything that is higher than 0.5. So you see that 0.64 is high. It's actually good, but I would really wanted it to be with the salary and not with the independent variables. So that's not there, and it's not an issue. Well, it is in some way, but we are going to look at it. So I also see that degree underscore T has a relation with SSC underscore S. Now I go on to remove HSC underscore S because it has a very low correlation. So that also takes care of degree underscore T. Now, after transforming it again, I go on to see the correlation with the salary and the other with the other columns, that the remaining columns. And I see that the remaining columns that I have taken into consideration are these 5 columns. Now, these are the 5 columns that are my initial selection for building a model, and let's see what the model does. So I need to split it into train and test. So I have my X variables that are my independent variables, and I also have, and I segregate or separate my Y variable into this particular variable. Then I use the model selection train test split function, which basically splits my entire data into X train, X test, Y train, Y test. So model selection is a package from sklearn, again imported earlier. And basically what I say that these are my 2 variables. So these are my independent variables and this is my dependent variable. I see that the test size that I have used here is 0.20, which basically means that I'm using 20% of the data for testing and the remaining 80% as my training. And I also do a random state, which basically fixes the particular selection for the training and test set. So remember, even when we were doing random numbers in NumPy video, we used something called the seed, which basically generates random values, but also fixes the values to a particular seed value. So this is more of like the seed value for this particular function. Now, after splitting the data, I just have a look at the shape. The shape is over here as seen here. Now, I go on to uh, change the y-test values, like because I had logarithmically transformed the data, I needed to change it back using the ESP function. And I told you why it works earlier. Now, I needed to change that because I have to test it properly, even though it makes the graph really similar, but I need to test it in this way. Like I need to have an actual value instead of a logarithmic value. Now, in the first way, I just built a general linear regression model. I use the linear regression function from sklearn and uh, use a variable LR. So I fit the particular model xtrain, and like I pass in the values xtrain and ytrain to it. Now it takes in all the xtrain values, looks at the values and looks at the ytrain values, identifies the pattern and tries to fit the line and gradually tries to make it optimal. Now after the model is done, it's going to give you an output something like this, and I want to test the model. So I use a variable called yPredict, and I use the models.predict function to predict the values from xtest. And after the prediction is done, I again go on to use the exponential function to see what the actual yPredicted values are. Now, going back to the theory section of this particular thing, I said that there is something called the mean squared errors. I'm going to look into that. The root mean squared errors, we are also going to look into that. And there is a particular function that you can use, but I just used the math function and did the square root of the same to have the similar values. Now, after that, we also go on to see the R squared value. Now, looking here, we see that after testing, my mean squared value was really high. Now, just looking at the mean squared value, it is quite difficult to interpret. Did my model do good or did my model do bad? Because the values were in lakhs, correct? So it is quite difficult to understand. Now, taking the square root of the same, it says that on an average, the mean value was 46,000. Which is not great, to be honest, but that's what we have and that's what we need to make do with. Now, coming to the R squared value, I see that the particular model can only understand, or can only express 0.085, that is almost 8.5% of the variation in the values. So basically, if I have the mean value and I just substitute the salary's mean value, and I do not fit a line, I just fit the mean value randomly, it is just going to have accuracy, it's just going to be 0.8 sorry, it's going to be lower 8.5% than the line that I fit here, which is not great. If I had, say, a 0.85% over here, which says that I actually explain 85% of the variation, it's actually good. But over here, I specifically took this data set because it has a very low correlation and doesn't make a lot of sense. But we're going to see how we can optimize this particular value and try to make it better. Now, there is this process called stepwise regression. Now, what stepwise regression basically does is, there are two ways of doing it. There is forward selection and there is backward elimination, or backward selection, if you have to put it that way. So the names are again counterintuitive, but forward selection means you take a particular column and check if that goes on to increase the accuracy. And if it does, you're going to keep it. And backward selection is basically eliminating that particular column or that particular feature and then checking how does it affect the accuracy. Does it reduce it? Does it increase it? Now, over here, I've used a method that takes in both the steps. So I'm using all the columns and then reducing one. So I'm doing backward elimination. And once I'm doing backward elimination, if I see that the accuracy decreases, I'm doing forward selection and getting that column back into consideration. So I hope that you understood that how I'm getting these values. The functions are pretty much like I cannot explain you how R2 score works. I've already explained how R square works, but this is a particular function from again, if I'm not wrong, sklearn. Let's just cross check that. You see that, yeah, it's from sklearn metric R2 score. The mean squared error is also from sklearn metric. So that's there, and you just import them and use them. But it's good to understand how do they work. So we covered that in the theory section. Anyways, so coming back to the stepwise regression, I basically create a def accuracy function here, which is just a copy paste of whatever I've done here, making a train test split and so on and so forth. So if you see, I've kept the random state same here, and I've also tested it out using all the columns, and I see that I have the same value. So I see that I've got 0.0856. Now I've reduced it to 4 decimal places because I don't want this high number of decimals in my particular accuracy. I can make do with 4 decimal places, and that's what I've done here. So I do everything same in this particular function so that I can just concentrate on selecting or removing the columns. So testing out the very same thing as we did earlier, considering all the columns, I have a R squared value of 0.0856. Now I remove the gender column and see what happens. So these are all the columns that the current model is working on, and I print the columns so that it's easier for people to understand who was going through the code. And I pass it to the accuracy function. Now, when I pass all the columns to the accuracy function, it goes here, it checks the list, and it uses transform df underscore one, and all the columns that I've passed here as a parameter is considered here, and all my independent variables are basically in this particular column. Now everything else remains same. You split the data into 80-20. You have the same random states. It's going to split it in the same way. And you go on to use the exponential function on y-test, build a model, fit the model. Then you go on to predict using the model, and then again use exponential function on the prediction so that you get the actual values. Yeah. So you use mean squared error here, and it's the same thing. I'm printing the same thing here, mean squared error, root mean squared error, and then R squared till 4 decimal places. So that's how you go about it, and it gives you the same values as 0.085. Again, just explains 8.5% of the variation, which is not good. Now I go on to remove gender and see what happens. So after removing gender, the value actually decreased. So I make a note of it that keeping gender as R square value decreased. And then I go on to remove SSC underscore P, and I go on to see that the value actually increased. So my base percentage is 0.0856. After removing that, I get accuracy of 0.0886, which is basically 8.86% of variation that my model is explaining now. So I go on to remove SSC underscore P. Now I do the same for SSB, and I see that the thing again, the accuracy or the R squared value decreases. So I do not remove it, I keep it. I go on to remove degree underscore t, and I see that uh, the accuracy actually increases a lot. So I'm definitely going to remove this, and that got removed. And now I'm explaining 10% of the variation. And after that, the last value is e test underscore p, and that reduces my r squared value. So I'm going to keep that. So now I have a separate section. I always make a separate section for results and conclusions so that people can just come here and understand what is the final outcome of the entire search that I've done, or the outcome of the entire thing that I am trying to do here, so that they can relate easier when they go through the top section. And it's a good practice, so you should do this as well. So what I did over here is, now I have all the columns that I have selected, and after deselecting and selecting and reselecting, these are the columns that I have. So I go on to pass it back to the same thing, and it shows me the columns here, the column values that I've considered, the mean squared error, the root mean squared error, and the r squared value. So it basically explains 10% of the variation, which is bad. But if you go on to compare it to the initial uh, r squared value, where we had just 8.5% of variation that was explained, it is better. Now, I would like to re-explain myself by saying that we used this particular data set specifically to explain why heteroscedasticity is important, why the data needs to be normalized, and various other things. So it's not good to have a 10% variation explanation. It's good to have somewhere around 70 to 80% of explanation. If you have somewhere around 90, 95, it's amazing. But it's best to have it somewhere around in the range of 75 to 85. A 10% variation is not good, but it's the best that we could do after all the evaluations and methods that we. Now, making an insight of the same is also important. So it was prominent from the scatter plot that there is no specific trend that the dependent variable follows, so that we could see. Now, using the stepwise regression, filter the columns such that the R-square values increased. So we used the stepwise regression to filter out the columns. The objective was to understand the data and model on it in the best way possible, which was achieved. So again, I mentioned the objective so that it's easier for people to understand. So the main objective was to understand what the data is and try to fit a model, not to make it way more robust, but to have the best combination, or to test out each and every method and have a model that is best for this particular data set. And that's what we did. So I hope you understand the various aspects that we did here. Coming to the settings aspect of Kaggle, you see that if you want to share the particular data, you can share it using this particular function, and you will have a button over here which says save the version. When you press save, it basically pops up something like this, and you see that is the 5th version now. Now there are two options that you get. You can either use the quick save version, which doesn't run any section of the code and saves it the way it is, or you can have a save and run all commit. Now I'm not going to save it, but when you save it, okay, I'll just save it. How does it matter? This is the version 5. If you want to overwrite a particular version, you can rename it here, but I would prefer that you make a new version of it every time. So when I press save, it's going to pop up something like this. And it says that the linear regression on placement data is running. So it's going to run all the cells, and it takes in quite some time. So after everything is done, it's going to say that it's saved. So if you have an error somewhere in the middle, it's going to show that, and it's going to say that you have an error here and you're not able to save it for the very same reason. So that's why I'm saying, if you have an error in the middle and if you want to save it and maybe, go ahead over it the next day or the upcoming day, it's best that you use the general save function. Just a quick save should do the job. And once you're done with the entire thing, it's best that you use it. So whenever you're going through Kaggle competition, it's important for you to do save and commit, and then go on to save your results in a particular data frame. Like, go on to update the data frame and then submit it. That's how you participate in competitions. So you see that this was successful. So what this means means is that all your code is correct, and you can close it without worrying about it. Now let's see why I did the naming section like that. So table of content, this is what I was talking about. You see that I made headers in the middle, which is quite important. And this is why I made them. So when I just click on importing data, it goes on to my importing data section, and it tells me that each and everything that is under this particular section is for importing data. So it's easier for people viewing your code, and it makes it more simpler, more robust, more understandable, explainable, which is important again. So coming to the results and conclusion sections directly, I can see, okay, so this is what the model did at best, and this is what my insights and inferences were. So once I'm satisfied and okay, so this is what this particular person is doing, and I would like to go through what he has done, I go through the other stuff. Okay, what are the data transformations that you can directly go through the particular sections without scrolling up and down, which is quite irritating. So reducing the number of clicks makes it more appealing to the public, which is also necessary for you to be viewed by a lot of people, and people coming to your code, looking at it, commenting on it, giving you suggestions, you trying to explain them what you have done. So again, everything boils down to what is your basic understanding of the code and networking. So this is a good platform to have better network presence. So I hope that you understood what we have done here, and you're going to try it out yourself. We're going to look into the classification tasks in general. And yeah, this was a basic regression task. And again, I would like to repeat myself that this is not the ideal percentage that you get, but I wanted to show you that the data over here was not heteroscedastic in nature, which is again not ideal for a linear regression task. So this is how you go about it, and the data is not going to be highly correlated in the real world. So it's best that you know all the practices that you can make to make your model more robust and the best for the data. So yeah, that was all for linear regression. So in this video, we're going to look into the various classification algorithms. So we are going to look into multiple classification algorithms and what are the various types. We're going to evaluate them through and a few other additional informations. So we start off with logistic regression. Now we already did linear regression, as the diagram over here shows. A logistic regression is just an S-curve. Let's see what we have. So logistic regression is basically a supervised classification algorithm. In this analytical approach, it depends on the finite category. You can have, well, we have a finite number of categories. We do not have a continuous variable. You can have, say, maybe 5, 6, 10, 20, 50 categories, but it needs to be finite. So you can have either A or B, which is a binary regression. It will be a binary classification problem. Or you can have a range of finite options where where the thing ranges from A, B, C, D, and so on. And it will be a multinomial regression. So these are the two types of predictor column values that you can have. It is used in statistical softwares and machine learning software, obviously, to understand the relationship between the dependent variable and one or more independent variable by estimating the probability
by using a logistic regression equation. So you're not going to look into the equation and make things complex for us, because Python automatically does take care of the equation. But we're going to understand why we are not using linear regression. So firstly, we need to understand that the value ranges from 0 to 1 because of the very obvious reason that the probability values will always be between 0 and 1. Now, why do we not use linear regressions and use logistic regressions? Now, the logistic regression value will always be between 0 and 1. Over here, you can see that the values that are the green dots here, those are the values. Now, for this set of values, I might just fit a line and can get values from like values in between 0 and 1. But say I have a point that is somewhere here. Okay. Now that pushes the line and gives me a value that is going to be somewhere here. Okay. If I just extend the line, it's going to be somewhere here. Okay. Now you see that the value is beyond 1. Now we know that the probability value cannot be beyond 1. So that's why linear regression fails in this particular classification problem. Now coming to logistic regressions, you see that the value starts from 0, goes here, it is somewhat 50 over here, and then becomes 1. Now that is 100%. So it gives you the value for a given particular point, that which class does it belong to. So for considering this point, we say that it belongs to class 0, considering that the line over here belongs to 0, or say maybe it is a bit higher than 0, say it's say 0.1. So it's 10%. So I'm confident that it's going to be over here. Now, as I go above, it basically says that the value over here is somewhere around 0.8, and it's going to be in class 1. So anything below 0.5 is going to be over here. Anything above 0.5 is going to be here. Now that's how the classes are distributed. So that was about logistic regression and how it basically works in the backend. Let's look at the evaluation matrix of it. So how do we evaluate the logistic regression? So now predicting is understood, like, okay, that's how the classes are distributed, but how do we justify our classification? So there is something called the confusion matrix. It's a good way to look at the correctly identified classes and the misclassified classes. So using the value from, there is another way where you can look into the accuracy, but let's just look into the confusion matrix first. So these are the predicted classes and these are the true values. So if my particular model says that yes is positive and the actual value or the true class is also positive, it is correctly classified and it is referred to as true positive. So I said that it is positive and it's actually positive, so it's true positive. But in a case where my class goes on to be in the negative section, I say, no, it doesn't belong to that class, or it belongs to the 0th class. So it's basically false positive. Okay. So it actually was, it actually did not belong to that class, but my predicted value said that it belongs to that class. Okay. So it's false positive. Now this is also called a type 1 error. In some cases, type 1 errors are, are more dangerous than type 2 errors, which we are going to look here, which basically says false negative, where the value was actually negative, but it was, the actual value was positive, but the predicted value said that it was negative, which is a type 2 error. Now, in a case of, say, let's taking our judicial system into consideration, we can say that if a particular person is not a criminal and is given a verdict that he is a criminal, he is going to fall into this particular category, which is a type 1 error, which is a more dangerous error than the type 2 error here, where the person was a criminal, but was said, okay, he is not. So I hope you understand the difference between the type 1 and the type 2 in this example. But yeah, just get this point that these are the two misclassified classes. Now coming to the last classified classes, which is obvious, which is pretty intuitive, that it's true negative, that the point was negative, and it was also like the true point was also negative, and the predicted like our model predicted negative as well. So it gave us a true negative value. Now the accuracy is also calculated in the following way. So I have these two class values. So I add them up and then divide it by all the particular values. So basically it's going to be like how many, it's a simple thing. Like if you go on even if you go on to consider a normal exam that you give, you have say 10 questions and you answer 3 of them correct or 5 of them correct. So you're going to get 5 out of 10, right? So that's what we are doing here. So these are the two things that we got right out of the entire thing. We're going to look into a practical example of this, and I think that will make it a bit more clear there. But let's see the additional informations that we have. So there is something called stratified sampling, where say you have a class imbalance, and it's best to use a stratified sampling there because it makes the data have the same proportion as in the training as well as in the testing. So what do I mean by that? Say that my actual data looks like this, where the 0th class has 100 records and the class 1 has 50 records. This is a binary classification problem where the classes are 0 and 1. So there are 100 records with the class 0, and there is there are 50 records with class 1. Now, if you see that there is a 2:1 ratio that is there in this particular case. So if I am doing stratified sampling, what it obviously goes on because we are doing a sampling technique, we are using a sampling technique, it obviously will take the values randomly, but will also keep in mind that the proportion that the actual data set has is 2:1. Now for my testing data, it needs to maintain that particular uh, proportion. So consider that my test size is 20%. So 20% of 100 is 20 and 20% of 50 is 10. So you see that it still maintains the 2:1 ratio. Now, why do we do this? Say my training data or testing data has a lower number of values from a particular class. Now, because the model sees lower number of classes from a particular class, it goes on to predict the other class higher. What do I mean by that is, so if I say that there's a distribution of 50-50. So taking a random sample will lead me to a data set where the probability of having equal distribution is very high. Okay, so my training data will have a similar distribution. There are 50, say there are 20 records of uh, the 0th class and the 20 records of class 1, which is fine. And again, there is 10 and 10 records of class 0 and 1 in the testing thing. Now that's fine because the data is trained on something similar, like the data is trained on 0 and 1 classes, which is fine, which has equal distribution. It's tested on the very same, but consider that the classes now have imbalance. So this is a class imbalance example where the records are not equal. There's a 50. So we basically we don't have a threshold exactly to say that okay, now we have class imbalance. But when there is a very high level of difference between the records, we basically say that yeah, there is class imbalance that we can see. If it would have been say 190 or 180, it still would have been okay. But 150 is quite a lot. For every 3 records, 2 of the records belong to 0 and 1 of the records belong, which is so every time my model sees a particular record, okay, I'll just set a 0 to it. Now, even with putting 0 value to say so considering an example where I'm just taking 3 records, now I know that 2 of them belong to 0 and 1 of them belongs to 1. If I just put randomly, if I just have a random function, not even a model, and just fit in zeros, 0 to all the records, all the 3 records. So I still have an accuracy of 66.66. And I haven't even used a model.
just because I'm fitting the majority value over there. I hope you got the concept of class imbalance, stratified sampling, logistic regression, and confusion matrix. I think this thing will be clearer when we go on to use the data set and fit a model to. So we are using the very same placement data set as we used for regression. You might be confused like, okay, that was a regression task and how are you using a classification? Let's look at how do I go about it. So it's the same thing. I run this particular section code that is already given to me in Kaggle, and I get the CSV file. These are the few libraries that I've imported, and we'll come back to it as and when we encounter them. So importing the data and looking at the head values, going down to the info section where I look at the distribution of the data types and the various columns. Okay, fine. So what are the sum of missing values? I see that salary had missing values. Even in the previous code, we saw that salary had missing values. And you're going to see the distribution of the place and the non-place records. So this is going to be our predicted value. So now we do not have salary as our Y. We have status as our Y variable or the dependent variable that we're trying to predict. So does all the rows with missing values have status as not placed? So we see that, yeah, it does do that. But in this case, we are not going to, remove the records because we are dropping the salary value. Let's see. So we see that sorry, my bad. That all the rows with status as non-placed have the salary NaN, which is logical, obviously. So recommended changes, drop the salary column as using that we can predict the place status with just an if statement. Now, why is that? So if I just going to say if the value is not null or NaN, the status is going to be 1 or else is going to be 0. And I'm just using an if statement. And my model accuracy will be 100% because if you're going to see here, all the null values are basically not placed and all the values which are not null are basically the ones that are placed. So as it is, we are not going to use the salary column because it's a continuous thing and we need to bin it and then the various other things that we need to do. We don't need it in general. And again, you cannot use imputations of any kind to fill in the missing values as well. So we are just going to drop the salary column. So that solves the problem of the null values as well. So now I'm just distributing the numeric columns and categorical columns. I'm basically using the select D type, and then I'm using the exclude parameter from that. So I'm excluding all the objects. So anything that is not an object is numerical according to me, considering that this is the data set. It's not always true, but for this we just have float object, and I don't think we have an end. Yeah, so that's that. Yes. So, and here I include all the objects. So basically anything that is of an object data type comes into the categorical column. I print them out to have a look at it. I'm satisfied with them. I want to describe the thing to see the minimum value, the maximum value, the quartile values, so that I can, maybe bin them. Now I'll tell you what binning is. I also describe the categorical columns. I'll tell you binning when we come. Yeah, so here we have the pair plot, just see the distribution. We looked into this in the previous video, so I'll just in a sense skip that. Same things that we mentioned earlier. Now coming to the categorical sections, yeah, we saw the distributions as earlier, it's the same. There's nothing new in the distribution here. Now coming here, we see that the status is more or less normal. So we are taking into the numerical columns, right? So numerical columns is more or less distributed. I see that salary is skewed, but we're going to drop that, so it's fine, I guess. Yeah. All the columns seem to have a normal distribution except the salary column. No outlier treatment required as we are going to drop the salary column. Typos. Yeah. Now we're going to do the data transformation. Now here we are dropping the salary column as promised, and we see the first table look. What does the table look like? The transformation df1. I'm going to so basically I make multiple data frames for each transformation, because there might be some cases or a model might work good on a particular transformation and may not work good on another transformation. So to identify such transformation discrepancies, I basically make multiple transformation DF. So you will see that I have multiple copies of the same with some changes here and there. We're going to look into that. So numerical to categorical, that's what I need. After I remove the salary from the num columns list, I have these as the remaining columns. And I'm going to describe it again just so that it's easier for me to bin. So I see that these are the ranges that I can bin them into. What do I mean by binning? I basically am trying to convert the continuous variable into a categorical variable. Now, how do I do that? So say if I have values ranging from 0 to 100. Now I can have values ranging from 0. I can have values like 0, 1, 3, 7, 10, 50, 55, anything. But it doesn't give me a lot of information. So what do? I just bin them so that I can know which category does it fall into, and if that category is related to the status over here, the dependent variable. So taking the example again, so if I have 0 to 100, now I want to know how many bins do I want. So if I say if I want to make 4 bins, the logical binning technique will be 0 to 25, 26 to 50, and so on till 100. Or if you say if you have 5, so you want to bin from 0 to 20, 21 to 40, and bins of 20, and you go ahead that way. So it depends completely on you how many bins do you want to make. Let's see what I've done here. So I've made a function getBin, which takes in a parameter the data frame, the column name, and the number of bins that I want to make. And what I'm doing is I'm finding the lower limit and the upper limit using the min and the max function, which we saw here. So taking say SSC underscore P as the column for an example. So the min value will be 40.89 and the maximum value will be 89.40. What I do is I use the bins, I make a variable bins and I use the linspace function. Now, if you do not remember this particular function, I highly recommend you to go back to the NumPy section, and it basically creates a list of all the list that I want, but I do not know the step size. So I know how many splits do I want. I know what is my range, but I do not know the step size. That's when we use linspace. Okay. And if I know the step size, we basically use range. In this case, we'll use linspace. So number of bins plus 1, I'll tell you why. And this is how it is. So let's take an example. If say I remove the number 1, okay, I'll just let it be and let's see what does this do. So it's basically saying that the first bin is from 40.89 to 57.06. The second bin is from 57.06 to 73.23, and from 73.23 to 89.4. Now, if I do not do the plus 1, what it is basically going to do is going to make the lower number of bins. So sorry. Okay, I think I've done the data transformation, so it did that. Let's just run the entire thing. So while it is running, so now because the bin number is lower, we are going to have a bin. Yeah. So see, if you're going to say 3, it's going to take just 2 bins now. It's going to make the one bin is ranging from 40.89 to 65.145, and the second bin is from 65.145
145 to 89.4. Now, when I say the bin number, it basically gives me the number of values in the particular list. So to avoid that, I need ranges. So I'm going to stick to what it was and to rerun it again. Sorry for that. Now, moving ahead, I think you understood what the get bins function does here. This is a user-defined function. You can also make functions as you go ahead. So what I'm doing is I'm taking the num columns and I'm passing each and every column. I'm using the pd.cut function to make bins. So this is how you make bins. So I'm taking transformation data 1, ith column. So it's going to take SS, CNS, P, and so on. In the first case, I get the bins from this particular function by sending this. I send in 2 and I'll get 3 as my output. 3 bins, yeah. And then I go on to, no, sorry, I'm going to get 2 bins because I'm sending the number 2, yeah. But it's going to make itself 3 over here. Okay, so that there are 3 values, but there are 2 bins. So consider that this is not there. So my first bin will look something like this, and the second bin will look something like this. Yeah. So I just label them 0 and 1. So basically, what I'm doing is I consider that I'll just distribute everything into 2 bins, each and every numerical columns in 2 bins. And if you see that now after converting this, I print the information and I also print the data head value. So we'll just set the head values as 0 and 1 as we have mentioned here. And if you see the information section, you see that they all are category now. They were float initially. See, they were float value initially. Now they're all category. So I want to change them into int because my model will not consider categorical or object variables. So we need to make that into int. So I did that for all columns and now it's int. So we see the distribution of the values accordingly, which is I will leave this section for you guys to understand. So this is your homework where you basically make insights. Okay, so that's for your homework here. You need to make insights based on these graphs. So basically, you'll have 5 sets of insights. You'll have an insight from this graph, this graph, this graph, this graph. So you just mention them here in the very same notebook as you want to. If you're doing it on your own notebook side by side, amazing. You should just make insights as we discussed that you need to have insights for each graph. So just make a few here. And now we do something called label, and this should have been in the additional slide as well, but nevertheless, let's look into it. So as I mentioned that categorical columns or object columns cannot be considered into the model. The model will only consider numerical values. So I need to change each and every categorical column into a numerical column. So initially, if you want to see even my status column had, placed and not placed. Now it is zeros and ones. Now, how did that happen? So I use something called the label encoder from the abbreviated. So what did I abbreviate pre as? I abbreviated pre as sklearn.preprocessing. So sklearn.preprocessing has, has something called label encoder. So what does a label encoder do? So considering the status example, I had placed and not placed. So it's going to take placed as 1 and not placed as 0, or the other way around. So it's going to convert it into an integer value, but it does represent the same thing. So my 1 will represent what my placed value did, and my 0 will represent what my not placed value did. So I'm doing that label encoder.fit transformation. I'm fitting as well as transforming at the same time. So that does it here. taking the categorical columns into iteration and passing it in here. That's pretty logical. And then I'm using the head function to visualize the thing. So it's done here. Let's go ahead and see what else we have. Yeah, now we're going to do feature selection. So we have something called the heat map. I think we have looked into this earlier as well, where we put in the correlation plot. Now, I'm not using the correlation plot exactly, but let's see what do they show. So I have the status here, and it says that SSC underscore P gives me a correlation of 0.51, which is good. I have a 0.36 for HSC underscore P, which is good again. 0.29 for degree underscore P, 0.28 for workx. Did I mistake that? No, I didn't. So good enough. So I have 4 variables at least, which I can see that, okay, they do give some information. That's fine. But again, if this would have been a real life scenario, if this would have been a regression problem, anything below 0.5 is not considered. So basically everything apart from SSC underscore P would have been completely useless. That's what generally the threshold is, 0.5 to 0.4, not beyond that. But so this was the basic thing. I see that there are a few multi-collinearity as well, but again, a classification problem, we can just avoid that. 0.6 from ambiguity and SSC. Yeah, we can remove them as well as we go. Let's see what we do. So I use something called mutual info classic. So it's going to give me the mutual information, and let's see what it does. So I have the mutual info here. So this is the basic variable that I'm assigning the mutual information values to, and this is the particular this is the particular function that I'm using. So mutual info underscore classes, and I'm dropping the status column. So when I say axis is equal to 1, basically the axis is 0, which basically means the row. And when I say 1, I basically mean the column. So I'm dropping the column for my x variables. So what basically I mean is, so these are all my x features. And now this this is my y column, just the status column. So I'm not destroying the transform df1 thing. I'm making a clone of these over here. I'm just passing the values over here. Okay. So I hope you understand that what is x and what is y. So x are my independent variables and y is my dependent variable. So I'm just mentioning them here so that my function understands. After that, I can see that these are the values for each of the columns. So most of them are 0. So it will range between 0 and 1, considering that they are probability. Now, this is not very intuitive. So let's just look at the serial values. How do I go on to do that? So I basically say that it's going to be a series. So I use the pd.series function, send the mutual information there. And I go on to say that mutual info has indexes. And you can just drop the status column and say that all the columns that belong to transformation df apart from status will be my index. Now, after I supply that, I basically go on to sort the values in the descending order. When ascending is for, we basically have descending. Okay. Now, doing that, we go on to see SSC underscore P, HSC underscore P, a lot of tongue twisters there, have the highest values. Now, coming back here, we see something similar. Okay. Remember 0.1, 0.51 and 0.36.
And we had specialization. Let's see what does that have. Now specialization had a 0.25, a negative 0.25, which is also good enough. It just says that it has a negative relationship, but it's fine. It's still good enough. Now workx had a good relation here, right? We saw that workx had a good relation here. It had a 0.28, but the mutual information that we got is not that great. But okay, it's fine. We saw that the others did not make sense, so mutual information function does give us the same information. But you can use either of them. Okay, you see that they more or less convey the same message, even though the values are different. It basically says what probability, what is the probability that, what is the percentage that this is a good variable to use in a particular function. This is what is defined, but it's fine, not an issue. Okay, so let's go ahead and, I have mentioned the insights here. In this case, we can't take the columns that provide some info and drop the ones that don't. Generally, we take the top end columns and defines the number of columns that the user wants to take into consideration, generally 5 or so. Here we do not have that many number of columns, so 10 is out of an option. But top 5, yes, we can do that. And let's just also make a data frame with values that have even a single amount of significance. So anything below SSC underscore B can be removed. But let's see what are the various combinations that we're. So these are the non-zero mutual information values, and I've mentioned them here. So you can see that still status. Sorry, oh, I've added status as well. Sorry, at the end. Specialization, correct? So specialization, work it. 1, 3, 6, right? 6. Okay. We have that, and mention them here. So now my transform df2 will only have the selected columns. I remove the others, and I also make a transform df3 with the first 5 values. So that is also fine. I just make a separate column of the transform df3 and I drop the status and I get the top 10 values. So what have I used here? It's the select a best. So select a best is another function that helps me select the top 5 or the top best records. So that is the one thing that I've used here. And what I say is, so I have the mutual information class of function that I want to use, and I want the top 5 from that. And I'm fitting the transform df3. I'm dropping the status again, so defining my x and my y. And on the basis of that, I want to see what is the list of the top 5 columns that I use. Now that doesn't make a lot of difference, but you're going to test that out. Basically, we do take the top 5 or the top 10. That's the only reason I have done that. Just so that you know that this is a process how you go on to find the top 5 records. So you basically fit this in, the select a best, and that does the job for you. Now going ahead, after selecting the top 5 records and appending the status back, I now have the transform df3. We can have a look at it. This is how it looks. So just making a note so that you understand. So my transform df1 has all the columns. My transform df2 has the columns with some mutual information. So if there is a column which has any amount of mutual information, I'm taking that into consideration. And my transform df3 has the top 5 columns such. So moving ahead, now I've made the column selection. Now again, I know that I going to repeat myself quite a lot, but always document your entire have a heading section, have a subheading section. It is good to document yourself that. So okay, so now I'm performing my transform df1. So I've looked into the train test split before, but remember we looked into something called a stratified Y. Let's go back to see the graph. I think the graph will give us a better idea.
where we had plotted. Yeah, so you see that it does have a class imbalance here. It's almost like 50%. To be more accurate, just look at the print statement that I did here. Yeah, so it has approximately 150 records and it has approximately 70 records. So almost half. Almost half. If this would have been 140 and this would have been 70, would have been exactly half, but it's kind of half now. So again, so there is a class imbalance, so we need to look into that. There are other ways of handling class imbalance that we look at the end after we have discussed all the models. So that's how we're going to compare the accuracies. So what I'm doing basically here is I'm using the logistic regression function from linear models inside sklearn, and I'm making the train test split. The common thing that we do from model selection, train test split. I'm defining my x variables here, my y here, mentioning my test size to be 0.25. I'm making my stratified as y. Stratified as y means basically I want my data to y basically signifies yes, and I want my data to be stratified, and I'm just setting a random state as 40. So when I run this, I basically get 0.7963 as my accuracy. So okay, how am I calculating my accuracy? We can do it manually. We'll check it out manually as well, but let's just look at it here. So I'm basically using the accuracy score function. Now, where does the accuracy score function comes in from? Sorry. Yeah, the accuracy score comes in from sklearn metrics, and it gives you the accuracy of the particular model. Now, we discussed how the accuracy works, but just to revise that, it's basically the correctly classified classes divided by the total number of, the correctly classified number of rows divided by the total number of rows that you use for testing. Now let's look at the confusion matrix. So I'm using the confusion matrix function here. Let's look at where does that come from. So that is easier for you to write that down. Confusion matrix comes from sklearn metrics import. You just use the from and import function like this. So from sklearn metrics, you import confusion matrix. Okay. So that's how you import that particular function. Now, how do we use that? Let's come back to that. That's it. So yeah. So I have the confusion matrix here. I'm passing it the y test and the y predicted. So after I fit my logistic model to the x train and y train, I basically store my predicted values from a logistic regression model by using the predict function on x test. Now, after doing that, I can have the confusion matrix here as well. Let's see how does the general confusion matrix look like. And you see that it looks something like this, but just to have a better visual of it, I use the SNS heat map function and pass in the confusion matrix. And I mentioned that I want it to be annotated. When I say annotated as true, it gives me the values inside here. Or else if I do not do that, it's basically going to give me blanks. Not doing that. Yeah, getting that back. So I'll just run all of it again so that it's easier for me to do that. Now we'll just look into the accuracy manually. Okay? I'm just going to do it side by side so that you guys can also understand how does the accuracy function work. But it's not necessary for you to do it manually all the time. So you see that I have my correctly classified classes here. And if you want to see, it's briefly has a similar distribution. So there is 37 classes here and there is 17 classes here, almost half again. Okay. So I have 43 classes that are that my model has predicted correctly. So 43 divided by what is the total number of classes? 43 plus 11, that gives me 54 if I'm not wrong. Yeah. So what does that give me? It gives me this particular value. See, so if I just use the format function so that you guys can
agree to what I'm saying. You see that it's exactly the same value. So you could have done that intuitively. You could use a function for that, but it's fine. I think it's not required. Okay, so just use the heat map and identify that, and the accuracy score gives you the thing. Now, if I'm not wrong, there is also the score function that gives you the same thing. Let's look at that if that works. So I have my function as log underscore r dot score. Does it have a score? Yeah, it does. What are the parameters that my score function takes in? It takes in x, y, in the sample weight. So basically, it's going to take in the x test value and the y test value here. That should give me the x test and the y test values. Yeah. So I'm basically using the score function from the what's it? Oh, so that it gives me exactly the same value. You can use any of them. Some of the functions do not have the score function with them, so it's better if you use the accuracy score to be on the safer side, but it gives you the same score. Okay, so you can either use score or you can use accuracy score because it does give you the same value. Now let's see what is the accuracy for the second tier. Okay, I'll just come again. So now I'm going to follow the same steps. So I'm not going to repeat whatever I've done here. I'm going to follow the same steps for the second data frame that I created, the second data frame which has all the columns with any mutual information, and I'm going to repeat the same steps for the third data frame, that is transform DF3, which has the top 5 columns with the top 5 columns with the best or the most amount of mutual information with status. So I want to see that it gives me approximately the same accuracy. 98,334. Okay, so you see that this, it's 10 and 7 here, and it's 9 and 8 here. So it's classifying better on my transform DF1 than on my transform DF2. Why? Because it's not able to predict. If you go to just see the top section, the 0 plus, it says that 50% of my outcomes are wrong. And over here, it's predicting my first class 1, 34 of them correctly and 3 of them, which is fine. But I'm more worried about the class 0. And this is because of the class imbalance. Okay. So this was also not that great, but at least better than this. And I think it does the same thing in transform DF3 as well. You can see a similar pattern. Yeah, it's exactly the same. My transform DF2 and 3 have one better prediction more than my transform DF1 in the first level class, or the class with level 1. But okay, that's fine. So we're going to look into the various other algorithms to try to see what are the various methods where we can use it. So that was it for logistic regressions. Let's look into the other modules after that. So in this video, we're going to look into naive Bayes. You can pronounce it either naive Bayes or naive Bayes. It's up to you. It's naive is the approach that it takes, and we're going to understand why it's called naive or naive in that way. Naive uses the Bayes theorem. We're going to look into that as well, and assumes that all predictors are independent. In other words, the classifier assumes that the presence of one particular feature in a class doesn't affect the presence of another one. Now, the very reason the name of the classification technique is naive or naive is because of the same reason that the model assumes that the features are conditionally independent. Now, because of the very assumption, the name of the classifier goes to be naive because it is based on an assumption. Okay, so there is no test for that. It's based on an assumption, and that's how we go about it. Let's look into the Bayes theorem. So if A and B are two events, then the formula for Bayes theorem is given by it's A conditional B or A given B. You can read it anyway, and it becomes A intersection B divided by probability of B. So probability of A intersection B divided by probability of B. Now, how do we come up with this derivation? Let's look at the formula. So this is the basic conditional probability, right? And if you go on to see, if I just go on to ask you, okay, so what is the probability of B given A? Now, the exact formula will look something like this, where the probability of A given B into probability of B divided, the entire thing divided by probability of A will give you probability of B given A. Now, if you just use if you just take in the values from here and place it here, it will look something like probability of A intersection B divided by probability of B into probability of B. So probability of B and probability of B gets cut down. So basically what we have finally is something like this. So probability of B given A is equal to probability of A intersection B divided by probability of A. Now that's the basic derivation. You do not need to remember this, but just get an idea then that whenever you have probability of B given A, it basically is probability of A intersection B divided by probability of A. It's basically a condition probability thing, but that's how we go about it. Now let's look at the actual thing. So applying Bayes theorem to understand conditional independence. So that's why I came up with the exercise of going on to derive that. So let A signify the occurrence of head and event event B with the occurrence of 1 in a roll of a dice. Now find the probability of B given that A occurs. So I know the probability of A becomes the probability of A becomes 1 by 2 and the probability of B becomes 1 by 6. Okay, that's pretty understood. Now, if you're having a difficulty understanding the condition probability and basic probability, I would recommend you to go back to the probability video, just have a brush up, skip through the videos, and you'll get the basic idea. Now, so probability of A intersection B when there is no common intersection, basically we go on to multiply it, correct? So probability of A into probability of B, as there is no intersection point. Just mentioning the obvious so that people remember it. Now, so what they have asked is find the probability of B given that probability A occurs. So probability of B given A is equal to is probability of A intersection B divided by probability of A. That comes from here, the derivation. And if you go on to solve it, it will be 1 divided by 12. After multiplying 1 divided by 2 into 1 by 6, that gives you 1 by 12. That divided by 1 by 2 will give you 1 by 6. Now, it's basic math. 1 divided by 2 divided by 1 by 2 basically is 1 divided by 12 into 2. 2 and 12 get cut down to 6, so 1 by 6. And that is, if you go on to see, probability of B given A is probability of B, that is 1 by 6, as they are conditionally independent. So basically, the value of given A doesn't affect the value of B. Okay. Now coming to the naive Bayes thing, let's take an example to understand this. So this is actually the naive Bayes function where you need to find y given that x1 and x2 occur. So basically, we won't have univariate or bivariate or kind of data for us to work with. It's basically going to be multivariate. But just to
understand the concept, we took in a few numbers of features so that we understand the concept. It's the same thing for more number of features. You just add on the x values, nothing else. So basically, you have probability of x1 given y, probability of x2 given y, and you multiply it with the probability of y divided by probability of x1 into x2. Now, let's look at the table first before going ahead in the sum. So I have x1 as marks, x2 as extracurriculars, y as admission status, and you have the values here. So if the marks is good and the extracurricular is bad, you still get an admission. If your marks and the extracurriculars are bad, then you do not get an admission. If your marks is bad but your extracurriculars are good, then you do get an admission. Now let's try to find out the condition probability of y. So what will be the value of y, or what will be the status, admission status, if my x1 is good and x2 is bad? Now I know that my x1 is good and x2 is bad, so I will get a y. But let's see what does the naive-Bayes approach solve the answer to be. So y given good comma bad will be probability of good given y, probability of bad given y, and remember that this good signifies this column and this bad signifies this column. You should not take it from the same column. There might be a mistake in this particular case because the levels in the particular class is the same. So just remember that. So divided by probability of good and probability of bad, just extending the same formula. Let's look into how do we go about making the tables. Now I've left this table to be filled in by you guys, but let's look into this. So I know that there was one good here and there was one yes that coincides. So I fill in 1 here, and there is a 0 good that fills in no, so 0 here. Now filling in the bad. So I know that there is 2 bads here. So let's look at that. 1 bad here, 1 bad here. One says no, one says yes. So 1, 1. Now that makes the total to 2 over here and 1 in this case. So basically a half probability for yes, a half probability for bad and yes. So x1 and y, x1 and x1 given y will give you half when it's good. X1 given y will give you half when it is bad. The probabilities, I mean, and the total sums up to 1. Okay. Now in this case, this is 0 and the total is 1. So 0 divided by 1 will give you 0. And if it's bad, it's definitely going to be a no. So it's given here. Now you need to fill in these things, fill in the values over here. It's going to be approximately the same, but just fill in for your knowledge. So after looking at the table here, we came to the final place here where we see that are placed in the same formula. So you get in the values of 1 divided by 2 from here, 1 by 2 from this table, whichever we formulate, but the value should come down to 1 by 2. And 2 by 3 is basically the number of yeses in the y column. So that is 2 by 3. I know that. Now the probability of good comes in from here. That is 1 by 3. And the probability of bad comes in from this column. That is 2 by 3. If you're going to see, this should cut down and the multiplication of this will be 1 by 4. So 1 by 4 divided by 1 by 3 is basically 3 by 4, which gives us a probability of 75%, which is quite good because it says that 75% of the chances is that you're going to get placed, and that is true. So works, right? Now it's for you guys. There's a homework. You basically take in probability of bad and bad. You already see that it's no. The probability of yes should be really low, or it should be lower than 50%. Then basically, then is it? It's going to be, then we are going to say that okay, the model is performing well. Okay, so that's the homework for you guys. Now that was all about naive-Bayes. We're going to look into the practical example of the same so that you have a better understanding of this. So we already saw our codes running till the KNN section, that is 4.2 here, and you had a few homeworks that you should have covered by now, obviously. So this was the part that we had already covered. Now moving on to naive-Bayes, we're going to follow a couple of steps that were similar. So we're going to still use the classification report to understand what the F1 score is and how is it performing and so on and so forth. So because of the naive approach, you're going to see that the accuracies are not that great. So
The only part that has changed here is the Gaussian naive Bayes that we get from naive Bayes here. So the Gaussian naive Bayes is basically the classifier that I'm referring here. So I have NV as the object of this particular function, and I'm using that. So the variable NV fits the X train and the Y train here, fitting the data. Now I want to predict the data and send it into ypredict, and again the classification report as usual. You're going to see the accuracy is 65 here, which is the lowest up till now that we have seen. And you're going to see that the F1 score is 40 for the 0 class, and it's 75 for the 1 class, which is not that good, to be honest, because the data is not that complex as we saw. The other classes, the other classifiers were doing a better job, but this is still the transform DF1. So let's look at the other transform DFs that it has. So for transform DF2, it gives you a 74% accuracy. It's 65 here, 74. That's a bit better. So you see that it still doesn't perform really great with the 0 class, that is 42, 0.4 to the 0.40. And it does a better job for class 1, but we want to have better F1 scores for both the classes, not just one. Let's see what it does for transform DF3. We give 74% accuracy. It does that here as well. I think it's the same precision and recall. So not a lot of change. So coming to using the function where I use cross validation and so on and so forth, there's no such hyperparameters that you can tune that great. It's just via smoothing or priors that you want to put in. Well, I wanted to keep it the way it is, the basic naive Bayes. And I go on to see that on a cross validation, getting the average accuracy using the method. Let's just look at the method once again if you've forgotten. So I've taken in the cross validation, stratified cross validation here with 10 splits. So it splits the data into 10 folds, and my X and my Y has been split here. I go on to use the split function for stratified k-fold, submitted X and Y. That is going to give me the indexes. I'm going to pass it here and store it here, and then it's the basic fit and append. Basically, I'm appending all the accuracies here. So it's basically model.score that gives me the score of the testing thing, and I'm adding it here. And after doing that, I'm doing a summation of all the accuracies and dividing it by the total number of accuracies that is present in that particular list. And I'm overwriting the all accuracy values and returning that. Now, that was for KNN, and we had results of this kind. Well, I think it reshuffled itself, but we had some different results last time. But anyways, not an issue. Now coming down here, we see that we have a 77% accuracy on an average, a 78% accuracy on an average for transform DF2, and a 78.94 for. There's a slight increase because of the mutual information thing, but it is not that great, to be honest. Correct? So let's see. So that was all for Gaussian naive Bayes. There's not much to see here, but it's basically because we already saw the other factors before this. So yeah, that was all for Gaussian naive Bayes. So in this video, we're going to look into another classification model, that is KNN. Now KNN stands for K nearest neighbors. Now K is nothing but a placeholder, so which depends on the number of neighbors you want to take into consideration. Now in this particular example, we will see that there are I'm taking the value as K is equal to 3, so it's basically going to calculate the 3 nearest points. Taking this as a graph, you can see that this is the point that I want to classify. Now, is it going to be a triangle or is it going to be a square? I don't know that. So what do? I use K nearest neighbors and I set the value to be 3. And I say, okay, so which is the class that is nearest? So it's going to use something called as the weight manager. So it's not exactly the weight, it's not called the weight manager, but let's see what it does basically. So it says that there are two triangles that are nearest to it, and there is one square that is a third point that is near to it. So the thing becomes two triangle and compared to one square. Because there are two triangles that are near to this particular point, we say that this is going to be a triangle. Okay. How do we measure which element is closest? We use some distance measure to decide that. We're going to look into the distance measures, but before going ahead, let's take another example. So consider that now I change the value to 5. Also notice that I am not taking even values, I'm taking an odd value so that my value always comes out to, so one class always has a higher value than the other. So consider that there are two classes, and if there are two classes and I'm taking 3 as the value for k, the the value of one class will always be higher than the other. So say if there is a distribution example in this one, I've got two triangles and one square. The other combination could have been two squares and one triangle, but there could never be two triangles, two square, or one triangle and one square, because I've taken the value as k as 3. Okay, so that's the very reason you should always take in the value for k as an odd number. Now going ahead, I wanted to talk about, say, taking the value of k as 5. So when I take the value of k as 5, the 5 nearest points are depicted by this particular circle. It's just to show that this is the nearest one. So now you see that the value of boxes are more than the triangle. So you see that there's a dilemma. So how do you understand what is the optimal value for k? And how do you measure which is the nearest thing? Okay, here we can just say that you're drawing straight lines and saying that, okay, this is the nearest or this is the nearest. But how do we go about it? Now we're going to look into the distance measures, but before that, this is the nearest neighbor where you calculate the distance using the various methods that we're going to discuss. But there is another way that you can use KNNs, and that is called radial based or radius based KNN, where you have this point as the centroid or the center, and you draw a radius of the value k. So now k is not the nearest neighbor, k is the value for the radius. So say this is 3 units. The radius of this particular circle is 3 units, and each and every point falling within this particular circle is taken into consideration then. Same goes for the outer circle. So you see that it's more or less same if you go on to see, but just that the value for k changes. So in our case, we are going to look into the nearest neighbors. That's what the thing stands for. So we're going to look into that. Let's see what are the distance measures. So you have Euclidean distance. That's what we were doing initially, where we drew a straight line and said that, okay, this is what the distance is between these 2 points. You also have Manhattan distance. The distance is the summarization or the summation of the perpendicular distance or the horizontal distance. So if you just see, if you draw a triangle like this, the Euclidean distance will be the hypotenuse, and the summation of base and the perpendicular will be the Manhattan distance. And Minkowski is another distance measure. It's the distance between 2 points by using a curved line. So this could be a line. You could also have a line going something like this, making an ellipse kind of a structure and so on. But it's more of like the, this kind of a midway between these two. So this is a straight line and this is a perfectly bent line. So it goes somewhere in the middle. So you understand why these 3 measures are used. So they are more or less similar, but they are different in their own way altogether. So Euclidean distance is the general distance that we basically want to use every time when we use KNNs, but Manhattan and Minkowski can also be used. Plus Manhattan is perfect for, say, navigation purposes. So when you have 2 points, so this is your house and this is your school maybe, and you have buildings and other things, a road, you cannot have a single road going straight to your school from your house. Well, if you have, it's obviously going to use Euclidean distance, but sometimes it's not the most optimal.
Okay, and you have a road that goes something like this, and there's a crossroad here that goes to your school. So you're going to take a route something which looks like an L. And also, if you go on to see Google Maps or other applications that use navigations, have multiple routes. So you have multiple routes that go on and say that, okay, this is another optimal route, or this is another optimal route. It's 3 minutes slower, but it's good enough, and so on. So that's how the distance are calculated, if you were wondering. So there are some additional information that we need to look into here. You can always use the the confusion matrix, but there's something better that we can look into it, which obviously takes the information from the confusion matrix, but it's easier to calculate and understand, and we'll see why is it that. There's something called precision. So precision and recall are, kind of confusing. I used to get confused all the time when referring to them. So let's see, what does it mean? So precision basically means what proportion of the positively identified classes was actually correct. Okay, so consider that we had a particular class and we want to see what percentage of it was actually correct. So basically it works like the accuracy, where you want to consider one class and say, okay, how much was of it was exactly correct. Now going to recall, it basically says what proportion of recall positives was identified correctly. Okay, so what proportion of actual positives, and here we have what proportion of positively identifications was actually correct. It's kind of confusing, as I said, but we're going to look at an example that will clear your concept. So you see that the formula is also more or less similar, just that you have false positive here and you have false negatives here. Okay, so now the F1 score is the harmonic mean. So it is calculated from the precision and recall of the test. Obviously, the F1 score is the harmonic mean of the precision and recall. And this is the formula for calculating the F1 score. Now, the definitions might be a bit confusing, but let's look at an example to understand it better. So this is my confusion matrix. So I have one true positive, one false positive, and 8 false negatives, and 90 true negatives. Okay. So there's a class imbalance. Obviously, you can figure that part out, at least in the test set. I don't know what the training set. That's what the confusion matrix says, at least. Now coming to this particular section, where you see the precision is 1 divided by 1 plus 1. So this was 1 here, this was 1 here, and the number of true positives is also 1. So 1 divided by 2 is 0.5. So it could, the total number of positive values were 2, and out of which it could only identify 1. So you see what proportion I was talking about here? I hope you do. Now, coming to the next section where we have recall, it basically takes the summation of true positive and false negatives. Okay, so you see that the false negative was 9, the total false negative was 9, and it could only identify 1 true positive. So 1 divided by 1 divided by 9 will give you 0.11. So it says that you only have a 0.11% confidence in this particular model. Coming to F1 score, you just take in the multiplication of these two values, 0.5 into 0.11, it will give you 0.055 divided by 0.61, that is the addition of these two values, into 2, that will give you 0.18. Now, the F1 score is a better way of seeing things when you have say a class imbalance, or there are some discrepancies. It's better to have a look at the F1 score than looking at the accuracy. We'll look into this why. So if you want to see, the accuracy is measured by the total number of correctly classified values divided by the total number of outcomes. So the total number of outcomes were 100 and the correctly classified classes were 91. So if you're going to see, 0.91 is our accuracy, but our F1 score is really, really low, because you see this particular class is kind of going missed out completely. So if there were 50 records here, 50 of them would have been wrongly classified and 50 would have been rightly classified. That's what the precision said. So you need to understand the fact here that accuracy is not always the best measure to look at things. You should always look into the F1 score as well, seeing just having a look at the bias, so if there is any bias there. So that is one thing. We're going to look into a few other measures that help us go on to find the optimal value. So grid search is the thing that I was mentioning, how to find out the best value for k, most optimal value for k. We're going to look into the practical version of the same, but let's understand what is grid search. So this is a hyperparameter tuning method. Now I'm going to explain what a hyperparameter is. So all the parameters that you pass to a particular model. Okay, so here say I'm passing in the value of k, the number of neighbors that I want to consider, and that would be 3 or 5 or whatever. So that is a hyperparameter value that you're passing in. So we need to tune that value sometimes to get the optimal value or get the optimal value for that particular parameter. So that's what hyperparameter tuning means. Now going ahead in the definition, so there's a hyperparameter tuning method where you put in all the parameter values that you want to train and test your model on, and on the basis that you get a combination of all the values passed. Okay, so you get a combination of all the values passed in it. Say that there are more than one parameter. So there is a parameter, say x, and there's a parameter y, and there's a parameter z. Just taking an arbitrary example. And you pass in the values 1, 2, 3 to x, 3, 4, 5 to y, and 6, 7, 8 to z. Now it's going to make a combination of all these things iteratively. So one value of x, one value of y, one value of z, and so on, till the point that it's going to do all the combinations and give you the best outcome. Now you see that it is quite a tedious process when you have a lot of hyperparameter that you need to tune, or you have a huge data set. So the better version of it, I won't say it's a better version of it, it's just the more optimal choice of grid search. Is a random search cross validation. So over here, it's similar to grid search, but doesn't make all the combination that are possible. So it basically takes a subset of the values that you pass in on the basis of the distribution of the particular data, and gives you the best results on the basis of whatever it's selected, on the basis of whatever combinations it made. And that's how you come up with the optimal values by not even going through all the combinations. So you can see that I've just mentioned here, just for your reference whenever you go through the notes. So it's best for large data sets and more number of parameters. Or you can have both as well. You have large number of data sets and a particular model which has a large number of parameters. This is the best version of what you get. So there is there are other types of cross validations as well, but here we do not tune the parameter. We basically go on to find the average accuracy, or you can say the average performance of a particular model. And for that, we go on to use k-folds and stratified k-fold cross validations. So in k-fold, we basically fold our data set k times. Okay, k is again a placeholder where you go on to mention the number of times you want to fold your data. And do the train and test splits, model training on that. This gives us k number of accuracies. Now you can either look at the range in which the accuracies lie, or just have an average accuracy. So let's take an example to understand this. Say that you have 30 records, and I say I need to cross validate this thing 3 times. So my k value over here, the k fold value is 3. Now this is going to divide my entire data set into 3 folds. Now making 3 folds will mean that it will have 10 records each time. And I say that, okay, so my testing set will be 20%. So 20% of 10 is 2. So for each time the model is run, is basically going to say, okay, the first set will have 8 and 2. So 8 will be the number of training records, and 2 will be the number of testing records. It's going to the next fold, it will have again 8 and 2, and going to the third fold, it's going to have 8 and 2 again. So that's how you get three values now, three accuracies. You can say, okay, so this is the minimum value and this is the maximum value, and this is where this is the range what your accuracy lies in. Or for a better explanation, you can just have the average accuracy. That's what people usually prefer. Gives you a holistic opinion of the entire range at the same time. Now let's come to stratified k-fold. Now I know that we have already looked into stratified in the logarithmic thing, that what does stratified mean and why do we use it. Just iterating on that again so that, just refreshes the thing. So the k-fold thing is the same. K-fold CV is the short form for cross validation. So the k-fold CV is same. The stratified keeps in mind that whenever the folds are made and whenever the splits are made in the fold, they are in the stratified form of it. Basically, keeping the class proportions same in the training as well as the testing set. So this was more or less the additional information that you need to know, and we are going to practice it out in the coding section of this particular video. But I hope you got the sections and you understood what k-folds and what does the cross validation when you talk about k-folds mean, and what is the cross validation you talk about when I say grid search cross validation. So this is a hyperparameter tuning method, and this is we can say that an average accuracy finding method if I have to put it in layman terms. So that was it for the theoretical part. Let's look into the practical part now. So in this video, we are going to look into the practical part of KNN, where, so just to recapitulate, we had the logistic regression done here. And what does the transform DF1 mean? It has all the columns. We're using the same placement data set. And transform DF2 uses the columns with some mutual information, with any mutual information for that factor. And transform DF3 uses the top 5 columns with mutual information. Now going ahead, using the KNN function, how do you get the KNN model? You just use sklearn.neighbors, import k nearest neighbor classifier, and that's how you go about it. So this is just a model placeholder value, just a variable name for the model. And I'm giving in neighbors as 5 and the algorithm as brute. So basically you can have auto or brute. This by default, if I'm not wrong, it's auto. Yeah, the algorithm is auto. You can also use a brute force. So it uses all its force to find the best possible combinations. You can also use KD tree and ball tree if you want to, but for this case, I'll just try out with it. Using the same train test split. Let's run this. That gives you the X train and X testing. KNN as well again. So here I'm making it a split of 75 and 25 and keeping the random state as 42. Now I'm using the model and fitting the X train and the Y train that I just got from this split function. And after that, I use predict function as before from logistic regression. I predict the values, the Y predicted values, and store it to the variable YPred. Now I'm using the classification report and also the accuracy score. So remember we spoke about precision, recall, and F1 scores. So here you see that I have two classes, 0 and 1. It gives you the precision and recall for each class and the F1 score for each class as well. So that you use using the classification report from the sklearn metrics function. You also use you used accuracy score before, but just so that you know, you use it from the sklearn metrics. Sorry, what is this called? The package. Yes, I'm so sorry. The package. Yeah. So you use it from there, and I see that the classification report will give you something like this, and where you see that the accuracy is 81. That's exactly what your accuracy score also gives. So you can see that here, but your precision, recall, and F1 scores are distributed here, and you see that the F1 score for 1 is 88, but for 0 is 62. So it's not that great because it's still not able to identify the 0 values that well. So let's see what does it do on the transform DF2. So I've done the same things here, just that you'll see that the transform DF2 is mentioned here where it was transform DF1 here. So it's the same thing.
just in one cell. Running that again, sorry, yeah. So you see that it's 88 and 64. Here we had 62 and 88. So the F1 score for 1 remains the same, but 0 increases a bit. And the score remains the same. Yeah, it's the same. It's kind of exactly the same with whatever decimal points I mentioned here. So the accuracy remains the same, but the precision, the F1 score for 0th class increases a bit. Now that's a good sign. Let's see what happens in the third part. Okay, so it decreases for some reason. I think it's, no, we have kept the same random state, so that shouldn't be an issue. So basically when I set the random state as 42 for all the things, basically the split is the same for all the X-train and Y-train data sets. So here we see that the accuracy for 1 and 0 both decrease by, say, 1%. So it decreases by 14% for 0 and I think 2% for. So we are not concerned about 1 that much, but we see that the 0 is facing a problem to be classified, and the accuracy also decreases by 10% here. We can see that. Sorry, it decreases by 3% here. Okay, so I would like you to make the insights over here. I've made the placeholder value, so you just remove this. I'm going to fit in one of them. So the accuracy for the first one was 81. So I'm going to mention that. And the F1 score for 0 and 1 was 64 and 88. 64 and 88. So I want you to fill up these so that you get a habit of working on them. Plus, I would also like you to find out the precision and recall for the confusion matrices here. You see that I think these two have same values, so you technically would just need to work on 1 and 2. Two confusion matrices, and that should give you the an idea of how precision and recall is calculated, how F1 score is calculated. So let's just make a homework section here. Space, sorry, and find the required precision. And if you have a difficulty in finding the precision or recall, just refer to the previous video and you will have the functions mentioned there. How do you go about it, and what is the formula? How do you calculate that? Okay, and you type in your code here. Okay, like if you want to put in your code, you can also use it as a code, because the confusion matrix, as we saw here, is basically a two-dimensional NumPy array. So you can say that, say, if you store it in A, let's see, what does this do? I think it should have it here. Let's see, what does this print here? Okay, I think it's printing the one from this one, because we made the new train test split. But anyways, nevertheless, just for understanding purposes, how do you go about it? Instead of the brackets, sorry. So instead of this, we just say we have a variable A is equal to this, and we say type, A, and let's see what does it do. It says a NumPy array, works for us, and does this print that out so that it's easier for us to understand what am I doing here. So I printed A, now I print the true positive, and you can fill in the rest if I'm wrong, but this will give you an idea. So true positive is 0, 0, and it should give me 6. Now you have the, I think this was a false negative if I'm not wrong. false negative is 1, 0, effective is 4. Yeah, see, so that's how you go about it. Okay, so I'll just rerun this entire thing so that you get an idea of it. We get true positive, false positive, false negative, and true negative values. So, yep. So I guess that should do the job. Yeah, so this is how I've kept it so that you don't, you can, or what you can do is you can just go ahead and create a confusion matrix for KNN and then work on that as well. Anyways, I'm asking you not to do it because you already have them. You already have the precision and recall and F1 score here. I just want you to find it for 1 or 2 confusion matrices that does the job. So I've left your job here. Your code goes here. Yeah, you can go ahead and KNN now. So we already saw the 3 data frames working on it. Now, this is again your homework to fill in, just so that you have a habit of filling in the insights. But we should use k-fold, k-stratified k-fold to have a better understanding of the same. So we used just one random state here. So if you want to see, I just changed the random state to 12, and the actuals was 74. It's 89 now. And see the even the F1 scores drastically increased. It became 0.84 and 0.91. It was 72, and this was giving us the least amount of accuracy considering the others. And now it gives us the most comparatively. Yeah. So you see, it drastically changes. Now, if I go back to 42, if I'm not wrong, that was it. Yeah. You see that it's going to give me the same value for 72 and 59 and 79 because the randomness is constant with the state. Okay, so keep that in mind. And for the very same reason, we are going to use k-fold cross validation to have a more holistic opinion about it. So for using k-fold cross validation and getting the best parameters, I'm also going to use grid search. So grid search can be imported from sklearn model selection, and you make the parameters as a dictionary. So I have param over here, I'm making it a dictionary, and you have n neighbors, and I'm making the list of a range that starts from 5, goes on to 55, mind you, and has a iteration value or an iterative value of 5. So the next value that is going to come after 5 is 10. Okay, or I can just have an increment of 10 becomes an even value, right? So let's have an iterative value of say 3. So that will give us more number of iterations, but we can have 7, but that will also give me even numbers. Let's just see, this gives us all odd numbers. Yeah, this gives us all of them. Okay, so we're going to work with this. Run the grid search. So you see that I've passed in the algorithms as brute and auto. You could add in more as you want to, but we're going to use, as an example, we're just going to use them. So now you have the grid search function. I'm storing it to grid. You are passing in the model, the parameters that you want to test for that particular model. You have a CV of 10. So basically the entire data set is folded into 10. And you have the scoring as F1. I'm not using accuracy. You can also use accuracy here if you want. So I have the X values and the Y values over here. I'm choosing the DF1 values first. So I think by now you already understood that why I dropped the status column here and add it here. So because it's the predictor column. Sorry, this is the predictor column. This is the column that we want to predict on. So that's the reason we split it and we fit the grid.
So now when I run it, it's going to take a bit of time because it has a lot of parameters to combine. Yeah, it does. That did that. Now it says that it fitted these values. Okay. Yeah. So this is it's just to show what is the scoring parameter, what are the parameters that you have passed in. The estimators just gives you a brief description of what you did. Let's just see what it does here. So the best score that you get, the best F1 score that you get is 84. And the algorithm that you need to use is auto, and the neighbors as 43. Okay. So what we're going to do here is, this is a function that I'm going to describe, but before that, I'm just going to change the values. This is auto, and this I have to make as 43 because this is what I get here. Okay. So now I'm done with the grid search part of it, where I go on to find which is the best parameter. So let's see what I've done here. So this is quite counterintuitive, but anyways, so grid.bestScore is a function that gives you the best score that I've mentioned here. Grid.bestParameters gives you the list of parameters or the dictionary of parameters that fit in best, and grid.bestEstimator gives you the best estimator. And if you see, it doesn't give me the algorithm as auto because that's the default parameter here. So even if I remove this, it's still going to work as it should because by default the algorithm is auto. Okay, so that was about grid search and how do you go on to find which is the best score, or what are the best parameters that you should use to have the best score, and so on. So let's look at the average accuracy function that I've created here. So this is a user-defined function. It's not a function that you can import, but I'm using the stratified k-fold here. Now that's a function that you can import for sure. So you have sklearn.model_selection and you import the stratified k-fold from there. Now skf is just a variable again to mention this particular stratified k-fold where I'm making 10 splits and saying that yeah, shuffle is true. I want to shuffle and I'm setting the random state as 12. I can also set it to 42, but I'll just let it be whatever it is. And I'm making a list where I store all the accuracies. Again, I'm doing the split thing here where I'm having all the x values and the y values. Now for this is one thing that you need to keep in mind. Now this is sometimes get tricky and people do get silly errors here. So skf.split xy will give you indexes. Now those indexes will be train and test indexes. So when you do the x train y train split, you basically need to use x.ilog, okay, and not just this. This is going to give you an error, and this is what you should use. .ilog train index, test index, y dot train index, and test index. Remember that the order here should be mentioned as it should be mentioned here. It should be the same. So if this is x train, this should be x train. If this is x test, this should be x test. Okay, you can also shuffle the order, but I keep it in the way it is because this is this, if you remember, this is the same order you get the train test split from the other functions. So that was it till here. Now we have the train test splits. We have the model here that are passed in as a parameter. I fit the train test, the x train and the y train values. I fit the model. All dot accuracies. I append the model score here. That appends the score. All accuracy is equal to sum. So it basically sums. And now this is out of the loop if you want to see. Now till this point, after this entire loop has run, basically it is going to run 10 times and it's going to fit in the train and test values after calculating the score of it to all scores, all accuracies. And after coming out of the loop, what I'm basically doing is I'm overwriting the all accuracy value. Now this is going to be a single value. Now when I'm overwriting it, I'm overwriting the particular value is basically saying that, okay, whatever it actually contains, just remove that and add this on top of it. So you see that initially all accuracy will have a list of 10, there will be 10 values in it, and I'm passing that. Now I'm using the sum function to get the sum of all the accuracies, and then I'm dividing it by the length of all the accuracies. So it's basically going to get divided by 10. So you can also, just skip this out and write 10. That does the job as well. But just to automate the entire process, so every time you go on to change the split here, you do not need to rewrite the value over here. Okay, so that's the only reason I use this particular way of writing. Now this will give you the average accuracy I'm overwriting it to all accuracy and returning that particular value. So I created the model here based on the parameters that suited the best, as mentioned here. Now, after doing that, I basically use 3 print statements and call the average accuracy function, pass in the data set and the model. Now, I run the thing and I get 7258, 7342, and 7433. So if you go on to see our assumption that, after selecting a few good columns or the better columns, the accuracy does increase on an average. And that's what we can see here. So let's compare the results from what we saw over here. So we have 72 for data frame 3. Now we have 74. For data frame 2, we had 78. Now we have 73. 7258 we had for data frame 1, like right now. And here we had 81. So you see that on an average, the data frame 3 performs better. Okay, just to recheck what happened in logistic regression. Okay, we haven't done it for logistic regression because I made the function now. So again, you guys have a homework. So you can find the accuracy of the models using the accuracy. Sorry, it was average accuracy from. Just check that. Average accuracy. So basically you just need to copy paste a few things and that should do the job. And you have this average accuracy method. Okay, so you basically just copy these 3 lines. Okay, create the logistic regression function, the logistic regression model up here and just pass it here. Just change KNN to logistic regression model, whatever is the placeholder value variable name that you want, and just paste it here and see what is your understanding of the models here. So you had 85, you had 85 here as well. You had, I didn't see, no, we have 86 here. So it's up to you guys to, go on to print the average accuracies and then, make insights on that. So that's another homework for you guys. I'll just mention it here as well so that don't forget. So say regression, average accuracy. So okay, that's sure. I'll just specify that this is the code section so that it highlights it and you don't forget that you need to use that particular function. That's how you highlight it and make it a code if you want to specify it. This is the code section, so I just highlight it so that you understand that you need to use that function, as you don't need to calculate it manually or something like that. You just need to use this function. So that covers KNN. We're going to look into other models now. I hope you understand how do you go about KNN and the various aspects of what to use and how do you hyperparameter tune it. What is grid search? What is K-folds? How do they work? We understood the theoretical aspect. This was the practical aspect of the same. In this video, we look into SVMs, that is another classification model. So SVM stands for support vector machines, where the main agenda of the model is to split the data into n categories. Now, n being the number of categories present, the basic version of SVM uses a linear hyperplane to distinguish between 2 or more classes. So a hyperplane is nothing but a line in a 2D space and a plane in a 3D space. So that is used to determine which side of it will it fall into when a new point is provided to it.
So basically, if you go on to see here, now so the name suggests that we have support vector machine. So there is a support vector. There needs to be something called support vectors. You see these lines that are the closest to the other group here. So this is one group and this is the second group. And you see that there's these are the most closest to this one. So this is the closest to this, and these 2 points are closest to this particular point here. Now, if you go on to see, creating them as support vectors, I draw a line, and this is just one of the lines. So you can even have a line going something like this. You can have a line going something like this, and this comes out to be the best. And the lines are based on something like, if I go on to have a line something like this, somehow a point, say a green point coming here, would be classified as blue, and the same would go for something like this. So if I have a line somewhat like this, and a blue point over here would be classified as sorry, a green point over here would be classified as blue. So something like that would happen. So this is the most optimal line or the hyperplane that could be possible. Now this is the buffer that we can have, and it is usually there so that, you know, even a point that comes in here is also classified as blue and not as green. So we'll look into the various boundary categories and how they look and what happens. So this is the basic thing. So this is the hyperplane, the red line, and these are the support vectors. Okay, that helps us classify. So what are the steps to create a SVM model? So step 1 is identify the support vectors. So you identify, okay, this is my vector, this is my support vector, and I'm going to draw a line something like this. So see if the data is linearly separable. So this is a linearly separable data set, and this is a non-linearly separable data set. So you cannot have a single line, say, going somewhat like this, say 45-degree to the origin. You will have a 50% kind of classification accuracy, because there are some greens and some red on either side of the line. So that won't make sense. So how do I go on to use a linear separator here? I cannot, obviously. So there is a different step for that, and we're going to look into it. But consider that we have a linear separator. What are the steps? If it is, then make a linear separator between them. So we did that exactly in the middle. It should be exactly in the middle with the buffer like we saw over here. So this is the middle line. If you just calculate, this would be in the exact middle. So going back here, so now after you have created the line and everything, I think your model is ready now. You just use the same model to, you know, have an extra point. Say this is another point, the point over here. Consider that this is another point. Now, because it falls on the left side of the boundary, which has the red clusters, it will form, it will be classified as the red class. That's for as per se. Now coming to the non-linear separables. Now let's see how do we handle that. So the process is simple. You use the kernel function to take the data points to a higher dimension. Okay, identify the support vector there, support vectors in the higher dimension, draw the hyperplane in n dimensions, and your model is ready. So we had something similar over here as well. Okay, we had two clusters, a ring-like structure, and you know the inside is filled with the green classes. Here we have something like similar, but you know, a bit different. But anyways, we cannot linearly separate it, correct? With any line, it would give us a very bad accuracy. So taking it to the higher dimension, we add another dimension, and the red classes stay below and the blue classes go up. And having a plane in the middle is or is more of like, you know, having a sheet of paper in the middle. You can easily linearly separate them. So that's how you handle you know, linearly inseparable data sets. You just take them to a higher plane, and you know, you use them in a similar manner. So that's how you go about it. Now coming back to the point that I wanted to mention after you understood SVMs a bit. So there is something called a hard bound and a soft bound. So basically it means these boundaries are, you know, is this the line that you want to consider as the hyperplane, or is this the entire section that you're going to consider as the hyperplane? So a soft bound will consider this line as the hyperplane, where a point over here will also be taken into consideration and classified. But a hard bound will classify this as it might misclassify, okay, because it considers this as the boundary. Okay, and let's have a look at the practical example for the same. So coming to SVMs now, we go on to use the SVM function from sklearn, and we use the function svc from SVM, from the package I mean, and basically you create a variable SVM, you write svc, so support vector classifier, you set in the kernel as linear, and you have class weight, and basically I'm setting weights to the particular class because I have a class imbalance. So this particular means it has an equal class balance, and we'll try to hyperparameter tune it. So class weights are now equal, and let's see what it gives us. So it gives us a 67% accuracy. The rest of the steps are same, where you have the train and test split, you have a random state. So I'll just give it 42. We were considering that earlier as well. So it gives us 84% accuracy now. It gives us 89% accuracy for the first class, a 72% accuracy for the zero class. Okay, not that bad, considerable, but we still need to look into the other aspects of it, because it still has a problem classifying the zeroth class here. Okay, so same steps. You store everything to ypredict and then use the classification report on it. Now I'll use I went on using the grid search, so I'll just use that only because the data set is not that big. And so what are the best parameters? What is the best score? So the best score is 82, and the best parameters are mentioned here. So zero class should have a weight of 2, first class should have a weight of 1, and the kernel should be linear. That's exactly what I've put. Okay, I'll just set the kernel as linear. And then just use the same average accuracy function to see what happens. So the average accuracy comes out to be not that great. So I have a transform df1 giving the best accuracy, having all the variables. Transform df2 having a bit of lesser variables, I think 6, and transform df3 having 5 variables, with gives us still a better accuracy than transform df2. So it's okay-ish, but we can still improve it, and we'll look into the other model, and we'll look into something that we can help that will help us identify the particular problem, and how to solve basically class imbalance. So we'll look into the next model and then finally look into that. So the next model that we look into is CART. Now CART stands for classification and regression trees. Now surprisingly, yes, decision trees is also another name for the classification trees. So the classification trees are also referred as decision trees. So it can you can use it for classification as well as for regression. So we are going to look into the classification aspect of it, but you can go ahead and try out the regression aspect of it on the earlier Python notebook that you have, where we have done linear regressions, and try this out and see what happens. Okay, now let's see what does it say. Okay, so name of the model is decision tree because it looks like an inverted tree, as we can see here. So if this is the root, this is called the root node. And you have a branch here, and this branches again, this branches again. So that's why it's called a tree. It looks like an inverted tree. The decision is made on the basis of some conditions, and splits are made accordingly. So on the basis of some condition, it is yes and no, and then young, and then drinker. So a smoker, if no, and then is he a drinker? And if if the particular drinker says yes I am, then what is his weight, and this is what his weight is going to be, and this is what I classify him to be, old or young. So if a drinker says no, I'm not a drinker, then he's old, and so on. So this is just a basic example, but yeah, it does make sense. So the tree goes on till the last node. So it goes on to the last node, referred to as a leaf node. So this is a leaf node, this is a leaf node. All the deep blue ones are leaf nodes, and till it can't be split any further. So this can't be split any further because my classification problem here is trying to say if the person is young or old based on the condition. So these are my features, and yes, no are my conditions. Less than 90, greater than 90, and so on. So that's what it is. and this was the basic thing where we have the splits, and you want to say, okay, this the percentage young or not. Let's look into how it works. So the root node, the starting point, is calculated using the information gain. So you go on to calculate the information gain of each of the features, and then you go on to say, okay, because this particular feature has the highest information gain, this is going to be my root node. Then you go on to do the information gain again, and then you go on to find the second the second node that's going to come in, and so on and so forth. So the information gain can be calculated in two ways. You can either use entropy to calculate it or Gini. Now Gini is more of a simpler way to calculate it. Entropy is more of the established way of doing it. So whenever people say, okay, I'm making a decision tree, the first thing that comes to their mind is, okay, so basically you're using entropy and information gain. So that was the basic thing, but you can always use Gini as well. So what is the formula for calculating entropy? Is listed here. E is equal to minus P into log 2 of P minus Q into log 2 of Now P and Q is basically probability, and 1 minus P. Q basically stands for 1 minus P and the probability of that. We're going to look into this here. So we have E2, E1 and E3. Now I have 5 positive and 2 negatives. That gets split into 2 positive, 1 negative and 3 positive, 1 negative. Okay. So my for E1, my P log 2P will be 2 by 3. So positives 2 by 3 here, log 2 of 2 by 3 minus 1 by 5. So 1 divided by total negatives, that sorry, the total number of positives. Sorry, my bad. 2 plus 3 is 5. Now 1 by 5 goes out here, and 5, yes, and this comes out to be the value. Now over here we go on to do something same, and we go on to find the information entropy for that particular step, and that's how you go ahead. So P is the total positive inputs divided by the total inputs. Q is the total negative inputs divided by the total inputs. So that's how you go about it, and more or less it's counterintuitive, right? So let's go ahead and see what else do we have. So there's a disadvantage to decision trees. Okay, so decision trees to its max depth tend to overfit. Now this is a general statement. This doesn't happen all the time, but happens most of the time. Okay, so when you have it to the max depth, now considering this is my max depth, where I know exactly that after this particular step, my model will classify old or my model will classify young. So that's called the last step. The leaf node cannot be split anymore. So that's what I'm saying by max depth. It basically tends to overfit. Now, what do I mean by overfit? We haven't gone to the conditions of overfit and underfit. So overfit, when the model takes in the training values and fits it perfectly and fails to perform well on the training set, we say that the model has overfit. So you can test this by checking the training and the testing accuracy. If the training accuracy is way higher than the testing accuracy, it is safe to say that your model did overfit. So if you go on to say for a decision tree, if my training accuracy comes out to be say 90 or 99 or 98, and if you go on to test the very same model on your testing set, it comes out to somewhere around 65 or 70. Basically, your accuracies have diverged and it has overfitted. So there are ways of rectifying it. You can prune the particular tree, or you need to identify what is the problem, why is it overfitting. So they're based on them. So if you just reduce the max depth a bit, maybe have a probabilistic answer that, okay, so over here, if I had stopped it in the first depth only, this is level 1, if I had stopped it here. So after, if the answer would have been no, I would have had a probabilistic answer for old and young. So that's how it would have been. So that way it wouldn't have overfitted. So now what is underfit? So when the data is unable to fit well, that is the accuracy is lower, or both the training and the testing set, we go on to say that the model, when both the accuracies are lower for both the training and testing set, basically can say that the model unfit. So this is generally the case when the model we are using is too simple for the test. So If you remember, the model that we were using is linear regression in the regression problem, and the data was really scattered, but we were still using a linear regression line. So that's what it means when I say you're using a linear separator. So if we go on to use something more complex, we might uh, you know we might as well use something that is very, very complex and could have got a better accuracy there. So that's what I mean when I say the model has an effect. So the training as well as the testing accuracy wasn't that great. So that was more or less about decision trees. Now we're going to look into the practical aspect of it and try to understand how do we identify overfit and how do we overcome. So this is the same Python notebook that we looked into further. So now we are in 4.5, the decision trees. We do the same thing, X and Y, split it, and we are using decision tree classifier. You can also use decision tree regressor that you should use for the regression problem and try it out yourself. And you'll understand how the regression works. So that's a good thing. Now you import it from sklearn.trees, tree, my bad, and you're going to fit the data. Generally, use predict function to create the y predict list, and then get the classification report. So the classification report says that the F1 score for class level 1 gives you 83, for 0 it's 48, which is not that good. Let's change the random state to 42. That's the one that we were using. Rerun it. So we see that it's 62 and 83 did not improve a lot, but we cannot change a random state and then we use it for different functions and say, okay, so that's how we go about it, and we use it this way, and I'll just use a better random state to get a better F1 score. That's not how it works. So that's the reason we were using stratified k-folds and k-folds and trying to understand that. Now, considering here, we have a lot of parameters to test, right? We have different class weights, we have different max depths, we have different criterias, the minimum leaf, the minimum sample leaf. So there's a particular parameter which says that you need to have a minimum number of sample leaves at the end. So that's what this is. And setting the random state 42 will not make a lot of difference, but let's see what did it give us. The best score is 76 that it got, and the best hyperparameters are this. So the class weight needs to be 2 and 1. So basically all models are saying that because 0 has less classes, give it more weight. So we're going to do that. The criteria is Gini. Okay, so that changed. Let me do that. The max depth is 5, that's 5. The minimum leaf samples is 1. Let's do that 1. And now reiterate. So you see that all the decision tree values came out to be more or less similar. There's a change in the fourth decimal place. Now it's safe to say that, okay, my transform df3 gives me a better accuracy, but it gives you a better accuracy in the fourth decimal place. Now that is not that great. Okay, so let's test if it's overfitting. If you go on to see, my training accuracy is 80 and my testing accuracy is 69. Now, remember when I told you that it does overfit and it's a general statement. Now, for our case, it's not so general. Now, it did give us a overfit. So how do we go on to do that? We can change the max depth to say a bit lower, say 2, and let's see if it makes any changes. I'll just format it so that it gives me a better look at the accuracies. So now you see it kind of is similar. When I change it from 5 to 7, let's just do it 5 again and see what happens. Now I'll just copy this thing over here and comment it out. So these are my values for max depth as 5. Let's change it to 3 and let's see what happens. So, oh, it's exact. So this is the best fit that we can have. Now let's see what happens with 4. Oh, it still overfits. Let's see what happens. 2. Sorry, I stopped. Oh, my bad. So yeah, the training accuracy is still a bit higher and the testing accuracy is still a bit low. So I think 3 gave us the best results where it gave us an exact accuracy for both the training and testing set, which is quite good and pretty rare to see. So that's kind of a good example to look at. So you saw that just by changing the max depth, you basically prune the tree. When I say pruning, basically you go on to make the tree shorter so that it gives you a probabilistic answer. Now, having a probabilistic answer is better because uh, you are not saying that, okay, if these are the conditions, it has to be class 1, or if these are the conditions, it has to be class 0. You give a more probability. It can be there's a 60% chance that it's class 1, or there's a 55% chance that it's a class 0 or something. So that's how it works. So we had a max depth of 3 and it gives us the best training and testing accuracy. So we're going to keep it that way for this particular random set that I have for 9. Let's see what happens with 42. It overfits. Let's just change it again. It's an iterative process, right? So 5, it's overfitting higher, max depth of 1, it's under. So fitting again. Doesn't make a lot of change. So I think 5 was kind of ish. So I think 3 was giving us the best that we could get. But anyways, for I think 9, we were having an exact value. So I'll just keep it that way for future references. So that's how you go about to prune a tree and get the best accuracy. Now, even after pruning the tree, as we saw for class, I think 42, there was still, overfit. Now, this is still fine. You have it's a 3% difference. That might happen, but it's still okay-ish. So if I have, say, a trace of this of 1, sorry, you see it's 69 and 76. So this is overfitting. That's how you go on to identify. A 3, 4, 5% gap is still okay. So now I hope you understood with various examples what overfitting is and how you go on to do it. I have a spelling mistake here again. So So now if you want to see all the F1 scores that we have is lower for the 0 class and it's higher for the 1 class, and even for the distribution that we had, let's just go back to the graph. Fast, I guess. No. Yeah, so if you're going to see the place and the non-placed graph, you see that it is approximately half. So even when we were using grid search, it was giving us a 2:1 ratio. So this is supposed to be double and this is supposed to be same. That's the very reason it was giving us that. Now let's look at a concept called oversampling and undersampling, which helps us do that. So what is oversampling? I think it's better that you visualize and look at it and have a more better understanding. So let's run this code and see. I'll explain the code later, but let's just see at the output what happened. So before sampling, I had 198 records for 0 and 2 records for 1. Somehow it did that. Let's just yeah. So this gives us a better idea. So it was 148 and 67, and I kind of made it so that it gives us a better accuracy. Sorry, it gives us a good split. So you can shift the weights and understand. So it was 148, so 140, 140 split. Now you increased the 67 value to 140. Now it has an equal class balance. Now let's see what all things that I use. So I use the make classification function to tell the particular method that, okay, there are two classes 0 and 1 is a minority and 0 is a majority. And I use IMB learn oversampling and IMB learn undersampling, and I use the very same functions, random oversample and random undersampler. and I made the splits on transform DF1. So the homework for you guys is to learn from oversampling and undersampling and replicate the same for transform DF2 and 3. You can always refer to what I've done here and, copy paste and try to understand, try to play around with the values. You're just learning. Okay. I do not expect you to code from memory. I sometimes am not able to do that. So it's completely fine if you do not remember a particular function or a particular package or a particular function from a particular package. It's completely fine. You can always Google. Anyways, coming back to the point, splitting it into X and Y, I guess by this time you already know that X, how am I creating X and how am I creating Y. Now I go on to make the classification on the basis of X and Y. I say that I have a sample of 200. It's just a basic assumption. Then I'm giving the weights, and then flip y. What does flip y do? Let's see what flip y says. Flip y. The fraction of sample this class is assigned randomly. Larger value introduces noise in the label and makes the classification task harder. So I do not want the classification task to be harder. So I'll not give a high value. That's why I placed it 0. So I do not want it to be hard. Anyway, so then I go on to use oversampler, or I want the oversample object of this particular function. So I want to use random oversampler. Sorry, this is not an object, this is a variable. And I want to use random oversampler, and I want to say sample underscore strategy, and I want to say minority. Now I go on to say minority because I want to oversample the minority class. In this case, it will be the 0. And then I use the fit resample method from oversample, and we go on to say x comma y and x, and I go on, and this particular value will give you x and y values, and it will give you x over and y over. So over basically signifies x over sample and y over sample. So, and this is the particular function. It's just converting the y over, because this is a NumPy array and this will also be an array or a list. So I'm just using the PD series function to go on to that, convert it into a series, and then use the value count function to see the distribution. Simple as that. So you see that 148.67 is now converted to 140, 140. I go on to create this k-fold accuracy function, which is the same as we were using before. There's a slight change. So now I'm passing in x and y, and I'm not splitting it inside it. And I have the model. Everything else remains the same. Stratified k-fold. I have all accuracies here. I train and I split it. Okay, now the thing that I want you to observe here, that I do not have ilogs here, because the x and y split is not a list now. It's a NumPy array, and NumPy array does take the indexing without the .ilog function. In fact, it doesn't even have an ilog function. It takes the index as it is. So same function, nothing much, nothing new. It's the same thing, just that the xy is now passed and not splitted inside. Now this particular cell, I'm creating the models for each and everything that we have learned up till now: logistic regression, KNN, naive Bayes, SVMs, and decision trees. And I am using the function and getting the accuracies. Let's see, let's run it and see what happens. So I get a 97% accuracy, a 93, 95, 97, 97. So see that, because it was just a case of class imbalance that was giving us such low accuracies. If you see now that the accuracies have boosted a lot. Now it's for you guys. I will leave it to you guys to again go ahead and see what is the F1 score. The F1 scores should be good enough as well, or should be better than what we were actually looking at before. Now let's look at undersampling as well. It's the same thing, but it goes on to undersample. Let's see what it does after undersampling. So the X shape. I think I miswrote something. Before sampling it's 12. It just should have gone down. I think I missed the, okay, I missed the weight altogether. Just copy that. I think it was a typo, or I missed it by mistake. Let's see what is value print y shape y. So okay, I've created 280, 280. I think it's replicating the samples, but it's fine, not an issue. For some reason, the weights isn't working that way. Work. Something. So that I have 200 samples. Okay, I think it's taking the majority class and it should have reduced it to the minority level. But anyways, if I have both the classes, this is again doing an oversampling thing only, a mix of both, an oversampling and as well as an undersampling. So the same thing where we use undersampling, transform DF, and undersample the data. So I don't know, summarize the data, summarize it on top. Yeah, so you define the data set, take on the weights, you use a random undersampler for this and undersample the data, use the X and Y undersample and dot fit dot resample for X, Y. And I want to print the shape just to see that if they are of the same shape. Taggle sometimes acts up, or maybe I've made a typo error. I will make the change in the original file if there has to be any. But for now, we have a 280, 280 cross thing here. It was the shape here. It was 140, 140. Okay, not an issue. The shape is also higher. Shouldn't be so high. Should be somewhere around 140 something. Anyways, not an issue. So we'll work with the data we have. Let's run it again. We're going to see that the data is giving us around about 87, 88% accuracy for all the methods that we have used. So that's what undersampling and oversampling was. So undersampling is basically reducing the X samples to the number of Y samples, but for some reason it's okay. I think it's, let's check that. So let's pronounce it. It says that I cannot use that. It's going to be the majority. We should have reduced it, but not an issue. But yeah, basically what undersampling does is, so if you have, say, in this particular case, we had 148 records from 1 and 7 records from Y. So this would have cut down the X values by randomly selecting 67 values and making it equal to 0. Now, undersampling is usually not preferred that much. You can use a mix of both, like oversampling as well as undersampling. But undersampling reduces your data set quite significantly. In this particular case, we had 67 rules. But say if you have a fraud detection case where you have 10:1 ratio, where you have 1,000 records and you just have 10 records from the, you have just 10 records from the other class, the ones that you want to predict, the fraud or not. The fraud rarely occurs, so that's why you have lower number of records. The other transactions happen on a regular basis, which are non-fraudulent. So that will give you a high class imbalance. Now, in that particular case, if you go on to undersample it, you will have just 20 records to go through. Now, that's not a good case. So in that case, you should oversample. In this case, we have a 52:1 ratio. So you could use either of the two. We tried it out just so that we could understand how it works. But yeah, try out undersampling and oversampling for all the remaining data frames. For data frame 2 and data frame 3, that is one of the homeworks. And the other homework that you have is going to use decision tree regressor for the linear regression Python. Now that you know how decision trees work, and you just need to use the decision tree regressor, that should give you a better accuracy compared to the linear regression. But test it out. You will understand and stumble upon a few things and try to rectify it. That's how you're going to learn. That's how I learned. So that's how you're going to work. So that was all from classification. We're going to look into other algorithms from unsupervised techniques now after this. So in this video, we'll look into clustering, that is unsupervised learning. So what is k-means clustering? So we basically choose an arbitrary value of k, and that depicts the number of centroids, which in turn depicts the number of clusters. Now the distance from the centroid is then calculated, and the centroid is the least, and the centroid with the least assigned with the least distance between the point is assigned the particular data point for that particular cluster. Now the cycle goes on till the centroid value doesn't change significantly. So if you saw the particular GIF that just stopped now, because it started off from somewhere here. So there were 4 green points. Those are the centroid points that we assumed initially, and then it went on to check the distance between each of the points. And this particular point was closest to these points, and so on and so forth. And it stopped only when it wasn't able to find a center point it wasn't able to optimize the center point anymore. So taking this cluster as an example here, the leftmost cluster, you see that the center point is this, and even if it calculated the distance with the other points in the other clusters, it wouldn't change the center point because this is the only cluster that is going to take into consideration. So that's how k-means clustering work. But whenever the value of k comes into mind, we go on to think, how do we optimize it, or how do we find the value which is the most optimal? There is a way for it. So how do we find the most optimal value of k in k-means? We use something called the elbow graph. Now, like KNN, k-means is also an iterative process. So the graph plots the value of k against the amount of distortion in the data points. The point goes after which the graph, so the point at which or after which the graph plateaus is called the elbow point. So if you look in here, when the value of k was 1, there was a high amount of distortion, and it goes on reducing. So it reduces drastically from 1 to 2 and 2 to 3, but beyond 3, the change is really, really narrow. And obviously, if you go on to see, it will be decreasing, obviously, but we want it to be optimal. Okay. Now, if you want it to be 100% accurate, you can just choose the number of data points in the data set and go ahead with that and consider each point as a cluster, but that won't solve the problem. So over here, this is the elbow point after which the data kind of plateaus. Okay. So that's how we go on to use the, that's how we go on to optimize the k value for k-means. And we already saw how the clusters are created visually. Let's implement the same in a data to understand how it works. So we are using the IRIS dataset, which is a pretty well-renowned dataset for clustering and classification purposes. Now, it was basically created by R.A. Fisher. You have a base description about the entire dataset here. You have the attributes here. But what we want to look into is the line that I've tried to highlight here. It basically says that one class is linearly separable from the other two, the latter are not linearly separable from the other two. So we cannot just use basic SVM to separate them, because it won't work that well, because on two of the classes it might work really good in one of them but not on the others. So let's see how it goes about. So we already see the attributes here. We have sepal length, sepal width, petal length, and petal width. We have three classes: iris setosa, versicolor, and virginica. Now there's a small note that I found on the website where I got this data. I think it's from UCI, and uh, it said this particular line, which I've mentioned here. So the data differs from the data presented in Fisher's article. The 35th sample should be this, where the error is in the fourth feature. The 38th sample should be this, where the error is in the second and the third feature. So we need to rectify this. So there was this one line that I came across in the data set that I found. On the website where I found it. So I've mentioned it here. It basically says that the data differs from the original Fisher's article, and the error is in the 35th sample, where the problem is in the fourth feature, and the 38th sample, where the error is in the second and the third feature. So we need to look into this while we are working on it. We'll make the changes as we come to it. Okay, so I am going to use SciPy for this for one of the clustering types. So you can install it right now, or you can install it once we come to it. So these are the basic data. We are going to see what is k-means, dbScan, and why are we using linkage and dendrograms and cut tree and so on. But for now, we just consider on k-means, and we go on to understand what is the data and how do we go about it. So I imported the data, but as you can see, I've given it the names as well, because the headings, sorry, we did not have a heading at all. So I had to give him the names. Okay. And I made the index column as none so that it doesn't make a separate thing. Now this is df.head gives you the basic first five records for the data frame, and this is how it looks. Now coming to df.shape, it has 150 number of rows and 5 columns. We already know that from the description, data description. Now rectification, as I said that there were two rectifications, the 35th row and the 38th row. So I go on to say df ilock this 34th row, because 35th row will be the 34th index, because the indexing starts from 0, as we can see here. So we change that, and we go on to change the 38th row, which comes to the index of 36. When I checked, it was the index of 36. So I'm changing the 36th index value here to this. Now you can see that I've listed the changes here so that it's easier for you to understand as well while we are at it. Now we go on to clean the data. Now there are no missing values here, but I did found two duplicate values using the df.duplicate function, as we have seen earlier as well, and summing them up to see what is the total number of duplicate values. So after removing or dropping those duplicates, I now have the final shape as 148 rows and 5 columns. Now going ahead, we see the data transformation. But so we have the labels here, the initial labels. Now print df class.count values. I have the values here. A basic count plot to see which are the two classes that were affected or had duplicates. So we see that versicolor was fine. The other two classes, virginica and setosa, were affected, where they have a single record lower than the other because there were duplicates. So that was removed. Now coming to, so I did not use label encoding. I manually encoded it. Sometimes it's just good to manually encode it so that you know which is what. And after doing that, it looks something like this. Okay, so let's just, I think you can also check it out which index is what. So if I say, let's see, df.class, and what does it give? Sorry, I had to run everything. take a moment. So what basically I'm trying to do over here is to get the value for the first class, or the value of class for the first record, and then let's see what happens. Okay, I think I did a mistake. I think it should be iLock. So I see that the first class is 0 here. So I'm just gonna check if my labels is working or not. What is my 0 class? It's Setosa. So you see that there were 49 Setosas, and 2 I think is this Virginica, and 1 is versicolor, that is 50. So that works out. So that's what basically I was trying to figure out. Now going ahead, I'll just rerun the entire thing so it's easier. So I have the count plot for class df here again, just to show after the data transformation as well, the counts did not change. They are the same, just that the labels changed. Okay, so 2 was Virginica as I suspected, and 0 was Setosa as we saw. Now coming to the data visualization, here is a pair plot. Now initially we read that there were 2 classes that were linearly inseparable and 1 class was linearly inseparable. So 0 is, I think, Setosa. Yes, it is Setosa. And if you want to see the petal length, we can linearly separate the 0 class. It's different from the other 2. And so is the sepal width. Sorry, it's the petal width and petal length, and it's linearly separable. The others are not that linearly separable, but if you can see, so basically the class that the writer or the particular node that was written, it was basically for the class 0, which is nothing but iris setosa. So that can be linearly separated, but the other 2 are kind of do have overlapping features. So we're going to look into that and how do we go ahead with it. So I've mentioned the same over here, and splitting the data into x and y terms. So I'm splitting it here, the same thing, nothing new. Now coming to model building and k-means clustering. So clustering again doesn't need the y labels, or basically doesn't classify it to iris setosa. It just says that it is all those points belong to a particular class, or and we're going. Oh, sorry, it belongs to a particular cluster, and the cluster is not defined. So what does that cluster mean is not known to us. It basically just says that it's a cluster. But we're going to take it a step ahead and try to understand how good it was in general. So k-means clustering, I import the k-means module from sklearn.clusters, and it's a basic thing. So k-means, I'm giving it the n clusters, so the number of clusters that I'm defining initially is 5. Setting the random state, nothing new. Getting the y predicted, k-means dot fit predict x, because I'm setting it the entire x. There is no need of train and test. So this is what, these are the clusters that it gave out. Going ahead, I see the centroid values here. If you go on to see, I'm giving it the value of 5 for 5 clusters, and it has approximately 4 and 5, 20. So it's basically going for 4 iterations, and after every iteration, the centroids change. So that's what is happening here. Now I'm just defining a color palette so that it's easier for us to visualize whatever we're going to do next. So here I'm basically going on to see, I'm making the k-means clustering, that these points, I'm setting it to a cluster, and I'm trying to plot that. So I see that this plot is fine. So I think I'm plotting this petal length and petal width, correct? So petal width and petal length. Yeah, I'm plotting that. And while I'm plotting that, I'm just setting the hue or the labels or the legend as the one that I predicted, and giving the color palette that I just defined. You can have a look at the other color palettes at sklearn documentation. But yeah, this is the one that I chose. It's just there. It's easier to identify the colors. Now going ahead, you see that is the same code is written here. I'm just using the subplot function here again. It's not something new that we haven't looked into, but I'm setting the hue as Y over here to get the actual clusters. So I know that there are more number of clusters here and there are low number of clusters here. This is identified correctly. So the 0th label is okay for both. And because of the more number of clusters, this section gets a bit clustered out in the wrong way. So we basically had 2 clusters here, but we are setting more number of clusters and the clustering is not done very greatly. Now remember we looked into elbow curves, elbow graphs. Let's just look into that. So I'm just setting the value, the error value here so that I can understand which has the more number of error values, giving it a range of 1 to 10, 1 to 11. So less than 11 is 10, so 1 to 10. So basically my minimum value of k will be 1 and the maximum value of k will be 10. I'm going to iteratively make the model, check the error term, plot it, go ahead with the next k value, and so on and so. So I fit in the x values to k means and error.append. So I'm basically appending the iterations over here, and when I go on to plot it, I use range 1 to 11 and the error that I have, the error list that I've made here. So I'm plotting this line graph, making it the title and the x labels and y labels, the general thing. And after I do plot.show, I see that there's a drastic change from 0, 1 was the initial one. So 1 to 2, there is a drastic change, and 2 to 3, there's another fall. But after 3, it is kind of flattened out, correct? So we understand that 3 should be the optimal number of clusters and not 5 that we initially chose. Let's see what is the change now. So I have made the value as 3 over here, the random state remains the same, and I've done the same plotting. It's exactly the same. So I've just copied and pasted it here, nothing different. So I wanted it to be exactly the same so that you understand the difference. So the colors may be different because again, I told you it doesn't have the Y labels to identify which particular cluster is labeled what, but it does a pretty good job at identifying, right? So this identification was correct even in the initial stage when the K value was 5, but the cluster over here has improved a lot. So you can see that the class 2 over here and the class 2 over here, the original cluster is kind of similar to the one that our k-means clustering is doing. And so is the second one. Obviously, it's not going to be 100% correct. So the class 1 does have a bit of overflow here, but it does a pretty good job. So we can see that k-means clustering is actually pretty good at doing its work, and we're going to validate the outcomes at the end. But visually, we can see that it's doing a pretty decent job. So checking, I just wanted to check the difference in the values. So these are the original values, and I can see that class 1. So I know that this class is 1 over here and this class is 0. The 0 and 1 should be same as we see. Now I know that the blue is the 0 here and the 1 is the one that it corresponds to over here. So 0 and 1. So 0 over here, sorry, this is the k-means graph. So the 0 over here is equivalent to the 1 over here. So 61 and 50, it has 11 more points here, and obviously it will have 11 less points here. And so we see that there's an error of 11 points that have been misclassified to one class and so on. But it does a pretty good job, correct? Now let's look at the other clustering types and how do they go ahead and then try to compare which is a better clustering algorithm. After looking into k-means clustering, now we look into hierarchical clustering. So we basically use something called a dendrogram. Now this is what a dendrogram looks like. And there are two approaches to creating a dendrogram or interpreting it. Either you can have the top-down approach. So consider all the data points to be one single big cluster and then go on to split it. So basically this is the point you start off from, and then you go on to split it on the basis of the criteria that you go on to select. Or you can have the bottom-up approach where you consider each point to be single clusters like here, and then go on to club them as you go ahead till you have a single cluster. These are the two ways, and this is how you're going to depict it. Hierarchical clustering is best visualized using the dendrogram that I've presented here. So we can see that we have a few points and it goes on to cluster then the ones that are near. So this is one of the graph. Now the second cluster is being created. That's the second cluster. Now after the third step, the entire thing is clustered into one. So that's what this says. So basically it says that there are 2 to 3 clusters in the entire thing, and you can cut it. So basically, how do we select the number of clusters? It's the vertical height, whichever point has the maximum amount of vertical height, we take in the lowest number. So we cut it somewhere here. So you can cut it somewhere at say 2 or 3, whatever, here, somewhere here. And now in each case, the distance is calculated the same way. So it doesn't make a lot of difference if you go on for the top-down approach or the bottom-up approach. So we'll wait for the graphical representation to end. So now we have 5 clusters. Going ahead, now we have 3 clusters. Going ahead, now at this point, it says that it is the optimal number of clusters. So we want to say that take the 2 clusters. Now there are different kinds of linkage that you can use. 3 to be more precise. There is single linkage. So for 2 clusters C1 and C2, the single linkage returns the minimum distance between 2 points I and J, such that I belongs to C1 and J belongs to C2. So in this, consider that these two are 2 different clusters and they have 2 points, I and J in them. So C1 has I and C2 has J. So whatever is the minimum difference is calculated, and that's how the clusters are created using the single linkage. Now complete linkage is just the opposite. So you consider I and J such that it belongs to C1 and C2, that is there, but it actually takes in the maximum distance, not the minimum distance. So that's the only difference. Now coming to the average linkage, it takes, as the name suggests, is take the average distance. So for 2 clusters C1 and C2, first, for the distance between any data point I in C1 and data point J in C2, and then the arithmetic mean of the distance is calculated. So that's how these are the 3 different values, and you can even use it in the code and try to see out. That's what we're going to see now. So you can put in various linkage values and go on to see how good or how bad does the particular clustering algorithm performs. So the hierarchical clustering code is somewhat similar to KV. It's just that we're going to look into the graphical representation of it. So we're going to see what and how we want to. So we basically take in the linkage and dendrogram and cut the function from a SciPy cluster.hierarchy. And we are using the single linkage here. So that is the minimum distance between the 2 clusters. So merging, because the linkage is basically what it's basically doing is merging. So I've just named the variable as merging. I use the linkage function, pass in the x values. I say that the method that I want to use is single, and the metric is Euclidean. The distance is going to be calculated on the basis of Euclidean distance. And I go on to have the dendrogram and plot it. So this is how the dendrogram looks. It is kind of clustered at the moment, like it's cluttered, if I have to put it in the way. But we still see that this is one cluster that it forms, and this is the second cluster, and we see that this section has the highest vertical distance. So the lowest point of the highest vertical distance is the thing that we're going to look. That's what we are looking for. Okay. So over here, it's not that intuitive, but we know that there are 3 clusters. So just for the sake of it, we're going to take in 3 clusters and we're going to run this. So you see that there are a few 2s, a few 1s, and a few 0s. And that's how it is. Let's see what the clustering over here looks like. So I've passed the same thing, the same function goes in here, and you can have a visual understanding of which are the clusters that are not performing very well. So the 0 cluster over here and over here are distributed evenly, and pretty well done. And here we see that there are 13 misclassified records in cluster 1. So we see that here, we can visually understand, right? So this is the original cluster, and this is the hierarchical cluster, which says that cluster 1 has a few more points here. So that's what it is misclassifying. But that's what is expected because the cluster values are overlapping. So it's understandable. We are going to have a few misclassifications, but it's fine. So that was single linkage. Now let's look at complete linkage. We see that this is the minimum distance. I mean, we should cut it at 3. It's pretty visible here. This is the I've just changed from single to complete, and that says that you should cut it at 3. So you're gonna cut it at 3 and rerun it, and this, and you can see the clusters are kind of similar. Let's see how many difference. So we still have a difference of 13 data points, but it is kind of similar, and surprisingly the color also has come out to be similar this time. But yes, so we have 13 different points in both the ends, the two classes that are overlapping. Now let's look at the average linkage. Here, in this. So a dendrogram usually takes some amount of time, so that's why I had pre-run it and kept it. But anyways, so we see that it says that it's 2, but we know that there are 3 clusters, so I didn't put it this way. But if you have to read it, you go on to say that it's somewhere around 2 here, which is not correct. It is not doing a very good job. So average is not doing a very great job. The best by far is maximum complete, which takes in the maximum distance. By far that is the best now. So we'll take that, maybe run it after this. Okay, so we already ran them. We still have 13 values that are, sorry, we are looking into this now. We run this, this. We still see that there are 13 points that have been misclassified. They might be different, but yeah, we still have 13 points that are misclassified. So k-means is still at the top, winning the game. Let's look at the other clustering algorithms. Third method that we are going to look into is dbScan. So dbScan considers only 2 parameters, that is epsilon and minimum number of data points. So epsilon is you can consider it to be the radius as per se, but it's basically this particular boundary, and the boundary is created by the radius. That's why I mentioned that it can consider it to be the radius. And the minimum number of data points is something that we want to look into and understand. So there's something called the starting point. So I'm just trying to brief you about the terminologies that we're going to look and understand. So we have something called the starting point. So that's a random point which we choose in attempt to make the cluster. Over here it's depicted by the green point. Then we have something called the core points. So the core points are all the points which fall within the epsilon of that starting point. So the gray points are basically the core points here. Now coming to the minimum number of points that we referred here, is the total number of points that should be within the epsilon, including the starting point. So basically is the number that depicts the minimum number of points that should be within the epsilon. So if this is the point that we're considering and this is the epsilon that we're considering, and if say the minimum number is 3, so this satisfies. But if say the minimum number is, so here we have 7 points, if say the minimum number is 8, this particular point will not be able to make it to a cluster. So that's what it is. And dbScan also classifies as it can also classify noises. So consider that this is a cluster and these are the points that have been left out after the entire clustering process is over. So we'll consider these points to be noises. We'll look into the demonstration in the practical part of it. But let's go ahead. So we have also something called the border points as well. So now once so this is not an atom structure, it's just overlapped epsilons, but let's see how it works. So we have something called the border points. So once you have the starting point and the core points, the core point goes on to make its own epsilon and tries to, expand the region of the cluster. And that's how you go on to add in more and more points. In this case, maybe this score point, and this score point, maybe these two core points are the points that have an epsilon, which take in the other 3 points lagging outside as well. So these are called the border point. Okay, so starting point, then you have the core points that are created by the starting point, and then you have the border points that are created by the core points. So you see that's the flow of the DB scan, and that's how it expands its scan. But yeah, that's how you go ahead. So let's have a visual of the very same thing. So you can click on this particular link and it will redirect you to the place where I'm going through, and you can, have the same visual effect on your laptops as well at the same time. So this is Mr. Harris's personal blog where he has created a code that simulates DB scan, which is pretty good. So let's consider, say, packed circles, and so this is the epsilon value. I can reduce it, say, to 0.5, and then the number of samples to be 3, and then let's say go. So you see that it iteratively just goes on selecting various points and then goes on to cluster each and every point. So this was a different point, this was a different cluster, this is a different cluster. And it will go on doing it. Just restart into something that's, let's say, a Gaussian mixture. Okay, so we can clearly see that there are 3 clusters. Let's try to reduce the values such that, there are some noises so that we can understand. So this will just consider the extremely dense centers of the cluster, and the other points will be left out. So you see that these are all the white points that are left out here are considered as noises. So you see that they're really, really dense here. Now we start Gaussian mixture. I just keep it to the default values and say go. Let's see what it does. So you see that it's pretty fast now because there are more number of points and higher epsilon value, so that it considers more points inside it faster. So this cluster is correctly classified as 1. You still have a noise point over here, which is correct. And this also has a good point. Yeah, so that's considered. So you see that at the end it shows noise points. So that was the visual understanding of DB scan. Now let's go back to the presentation and understand how we validate these clusters. So validating clusters. So basically we are using, there are various validations, but I found this to be the most optimal one. There is something called the adjusted RAND index. RAND stands for random. So RAND index is a function that computes a similarity measure between 2 clusters. For this computation, RAND index considers all pairs of samples and counting pairs that are assigned in the similar or different clusters in the predicted and the true clusters. So it considers both of them, the pairs and the counting pairs and so on. So afterwards, the raw random index score is adjusted for chances that there might be a chance that it, misclassifies. So it adjusted for the chance into adjusted rand index score by using the following formula. So the formula is random index minus expected random index divided by maximum random index subtracted by expected random index. So that's how you go on to calculate the random index formula. You don't have to remember this, just understand what it does. So it's basically used for cluster validations, and it takes into consideration the points and uses random indexing to go on to satisfy or help us satisfy the need of giving us a score of how accurate our clustering algorithm works. So that's how you go on to validate it. Let's look at the practical aspect of it now. So now coming to DB scans. So I use the dbscan function from sklearn clusters. I have mentioned the package name at the top. You can have a look at it there. So I put it into dbscan variable. db clusters is equal to dbscan fit predict x. So it predicts these values. If I just print, I just wanted to see the value. So this is this. Now, usually when people see this, okay, there is one and there is -1 and then there is 0. Okay, so now there are 3 clusters and my dbscan has done a good job. Well, that is not the case. Remember when I said that it also has noise points, we visually saw them. So -1 refers to the noise that it identified. So basically there are 2 clusters, 0 and 1, and then there are the noise points. Let's look at the visuals to have a better understanding. Let's print it out. We see that basically it said that there are 2 clusters and there are noises. So uh, so it doesn't do a very great job, right? So it even has 1 less point in 0. It says that it goes into noise. There are a few noises here as well. An entire cluster is missing because I think maybe they overlapped and dbscan could not identify the overlapping thing. But yeah, it didn't do a very, very great job. So let's see how the data performed. So we make the models again and go on to work on it. So now I'm just using the ARI, the adjusted rand index. We already saw the formula, so I'm not going to discuss that again. But let's see how they perform. I'll just run them again and see. So hierarchical clustering is doing a good job. And merging is based on averaging because that was the last thing that we used. So merging is average, you see here. And that's the very same thing that is used here. So averaging gives us a 77% accuracy. K-means is giving us a 74% accuracy. dbscan is not giving us a good accuracy, as we saw. It's giving us a 51% accuracy. So that's what it was for dbscan as well. Now, for your homework, I would like you to replicate same thing for the placement data set. So how do you go on to do that? You go on to remove the salary and the status column and then go on to see how it works. So basically your Y that I've used here will be the status column. So when you split your data, you will have all the features in X and you will have Y as the status, and you remove the salary. That is, I don't feel that it will be very helpful, but you can put it as well. Try it out. That will be a great experiment. So you have the status as Y and the other things as the X. You use only the X and then try to plot something similar to see what visually where the model went wrong. So over here, I can see that the model went wrong in these 2 clusters where the clusters were a bit overlapping, and it considered it to be a single cluster and made this cluster very, very big, and also came up with some noises, which currently or according to the original data set, they are not noises. They are actual data points that come in the cluster. So that's how you visually understand clusters and go about it. And coming back to the homework, you use the placement data set to go on to work with the entire thing and just follow the same steps. Use this as your guide to go ahead, and I hope you understood what clustering is. And yeah, that was your homework. So in this video, we're going to look into ensemble machine learning techniques. So one of the machine learning techniques which is ensembled is bagging. So we have different machine learning ensemble techniques. One of them is bagging. So it is a technique which takes the mode value, the outcomes predicted by the various machine learning models. So the point that is important over here is it takes the mode value and there are various machine learning models. So there is more than one model that comes into picture when we talk about bagging. So ensemble itself means multiple models that are working together. When you talk about ensemble machine learning techniques, there has to be more than one model that is involved in that particular technique. Now, there are various weak learners. We call them weak learners because maybe individually or just by themselves, they are not able to do a very great job at predictions or classifications. So we go on to cluster them, or we go on to combine them to improve their performance. So there are various weak learners, and you can combine them in a way that all the outputs are taken into account. Now, taking an example, consider that I have a logistic regression value. So I have a logistic regression model. So one of the model is logistic regression 1. Now I have 3 models such, and all of them might have different parameters and all, but they ultimately are logistic regression models. Now the first model predicts 0 for a particular record, and the second one predicts a 1, and third one predicts a 0. Now in this case, the mode value will be 0. The modal value should be 0 because 0 has the highest frequency. So that's what I meant by we'll consider the mode value. The final output that this bagging technique will give us. So this bag over here will consider 3 models, that is logistic regression 1, 2, and 3, and the bagging technique will give us 0. Now, how do I go on to say that, okay, so 0 has the highest frequency? Do I sit down and calculate it? So no, but there are concepts that do it for you. We're going to look into it. So there is something called the voting classifier. Now the voting classifier is the method that checks the frequency of the classes and predicts the outcome for the given input. So basically, after passing through the logistic regression models, the data is then passed through a voting classifier. So there will be a section over here where all the 3 inputs are passed to it, and it calculates, okay, so there was a class 0 that has a value of 1. Now the next time there is a class 1 that has a count of 1 now, or a frequency of 1 now. Now the third time you get 0 again, so now we increase the value of 0. So now the ultimate, you can conceptualize it as a form of a dictionary, where the 0 will now have a frequency of 2 or a value of 2, and 1 will have a frequency of 1. Now, because 0 has a higher frequency or a higher value, we go on to predict that value for that particular way, which we had initially passed to these 3 models. So that's how voting classifiers are better, where you take an average, or basically not an average, but you basically take a mode of the particular class. So that was voting classifiers. Now there is something called bootstrap sampling. Now basically, if you go on to use bagging techniques, generally they use decision trees, and that is the base estimator or a base model that we consider. We can obviously change the models. We're going to look into that in the practical section of the video. But just for knowledge, you can have different models. Now consider the bootstrap sampling to be a sampling technique where you want to use the data with replacement. So what is with replacement? What is without replacement? So consider that you have a bag which has 3 red balls and 2 black balls. So if I go on to ask you what is the probability of a red ball, you will say, okay, the probability of a red ball is, there were 3 red balls and 2 black. So the probability will be 3 divided by 5, correct? Now, if I go on to remove that ball and ask you to, take a sample again and consider and tell me the probability of a red ball now the probability will be different than the initial one. So initially I had a probability of 3 by 5. Now after I've removed a particular ball from the bag, I have 2 red balls and 2 black balls. And you go on to see that my ultimate probability of getting a red ball is now 1 by 2. But with replacement examples, we basically consider that the ball that was taken out is kept back inside the bag. So the probability remains the same. So over here, what basically it means is that you can have, say you have 5 records and 3 models as we are considering. So 5 records and 3 models. So you say that, okay, I'm going to train on 3 and test on 2. So the first 3 record is given for training, and the latter part is given for testing to the first model. Now, iteratively, there can be situations where the second model or the third model also has similar records or same records that has been transferred to train and test. So that's what basically bootstrap sampling means. Now let's look at the practical explanation of the same to understand it better. So we are using the same placement data set for an example for ensemble techniques. So we have seen this function before where I go on to see what is the average accuracy considered that I'm passing a data frame and a model. Now I haven't done oversampling, undersampling yet. I'll do that at the end. And we are going to see how it goes about. So I'll just explain the function again. So you have a stratified k-fold over here where the random state is 12 and the n splits are 10. I have a list over here where I'm going to add in all the accuracies that my model is going to give. So basically it should be 10 because I'm giving n splits as 10. So there should be 10 accuracies. In here I'm doing the x and y split. And on the basis of that, I'm giving x train, x test, y train, and y test the values on the basis of the indexes that the SKF function is giving. SKF basically is stratified k-fold. And that's how I go on to get the train test split. After that, I fit in the model that I passed into the particular function. And on the basis of that, I go on to calculate the accuracy by using the model.score function on x test and y test. And after that, once I'm done with this entire loop, I come out of the loop and I override the value of all accuracy by summing up all the values and dividing it by the length. Again, I'll just repeat myself that, you can also put in the value as 10 over here because the n splits are 10. But just to make it more dynamic and more user friendly, you can just change the value here and it will still work. So that was about the function. Let's go ahead and see the things that we've already seen. So this is a basic logic regression function. I haven't done a lot of parameter tuning. I'm just making the function and passing the general function in, and I'm getting accuracies like 81, 77, and 78, 51. So that's fine. That's a pretty good accuracy considering that we have a class biasness. Now, same goes for KNN. I'm considering 5 neighbors and the algorithm as a brute. And I go on to see that it gives me approximately the same values for all the data frames, 75, 75, 76. Coming to naive Bayes, again, a general classifier, nothing like I haven't done any parameter tuning or haven't passed any parameter, just the default parameters that the function already has. Now, seeing the accuracy, it's 77, 76, 78, approximately in the same range, 75 to 78. That's what we have got up till now. I think the lowest is 75.17 that KNN gives for data frame 1, and the highest is 81.75. So same for SVM, we get consistent result for all the data frames. Now here I've given in the values as 5 and 5. Let's just say that I give in the value as this. So let's see what happens. So I know that 0 class has more. I'll just change that and see what happens. Okay, so basically class weights is not required for us because it has equal class weights. Just work that way. So 7778. This is okay. I'm just giving the values as 5 and 5, even though I'm giving it the same class weights, the accuracies are different. So I'll just put it this way, not an issue. And I'm setting the probability as true because we're going to need that earlier ahead in the coding section. Now coming to the last model that we took into consideration, that is decision trees. No parameter tuning again. And I'm getting values as 71, 68, 75. Obviously, it needs to be parameter tuned. Overall, we can see that the DF3 has the least amount of parameters and gives us a good result, more or less, apart from logic regressions where I have data frame 1, which gives us a better result. But more or less for the other models, this DF3 gives us a pretty good accuracy. Even for logic regression, we get a 78.51. That is almost that's almost 80 according. So it's fine. It's almost near. So we'll just consider the data frame 3 for earlier experiments. So because of the very same reasons that I've listed here, that it gives you the best accuracy approximately for all the models. Now I've just printed out the results here. I'll just print it out again. So it gives you these accuracies for DF3. I've just mentioned that ahead. So just for our reference. Now coming to the ensemble techniques, we'll firstly look into bagging. Now, I think you've already heard this term before, but I don't think you know what it means. So there is something called random forest, and this is one of the go-to techniques for all machine learning developers whenever they are looking into classification techniques because of its accuracy and uh, easy to use. We know that in the basic techniques, decision trees do a pretty good job in general, and it tends to overfit. Now, random forest is basically used to overcome that particular shortcoming. Now, remember that I told you that decision tree is overfit. So what does random forest do different so that it overcomes it? So it obviously uses decision trees that we have mentioned, the entropy here and the max depth. These are the same parameters that you see in a decision tree. So it basically has, it doesn't take the entire decision tree into consideration. It takes something called a stump, which is a smaller section of the tree. It doesn't take the entire tree into consideration. So you get a probabilistic answer. That is one. And two, there is still scope for improvement. So a split is not done in such a way that at the end of it, you only have a particular outcome. So say there is a gender split where the left, the left section only has male and the right section only has females. A split in random forest decision trees will look like two males, 2:1 female, and 1:2 female on the right and the left section respectively. So that's why it is considered better, and it overcomes the shortcoming of a decision tree when it comes to uh, overfitting the data for the training data, obviously. So we look into the accuracy for the very same. So I basically use sklearn.ensemble. We are going to use all ensemble techniques. So ensemble random forest classifiers, which is again a bagging classifier. It bags decision trees only. And here we have it. We are using the random forest classifier function, giving it a few parameters. And you can always go ahead and play around and see what happens if I say give max leaf node as 2. So initially with max leaf node as 3, it's giving me 78.96 accuracy. Let's see what happens now. It's going to take some time because it considers a lot of estimators. Let's see what are the default values. So the n estimators is 100. When I say n estimators, it basically means the number of models that it's taking into consideration. That is 100. So it's going to take some time when it gives you the outcome. So I'm going to set it back to 3 because that was giving me a better outcome. I'm going to keep it that way. Now going ahead, let's look into the bagging classifiers. So I have a logistic regression bag. Okay, so I'm bagging all the logistic regressions. We already saw what the decision tree gives us, but we're going to see what bagging a decision tree gives us different. So we saw when we say that random forests are equivalent to bagging a decision tree, we're going to try to justify that statement. So over here, I'm using the bagging classifier from ensemble technique, same here. And I'm saying that the base estimator over here that I want to take into consideration is a logistic regression. Now, you can always go ahead and, use the class weights and other parameters of this particular model as well, setting the n estimators to 100. Now, generally, most of the techniques have n estimators as 100, but sometimes so over here we have n estimators as 10. Now, if I'm going to compare two models, I have to have most of the parameters same. So if you go on to see, I'm keeping even the random state similar. Okay. So just keeping that in mind, setting the n estimators as 100. Coming here, I do the same. The only change that you will see is that the model over here changes to KNN classifiers, where I'm setting the algorithm as root and the nearest neighbors as 5. Coming here, the thing changes to Gaussian naive Bayes. In the fourth model, I'm considering SVMs. So I'm doing that it's kernel, class weights, and estimator at 100, and so on. Decision trees over here. So this is what we are trying to compare. Now I'll just rerun this just to see. So it's obviously going to take some time. It has got approximately 500 estimations that it needs to take into consideration. 100, 100, 100, and 100. So 500 here. See, we got 3 outcomes here. It's still running. As you can see, it's going to take some time, but it's going to give you the output. So you see that I bagged the logistic regression. I'm getting 75.76 value. Bagging KNN gives us 76 again. 79 naive Bayes gives us a good accuracy. SVM gives us a good accuracy, a 79% accuracy. Coming to bagging decision tree, this gives us a 76.21% accuracy. So if I go on to see here, it was higher. Okay, so there are a few changes, but you see that it's not really high. It has a percent, it has a change in the second decimal place, so maybe a percent or two's difference. So that's what it is, but generally they do have similar outcomes. They cannot be exactly the same, but because of the other parameters that you need to take into consideration, but they will be more or less similar. So we do justify that part. Now coming to voting classifiers, now we said that we use voting classifiers, or bagging uses voting classifiers to simulate something. So we will use it to simulate something similar to bagging. So I go on to import voting classifiers from Ensemble. I say voting classifier hard. So basically I've got hard and soft, and let's see what does that do. In this case, the accuracies are not that different. I'll just rerun it to see what happens. Here you see that the accuracies are not that different. There's a percent accuracy difference in hard and soft accuracy. So coming to logistic regression, so I'm setting logistic regression over here, log R. So I am not recreating them, but you can obviously recreate the base estimators that I'm creating here. You can always create it here. But basically, these are the models that we created earlier. Remember when I told you that we are going to use it so earlier? Yeah, see, SVM, naive Bayes, NB, KNN. So these are the very same models that I'm going on and recycling and using it again here. Just the only thing is that the voting is hard and soft. So we'll see what does it mean in the description, what they have mentioned. But generally it's the same thing, just the voting section is changed, and I'm checking the values for both. And you can obviously see that there's a percentage difference. Let's see what does voting hard and soft mean. So estimator voting hard and soft. If hard uses predicted class labels for majority rule voting, else if soft predicts the class label based on the argmax of the sum. So it's basically argmax is another function that uses probabilities. And hard is basically the modulus thing that we looked into the presentation. So this is what most of the bagging sections does, but you can also use voting as such. So that was more or less all about bagging techniques, voting classifiers, and random forests. And whenever you are, so after this course, when you are actually interested in machine learning and data analysis stuff, so we are going to participate. I hope that you participate in Kaggle competitions. You can see a lot of competitions that are posted on a regular basis over in this section. And once you do that, I hope you use ensemble techniques, or if you even do not participate, you go on and see other competitions that have closed, and you can still see the code for them because people publish it. And you can see that most of the codes will have ensemble techniques if they are using machine learning. Most of them will be either boosting or bagging. We're going to look into boosting in the next video. But generally, people go on to use these techniques to overcome the shortcomings of the models. So we saw that logistic regression or KNN naive, they somehow the predictions are not that reliable because they are based on the random state. And if the random state is different and there's a different sample that takes into consideration, the model fails to perform very well, or the average accuracy reduces drastically. But in the ensemble techniques, because we are averaging out the outcomes or basically taking the mode of various models, we go on to overcome that particular section. Okay, so other difference why I use voting classifier and showed you this particular thing is, here we are using different models to get a particular outcome. So even though we have a binary class problem, say there is a value that is predicted by logistic regression, a different value predicted by KNN, a similar value to logistic regression is predicted by naive Bayes, and so on and so forth. What is the outcome? And here basically when I say that the base estimator is this, and I'm creating let's see, okay, I'm creating an estimator that's 100. So there are 100 decision trees that I can. Okay, so you need to keep that in mind. So what is the difference between this section and this section? Okay, over here the same model is created 100 times, and based on the various sampling techniques, like we saw the bootstrap sampling, based on the sampling data, the decision tree goes on to give you different outcomes, and that's how you go on to bag the outcomes and give you, then that's how it gives you a better accuracy. Now going here, we have different models that gives us different values, obviously, and we go on to use either voting as hard or soft and then get the best out. So that was more or less all that you needed to know about bagging. Now let's look into the other models.